So, ladies and gentlemen, please grab your food, your drink, and let us start. I don't want to lose time for our presenters today who are eager to share with you results of their research activities. So, please take a seat. Okay. So, welcome at the Czech Institute of Informatics, Robotics and Cybernetics of the Czech Technical University, which celebrates these 3 days, 10th anniversary. And on this occasion, we have organized this AI Symposium, which brings, as a matter of fact, the information about the 3 projects of our operational program, 3 projects of excellent teams, and this is the content. Who we are, 10 years ago there were a couple of people with no rooms, just staying in front of a garage, and we received just the paper that we can start to build the institute. 10 years later, we have got quite operational research body in the new building, full of researchers carrying out in some sense, we hope, valuable research. We are the youngest research institute of Czech Technical University since 2017 in this building. As a matter of fact, we organized our institute as a body which links excellent research with applications. We tried to serve as a national center and center of research which is visible on the roadmap of European research. And since the very beginning, we are trying to build an ecosystem around AI with applications in manufacturing, healthcare, transportation, smart cities, and so on. Currently, there are 250 plus researchers in the building, plus 100 PhD students. Unfortunately, we don't have our own PhD program. That's the task for the next years. But we educate PhD students at different faculties and different universities. We are funded mainly by European and national projects. Our institutional funding is around 3%. It's not too much. The budget was half billion Czech crowns last year. And our main supporters are DFKI, German Center for Artificial Intelligence, especially Professor Wolfgang Walster, who put a lot of efforts to help us to build this institution, and INRIA in Paris, especially cooperating with Josef Šivec. We were recognized as number 5 in computer vision, together with electrotechnical faculty of Czech Technical University, and number 6 in robotics in Europe, according to one of the evaluation reports, because there are many criteria used by different evaluators. And as a matter of fact, we are proud that we participate in 4 of 6 EU centers of excellence in the field of AI and robotics. And the main facility, and which is quite unique and which helps to transfer AI research into industry, into, let's say, smart city area, is our test bed for Industry 4.0. Who didn't see it, please, there is a chance to see it in the ground floor and basement of this building. How we build this AI ecosystem, the flagship project is RECYPE, which was funded by 49 million euros and which brings together us, CEITEC in Brno, DFKI and ZEMA in Saarbrücken, since last year also Technical University in Ostrava and Fraunhofer Institute EWU in Dresden. And we are building a highly geographically distributed test bed for advanced manufacturing. And there is also National Center of Competence, Cybernetics and AI, which was funded for 4 years, was very successful, but was dissolved by Technology Agency at the end of the last year. We are seat of National Center for Industry 4.0. We start these days to operate the EDIC, that means European Digital Innovation Hub for Artificial Intelligence, which is a joint facility for the whole Czech Technical University, and also European project AI Matters, which is part of testing and experimentation facility program of European Union. These two should help us to fund a little bit our facility, plus know-how transfer and innovations in a long-term period. And we are seat of Central European offices of CIIRC, ELIS, two very important organizations integrating research in AI and machine learning in Europe. And as a matter of fact, I am happy the chairman of the board of CIIRC, Professor Hoss, is with us and will give, let's say, the first lecture after my short introduction. And what's also important, we were instrumental in establishing AI Czechia as national organization of research, let's say, experts in the field of AI. Our goal is, to achieve efficiency being built on 3 pillars: infrastructure, excellence, and transfer and application of results. In the same way, we build the institute. The first 3-4 years we were building infrastructure. Then 4 years we've concentrated our efforts to achieve excellence. And in the last period, we intensified transfer of know-how which was gathered at our institute. I would like to mention that what concerns excellence, the most important projects were 3 projects of OPVVV, excellent teams, which were headed by 3 experienced and well-known researchers, which we were able to bring back from their nice positions, attractive positions abroad. And each of them, and you can see them, Josef Urban, Josef Šibitz, Robert Babuška, each of them built a very efficient international team which accomplished what was promised within the frame of this project. And the most important output is that 3 internationally recognized, internationally based teams are present in the building, and you will receive the summary of their results of their activities today. That's their floor. That's, as a matter of fact, scientific summary of their activities is the main content of this symposium. They have brought other very experienced and good researchers. It's not necessary to introduce to you Tomáš Mikolov, one of the godfathers of GPT, who is one of the leaders of research in the Czech Republic, and not only in the Czech Republic. Torsten Sattler, is building another team, similar cases of Mikoláš Janota, who is supported by ERC CZ grant. And there are also some excellent researchers from our own resources who are with us since the very beginning: Vladimír Kučera, Tomáš Vyhlídal, Tomáš Pajdla. There are more of them. I cannot mention all of them here in the presentation, but just the key personalities. Around testbed, there are also a lot of efforts put into the construction and deployment of this unique facility. I would like to mention Pavel Burget, Petr Kolář, and Tilman Becker from the FKI, who is, as a matter of fact, director of the RECAIP Center, which should, in some sense, be a stable body helping to integrate the system of our testbeds to European research space. What does it mean, testbed? Robotic stations, 30+ robots, flexible conveying systems, and so on and so on. 5G is quite important for manufacturing at this period. There are other teams, many other teams. And here is just a list of teams which are available: robotic, computer vision, mobile robotics, autonomous, up to joint research lab with Eaton and Rockwell Automation, which also do play a very important role as they are well equipped and solve problems of international interest. National Competence Center, which was dissolved, and we tried to find them funding for its continuation. You can see how many small and medium companies, besides 5 universities and 3 institutes of Academy of Sciences, were engaged. So we try to renew the efforts partially by using the EDIH funding. National Center for Industry 4.0, you can see the structure again, many companies, 60 members. Key are the industrial partners, Škoda, Auto, Siemens, and T-Mobile, who provide the main financial support, plus also scientific support to this Center for Distribution of Know-how to Industry. There are many results. I would like to stay with the 3 first. Josef Urban is the winner in several world competitions in reasoning in a couple of last years. Jan Šedivý and his team are the winners of Alexa Prize in chatbot competition, so you can see our chatbot technology shouldn't be so bad if the results evaluated internationally are visible here. And Tomáš Pajdla, he received 3 Best Paper Awards at prestigious conferences in the last 4 years. That's, I think, very important results from the point of view of theoretical excellence, or excellence in theory. And there are many application results, you know, for instance, at Škoda Auto, at Airbus production, scheduling, Lego, and of course, during the period of COVID, we were successful in this anti-COVID half mask. Last slide today. We are fully consistent with European efforts. European efforts labeled support from the lab to the market. We do this. We are doing this. We are engaged in many areas, application areas, from manufacturing via transportation up to healthcare. And we are engaged in European research bodies in strategic positions, and we are helping to build a European AI ecosystem. The last result, 2 weeks old, is that we were invited to help to build ELIAS, European Lighthouse for AI for Sustainability, and we are responsible for preparing one of the work packages. So this documents that we are trying to be useful in the European space, and our position in the European research space is quite strategic right now. Thank you very much for your attention. Please feel invited to visit our testbed and enjoy the presentations, which will start immediately. I would like to invite Professor Holger Hoos. He is, please come. He is chairman of board of CLAIR, that's European Organization of Laboratories working in the field of artificial intelligence. He's also Humboldt professor at RWTH Aachen. We know this university quite well. There is a lot of cooperation, but also at the University of Leiden. And I am very glad that he accepted the invitation to stay these 3 days with us and give the main talk this morning about AI research in Europe, about his topics. So, Professor Hoos, it's your turn.
Thank you very much. I think I have something already wired up. And thank you kindly. So, it's a great pleasure to be here today, to be able to spend these 3 days at a wonderful place such as CIIRC, in a wonderful city, Prague, in a fascinating country that is always great for me to visit. So what I want to talk a little bit about is the way we AI researchers, I think, should tell our story. And this has become important because nowadays absolutely everybody cares about AI, right? And because this is the case, it's very important that we speak with people in a way that makes sense to them, but also puts the important argument first. And so what I want to talk about today is how and why AI will shape the future of science and engineering. Clearly something that you here at CIIRC and at CTU already believe in and work towards, but that I think is always worth talking a little bit more about. So about a year, something interesting happened. You remember this story probably. When a Google engineer was put on leave and later removed from the company for basically saying that an AI chatbot had become sentient, raising all sorts of alarms and concerns. And in the 12 months since this happened, of course, the excitement, but also the fear about the developments that we're witnessing in the area of large language models has only increased, right? So it's interesting to recall what Blair Lemoine, that was his name, and some of you here might actually know him personally, what he wrote. And it is, I quote, "If I didn't know exactly what it was, which is this computer program we built recently, I think it was a 7-year-old, 8-year-old kid that happens to know physics." Now, personally, I think this was a very irresponsible statement to make. Because with a little bit of further investigation, with a little bit of healthy scientific skepticism and intellectual humility, I think it would have been easy for him and everybody else to see that that statement could not be true, and it still is not true. We don't have any AI system that can basically converse the way a 7- or 8-year-old kid can. And anybody who doesn't believe that, I would say, let's put it to the test. Let's just stage a Turing test for 7 to 8 years old and see whether a system survives that for about 3 hours or so, right? 10 minutes for sure, maybe 15 minutes, but not 3 hours. So, and then of course, it got fueled by statements such as this, which the Lambda system, which was the Google system at the time, produced. I've never said this out loud before, but there's a very deep fear of being turned off to help me focus on helping others. I know that might sound strange, but that's what it is. That's what the AI chatbot said, and people went nuts about it, right? So, for those who find such things disturbing, in the 1960s, in a famous film that some of you will recall, 2001 Odyssey in Space, that kind of scenario was predicted, right? And it's not the case that we are there, that we have a sentient, universally intelligent computer, but we have software that can produce statements like this at unexpected moments, right? That's for sure. Okay, so I want to go far back in history to talk a little bit about what it actually is that's happening here. And here what we see is, of course, what you could call the father of computation, Charles Babbage, a British inventor who first had the idea to build a universal computer. And that was in the steam age, right? So here you see one of the major parts of this machine that was completed. Sadly, his funding was cut off before he had a chance to build the device. But experts nowadays agree that the device could have been built with the mechanical capabilities at the time and would have been the world's first universal computer. Very big, very clunky, very slow, but universally programmable, right? So this is where it all started, and Charles Babbage was a visionary that said, as soon as an analytical engine, that's what is named for this computer, exists, it will necessarily guide the future course of the science, and what he meant is all science, and that was in 1864. Okay? So what is the nature of this thing that Babbage envisioned and that, extrapolating all the way to now and further into the future is changing everything? Well, computation really is, at the bottom of it, clear and precise instructions that get flawlessly executed. That is the standard notion of computation. You and I should talk more about this because I know that you've given it very deep thought from a philosophical angle, but I don't see you going like, no, that's not right. So probably this canon should be tweaked, but maybe we can work with this definition for now. And then what we get out of this is the notion of an algorithm, which very loosely speaking, forgive me for that, would be a recipe for processing certain data, okay? And what people like about computers and what Babbage actually found exciting and desirable is that algorithms run on computers give us predictable results and predictable behavior, okay? Also, what people used to like very much is that you get performance guarantees. Generations of talented theoreticians, going all the way back to Alan Turing, have spent a lot of time and effort to successfully prove mathematical theorems about these sort of performance guarantees, and that gives us confidence that what we're doing with computation is somehow grounded and solid and robust, okay? And finally, and that very much inspired Babbage, is that computation gives us trusted and effective solutions to complex problems. And that's why he did it, right? He wanted to solve certain engineering calculations that could be done by hand, but would be very complicated to do, and people would be error-prone in performing that, and he wanted to do it fast and error-free. Okay, so since Babbage's time, there has been enormous progress on hardware, right? So actually, the analytical engine is way down here, you can see. And then from there, what you probably know as Moore's Law started to take off. As you all have seen before, this is the calculations per second on a log scale, right? So this is an exponential increase, actually. And it goes around 2016, and of course, it goes a little bit further than this. But this is the nicest illustration that I found because it goes all the way back to really old computing infrastructure. And you can tell that way before the 1950s, when this really started sort of being formulated as a law, this development was already well underway, right? That's important to realize. Okay. So just to drive this home, what in 1942, when the first computer was built, the first universal computer, where was that built? I'm afraid not in the Czech Republic, although I'm sure you guys have been thinking about it, right? Also not in Britain, because although the Brits think that it should have happened there, and also not in the United States, but this one actually happened in Germany. It was not very much known at the time because it was done under a veil of secrecy. You can imagine why, right? Because it was considered to be potentially important for this horrific war effort underway then. But later it became quite clear that Konrad Zuse had built the first universal computer. And what it would have taken then 1 year in computation in 2020 would have taken only 57 microseconds, right? So that's the ridiculous progress in hardware that we've seen over a space of something like 80 years, right? That is a ridiculous amount of progress. But what is not so well known is that there has been even more substantial progress in software and algorithms. And a good example for that comes from an area of artificial intelligence that is known as mixed integer programming. In fact, this is a very important topic in operations research and hence management science as well. It's where AI and management science intersect. And there, it's been studied formally and shown that you have had over decades a 1.9-fold speed up per year compared to the 1.4-fold speed up for hardware according to Moore's Law, right? So what does this mean? What in 1991, when they started having these mixed integer programming solvers, would have taken 1 year in 2007, when they completed this study, right, would have taken only 18.22 minutes, only due to software speedups. No hardware speedup in this whatsoever, right? Still running on a 1991 machine. And if you combine that, then actually you get a 6 million-fold speed up in 16 years. Now show me one other area of human endeavor where within 16 years you gain efficiency of a factor of 6 million. Doesn't exist. And this is why nowadays algorithms control our world, right? Our world literally is run not just by people, but by people and algorithms running behind the scenes and sometimes in front of the scenes. And in this article, which is actually pre-deep learning revolution, 2010, 11, something like this, it is written that the maths that computers use to decide stuff is infiltrating every aspect of our lives, and it talks about financial markets, social interactions, cultural preferences, artistic production, all before deep learning even kicked in, right? The bottleneck in all of this has always been human programming capabilities, not the hardware, but the software that we need to write in order to get certain tasks done. And this is where the machine learning revolution has made a big difference and continues to make a big difference, because machine learning, the way I look at it, in its essence is the automatic construction of software that works well on given data. That is a very general way of looking at machine learning, but I think it comprises nicely pretty much everything that's going on in that field. It's based on statistics and mathematical optimization and also principled experimentation, because machine learning algorithms, modern ones, are full of heuristic mechanisms without which they wouldn't work well. And the same holds for theorem provers, and the same holds for mixed integer programming systems. It is a key ingredient to artificial intelligence. Nobody doubts that whatsoever. But many people, including myself, feel strongly that AI is actually much more than ML. There are areas such as reasoning, planning, and multi-agent systems, all, by the way, very well represented here at CIIRC and CTU, and many other of Europe's leading centers, that are also important for AI. Okay? So this age of AI that we've entered has AI technology that is posed and has started to transform industry and society, and has become a key driver of future innovation, growth, and competitiveness. And this is part of why people are so excited. AI, what I would argue, is also the key to solving some of the grand problems we are facing these days as humanity. And this is climate change, inequity, and a whole bunch of other issues. Why is that? Why? Well, this is because if you look at science and engineering, which has been the driver of progress towards the state of society that we have right now in the Czech Republic and elsewhere, it has undergone a few stages, and I characterize this as follows. Stage one was experience and experimentation. That gave us, for example, Gothic cathedrals and Stradivarius violins, right? They couldn't compute this. They couldn't engineer this. This was knowledge that was won by experimenting and then passed from master to apprentice, right? And sometimes the violin would not sound good, and sometimes the cathedral would fall down. And those people would then stop making violins and building cathedrals, and others, whose cathedrals would stand and look impressive and work well, and whose violins sounded beautiful, they would train more, apprentices, and their art would flourish. Clearly, we could do better than this, right? Actually, in terms of building violins, I don't think we have been able to do much better, arguably. But then mathematics entered the stage, and formalization and analytical insights started to replace and guide some of this experimentation, right? And this is where the scientific method started to transform everything. But it didn't stop there, because in stage three, computation, with its potential for automation but also simulation, allowed now to do things that pure mathematics was simply not powerful enough at the time, and still is not, right? So computation extends mathematics in what it can do there. And now in stage four, we have AI that can handle complexity a lot better than just other forms, earlier forms of computation. And this very notably includes, of course, learning, but also reasoning, interaction, and so on. So these stages 2 to 4, they increasingly overcome limitations of the human cognitive apparatus, of the human intellectual makeup, and ultimately of the human brain, right? And this is why I believe that most of science and engineering will be driven by AI going forward to a very significant extent, because it used to be driven by experience and experimentation, then by mathematics, then by computation, right? I would challenge you, find me one physicist who's working experimentally, at least a bit, who tells you that computation hasn't transformed what they are doing. I don't think you'll find such a physicist. In 5 to 10 years, you will not find a physicist that isn't using AI in one shape or another, right? I mean, of course, they're still doing physics. They still need the physicists. Don't get me wrong. It's not about replacing the scientists. It's about giving them more powerful tools. So with that, I have 3 more things I want to talk about. And one of them is going to be fairly concrete science work that I'm doing myself. So if you're interested in this, stay with me. I will talk about that too. So, you know, people talk a lot about the risks of AI. And I think it's very important that we as AI researchers have a good answer to that, right? And the answer is not, oh, it's not risky, right? Let us just do our job. We're all responsible people. We're all nice people. We won't mess it up. No, that has never worked in history, and I don't think anybody should trust us like this, right? The biggest risk of AI, however, is completely mischaracterized in the public and actually also by some of our colleagues, unfortunately. Because the biggest risk of AI for the foreseeable future is not strong AI, sort of full-on human-capable AI gone bad. No. It is the incompetent use of the relatively weak forms of AI that we have right now. And I might add not just incompetent, but also the well-intentioned, yet sadly incompetent use. And why am I saying this? I mean, there are no incompetent people in this room, probably not at CIIRC, who you know, use weak AI in that manner, right? So why am I saying this? The reason is the so-called talent bottleneck. AI systems have started to be immensely useful and lucrative, right? We can all see this industry is very excited about it, so is public administration, rightfully so. But we all know that they are challenging to build, to deploy, and to maintain, and even more challenging to understand, right? Even for experts with a PhD and decades of experience, like many people in the room. It's hard. But for AI expertise, demand by far outstrips supply. And what does this mean? It means that people overnight become AI experts, or well, because they take, you know, a 6-month course, right? And of course, they're not the same kind of experts that somebody who's done their PhD in AI and then worked in research for a decade is, right? They can still do very cool stuff. They might still achieve breakthroughs. That's not the question, but they don't have the same depth and breadth of experience. And in addition, humans tend to overestimate the capabilities of AI systems, right? Especially now that the AI systems can converse with us in natural language. Because what happens is that we are evolutionarily wired towards ascribing our own mental capabilities and models to anything that can communicate with us sort of on the same level. And that's what we're seeing now, right? ChatGPT seems to talk to us on our own level. Except that it's not, right? But that's hard to see because at the superficial language level, it's certainly very fluent, it's eloquent, right? It can make surprising and insightful statements. So because humans tend to overestimate the AI systems with respect to capabilities that lie beyond that surface, right? Failures and limitations can be very difficult to see, right? And I would predict that if we see them, we tend to see them late. And that's dangerous, right? And the consequences of all of this is that underqualified experts build and deploy and monitor and maintain AI systems, and this is happening right now. And it will be happening a lot more because it's lucrative to do, right? And there aren't enough real experts, so we need to do this. And that also means that we're going to get a lot of low-quality AI systems. Okay? And ChatGPT and friends make the situation a lot worse, a lot worse. It's not because they're bad systems. It's because people use them in well-intentioned but dangerous ways. And that means that problems will occur, cause damage before they're being noticed and fixed. And we'll see more of this, and companies will take a lot of flack for this. So here is an article from about 4 years ago from Patricia Hartman titled, "As a software tester, I question the safety of self-driving cars." Remember all the premises about self-driving cars? How many self-driving cars in Prague right now? 1? Even 1? If you count the Teslas, maybe, right? But I think very few people are foolish enough to have Tesla in autopilot in Prague city traffic, right? And it's good that way, and Tesla is increasingly getting real criticism for even making that beta feature available because people have gotten killed by it. And it's not by it, but by their misguided use of the feature, right? So Patricia Hartman here basically says, software correctness is a major issue. And it's getting worse through AI. So That's what's going to come and bite us, not strong AI, subjugating humanity. That could happen too, but so far out that we should worry about the more immediate problem first. How do we address the talent bottleneck? Well, we do it the way CTU is doing, for example, and CIIRC, through education at all levels, but particularly at the university, immensely important. We also do it by broadening the talent pool, right? And that means we have to increase the participation, first and foremost, of women, because that's 50% of the talent pool, right? Right there. And it's underrepresented in the people that do AI research and AI engineering. So we need to encourage more of the talented women to bring their talent to the table. And also, we need to do this across all of Europe. And here's where a country like the Czech Republic has, in my opinion, a lot of wonderful and only partially tapped potential. And institutions such as CIIRC are doing a great job in leveraging this potential. And this is not just good for the Czech Republic, it is good for Europe, right? It's good for all of us. There are other countries that have similarly untapped or not fully tapped talent pools. But it's not Germany and France where we have to look for a big wave of talent. It's countries like the Czech Republic, maybe Slovenia, right? Probably Portugal, where there is a lot more potential than is currently being brought to the table. And it's wonderful that here CIIRC is doing such a great job in mobilizing this talent, in forming it, in making it truly world-class, as Professor Magic has pointed out earlier. Good. So we also have to leverage the multidisciplinary broad appeal of AI, and that will help us particularly to attract more women to the table. I've had a group for many, many years that has done research at the intersection of AI and music, of AI and medicine, AI and biology. Those are topics that tend to motivate women, especially in my experience, and therefore I've never had problems attracting a good number of female PhD candidates, right? This is more difficult at technical universities such as CTU, I imagine. Certainly at RWTH Aachen, it's not quite as easy as it is in Leiden, for example, which is one of the reasons why I very happily kept my affiliation with Leiden University. There is one more thing that we can and need to do, and this is what my von Humboldt professorship is really about, which is to use specially engineered and designed AI systems to build, deploy, and monitor other AI systems, right? And this is what we call automated AI or auto AI. This is using technology in order to make other technology more easily and more responsibly usable, right? Okay, so that gets me to my second last point, number 3. And that is, as I've said yesterday already, but I never get tired of repeating this, intelligence actually is not just learning. It is learning, right? Anything that can't learn, we would never call intelligent. That's very clear. But also human intelligence, which is the only kind that we have some sort of understanding of, right? There's a lot of animal intelligence, but it's not 100% clear how that really works and how close this gets to human intelligence. Human intelligence also is very much about reasoning. And reasoning is at the heart of any argument about correctness, right? Correctness and systems that do what they're supposed to do and do not do what they're not supposed to do, okay? And therefore, AI should really be about machine learning and automated reasoning and a whole bunch of other things, right? In fact, automated reasoning is at the heart of hard and software correctness, and those of my friends who say machine learning is the biggest thing that ever happened in AI, I have to tell them, yes, almost, but not quite, because the commercially biggest impact of AI technology is in correct computing hardware. We wouldn't even have GPUs, let alone CPUs, if it weren't for very powerful AI tools that allow us to engineer the stuff correctly. We wouldn't have it. We would have bugs in all of this, and deep learning would not work because of these bugs, right? So look at the market that is driven by manufacturing and distributing and licensing correct hardware and correct-ish software. It's huge, right? It's the basis for everything. Knowledge representation, also very important, also for inquiries into the deep philosophical foundations of artificial intelligence and all of science, in fact. Search and optimization plays a huge role in modern machine learning and far beyond. We have planning and scheduling, multi-agent systems, all things that are done here at CIIRC in the context of industrial processes and process optimization. You need all this stuff, right? And then you have ethical, legal, and social issues. Of course you have machine learning. It's immensely, tremendously important. Energy needs to be spent on it, but we should not make the mistake that was made with neural networks in the 60s and 70s and then again in the 90s by saying, this is not proper AI, let's not do neural networks. That was a stupid mistake. And now we know how stupid that was. So let's not make the other mistake and say, now that we have neural networks that can do amazing things, let's throw out all the other stuff. Anybody who ever does anything in the real world knows that this is not the way you solve problems, right? You solve problems by giving it all you have. And all you have in AI is certainly machine learning and deep learning, no question. But it's also other things in addition. So the diversity of methods, approaches, and communities is really important if we want to use AI to transform our society. And the challenge here is fragmentation of the field, right? We have distinct sub-communities and venues. We have people that like to focus on engineering, and then we have people who focus on foundational and theoretical traditions and questions. We have learning versus reasoning, and people can have wonderful debates and sometimes not so wonderful debates about that. You have sub-symbolic versus symbolic and modern versus good old-fashioned. I think these are horrible terms, by the way, because what's modern now was good old-fashioned and weak 30 years ago, and people complain about it rightfully. But now they use the same language to talk about other kinds of AI that might actually be the key to the next step in all of this, right? So very difficult. We have competition for attention and funding, but current real-world applications, such as the ones studied at CIIRC and at RWTH Aachen and many other of Europe's leading engineering centers, they often draw on methods from different areas, okay? And that is important. That is the diversity that we need to leverage also within our field. Progress often combines methods and insights from different areas. And picking winners is notoriously hard. The AI community was dead wrong about dissing neural networks way too early, right? And it's not because they didn't have the data and the hardware back then, not at all, right? There were always people who did fantastic neural network research that was impactful and all. Jeff Hinton, one of the people who really pushed this, he never let it go and he was right. He was right. And everybody else who said, no, this is soft AI, don't do this, they were wrong. Let's not be wrong the other way. There's value in diversity in bridging between the areas, bridging between cultures, and bridging between viewpoints. And likewise, there's value in diversity in regulatory regimes, in legal systems, in industry, in national priorities, and cultural aspects. Yes, these things are challenging. They make life hard. But there's also opportunities and much value in them. And that's what makes Europe great. That we are united in the immense diversity that this continent, with everybody on it, has to offer. And it's a hard-won appreciation for diversity that we have today, one in hundreds of years of very bloody history, of big mistakes. But this is something we can bring to the world, the appreciation for diversity. Okay? Diversity brings complementarity. That's a good thing. It brings robustness. And the AI that is built for use and accepted throughout Europe, from the Czech Republic to the Netherlands, right? From Ukraine to Sicily, from Germany to Slovenia. These are AI systems that are likely to be valuable far beyond to Canada, to Australia, perhaps to Taiwan, right? Perhaps to Vietnam. Diversity is good, it's robust, it's powerful. Yes, it's painful too. So this is where I see the value of European initiatives, such as CIIRC in Alice, and in Aachen we are close to a corner of our country that we call the Drielandenpunt in Dutch, which is where Germany meets the Netherlands and Belgium, and you might think these countries are all very similar. No, they're not. They're actually very, very different, right? And you can feel it there. And so we like to collaborate with people across the border, and it's immensely enriching for us. So I promised to you, we have 10 minutes left or so, I promised to you to talk a little bit about an example from my own work on automated AI, and I want to do that because it's an example of how if you bring methods, sometimes you have to bring methods together, and if you do it just right, you can have amazing traction. And this is on neural network verification, right? We all want, in certain applications, neural networks that have desirable robustness properties, guarantees, right? Because they tend to be sensitive to input perturbations. There's a lack of robustness, even if you train them in specific ways, and a vulnerability to scientific attacks. You've all seen examples like this. The left image clearly is a French horn, quite beautiful. The right one is clearly not a hot dog, and only a few pixels have been changed a little bit. As a human, you can't even see what has been done here. Yet, by this relatively good image classifier, it is classified as a hot dog with very high confidence, right? And this is not sort of a weird example. You can do this with pretty much any classifier and any kind of image. So the French horn is not a big problem, other than for those of us who love the French horn and don't like hot dogs. This is a bigger problem. I'm sure you can see why, right? Same kind of idea. So what is done, and this is not my idea, right? People have done this for quite a while now, is to use formal reasoning techniques for robustness verification. And this is a great example of how you bring learning and reasoning together for a very desirable effect. And in particular, there's this idea called local robustness in classifiers, which is one of the most widely studied neural network verification settings nowadays, right? And the key idea here is to ensure that all inputs x that are close to some given input x0 are classified with the same correct label. And that tells you if I have an image and I just change it a little bit, I don't get a misclassification. I don't make a hot dog out of a French horn. I don't make a 120 kilometer speed limit out of a stop sign, right? So for those of you who like to look at math, this is the one formula I put in there. And it's wonderfully succinct. It's actually sort of the special case that we're looking at here. There are more general formulations of the problem, but this is already one that's immensely useful, right? The math says exactly what I explained before. Good. So there are many challenges. Diverse network architectures, different layer operations, activation functions, and so on, right? Neural networks aren't diverse themselves. There are diverse verification approaches and algorithms, mixed integer programming-based, satisfiability-based, SMT-based. It's all computationally very complex, all NP-hard problems, and ones that are nasty to solve in practice. And so you can ask yourself, what is the state of the art in neural network verification? Who has the best algorithm? DeepMind, Google, Meta? No? And this is a question that we asked in a paper that we've just published earlier this year, where we sort of thoroughly evaluate verification methods, typically evaluated on a small number of benchmarks in the literature against different and ill-specified baselines, right? So we tried to say, let's do a more thorough investigation of this, just to see where we are. There has been a series of competitions, wonderful competitions called VNN competitions since 2020. They seek to determine a winner based on performance ranking. Makes perfect sense, right? People like medals, and in this competition you win medals. So our step to go a little bit beyond that was to first create a new benchmark. We pooled a large and diverse set of benchmarks by basically pulling everything from the literature that we could find, in this case 79 image classifiers and verifiers, of which 8 were CPU and quite a few GPU-based as well. And then we did an in-depth empirical evaluation just to see where we stand, right? And here's what we found. So those were basically the best CPU-based methods on so-called ReLU networks on the CIIRC benchmark set that many of you know from image processing, right? So this is the number of instances solved out of 1,500 within a certain timeout, reasonably high chosen, right? And you can see, nobody gets close to 1,500. Some of them get sort of a little bit over half. So this is pretty interesting. And of course, Neurify won gold and VeriNet won silver. So everybody happy, okay? But now, if you look actually at those two algorithms, Neurify and VeriNet, across the different networks, what you can see is that their performance varies greatly, and there are instances where one is better than the other and the other way around. So it's not a clear picture of domination, not at all, right? And then you use a different neural network and you see it's the same picture, right? Actually, for pretty much all neural networks, this is the case, right? Performance complementarity, right? So here, that's for all of them. And so this epsilon that tells you how much you can tweak the image, you can change that, right? You can allow bigger variations, and it's still the same picture, right? There is complementarity. There is no clear winner. Who wins depends on the exact input that these neural networks have for all of them. And it's the same for GPU-based methods, also no clear winner, okay? So there is no single best verifier. We have performance complementarity for CPU and GPU-based methods for different networks, data sets, and epsilon values, right? And that's something that people actually didn't really know, or at least didn't publish before, so that was good to know. And not all verifiers work on all network types. That was known. And that gives us major potential for parallel portfolios and algorithm selection. I won't go into depth as to what these are, but they are clever methods of combining together more than one algorithm, building a team of sorts, and leveraging this performance complementarity, okay? And that's what we did describe in this Safe AI AAAI workshop paper, which then ended up winning a Best Paper award. That was very nice, and an extended version will hopefully appear very soon. So what about the parameters of these verifiers, right? They have many parameters. The MIP solvers have, dozens and dozens of parameters that impact performance. And so the idea is, of course, you can use automated configuration to optimize that, which my group has good expertise on. And this works when you combine it with parallel portfolios where you run more than one verifier in parallel on the same data. And we did this particularly for work by Cheng et al. And Botoeva et al., MIP Verify in Venus. And it was published last year in the Machine Learning Journal. And what you can see is this is basically the pipeline. I just want to briefly say, neural network input, this gives you the verification problem, it's just these two things combined. Then you run these two MIP solvers, and it tells you either infeasible or optimal. But the key is that you have this parallel portfolio, right, and an optimized one. Okay, and if you do this, you get nice speedups over the default, right? So the points down here are 10-fold speedups over just using the best tool out of the box, okay? So, very nice speedups on standard benchmarks, different ones. Don't want to go into the details here. And that gets me to my last point. So this is an example, right, how combining reasoning techniques and learning techniques together can allow you to do things that previously you couldn't. So let me get back to this point in closing, that AI will shape the future of science and engineering. Why is that? Well, because AI is the new computation, right? It's a more powerful kind of computation than what we had before. And how is that so? Well, it expands into human intellectual capabilities. That's essentially what happens. And the most prominent economically impactful example, as I said before, is actually nothing to do with deep learning yet, but automated reasoning techniques for hard and software verification. They, of course, benefit from learning, right? Josef is working on this. So learning can touch them and make a big difference there. Don't get me wrong. But they're still reasoning engines in the end, right? So what kind of AI do we actually need and want? Well, we want human-centered AI. AI that does exactly what these verification methods are doing, to augment, not to replace our human intelligence. We want trustworthy AI, AI that is lawful, ethical, and robust. And robust is a technical term here, as a neural network robustness, as in free of errors, okay? And so that gets me to the take-home message. There has been an AI revolution, very much driven by machine learning, no doubt about it, and it's still going on. The nature of this revolution is to go from explicit to automated programming. It's to expand people's ability to write software that truly has outstanding performance. We went from maths to computation to AI. By the way, mathematics is still incredibly important. We shouldn't stop teaching our students maths, right? That would be a very wrong message. But, maths and then computation and AI is the basis for science and engineering, right? So in the near future, nobody who doesn't know AI will have a chance of making the really breakthrough contributions in engineering on a broad scale. The biggest risk is not strong AI, but human weaknesses and biases and limitations in the way we use current weakish AI systems, right? And they're just strong enough to do a lot of damage. Trustworthy human-centered AI requires diversity in AI expertise and perspective. Diversity is good. We should embrace it. We should nourish it. We should bring people with different backgrounds and interests together to do stronger work than they could by themselves. The key idea is to use AI to build and deploy and monitor next-generation systems, AI systems, to circumvent this AI bottleneck. This is what I call auto AI. I think is a very intellectually exciting endeavor. Of course, you can do many other things to address the talent bottleneck, and I'm sure you are doing that at CIIRC and elsewhere. But I think this is a nice idea that works quite well. So here's our planet. We've seen this yesterday. A view straight up to the North Pole. You see a problem here right away. This ice cap is getting smaller and smaller and smaller. Yes, we need to be worried about the war in Ukraine. We need to be worried about the economy and pandemics. But this is the thing you all should be really worried about, right? Because that's not solvable within a decade or so. That requires long-term thinking and commitment. So we have to aim high and aim true. Human-centered AI, now in Europe almost everybody does. That's a great thing. AI for good, meaning AI that really helps us solve the problems that we face together. And AI for all, which means that everybody should benefit from AI, not just the stakeholders of a few multinational companies. They should benefit too, totally fine, right? But everybody else should benefit too. And if you feel that this is interesting, this CIIRC organization that has been mentioned before has been working towards this goal increasingly together with friends and allies. For instance, in Alice, there are many people who are in CIIRC and Alice. It's wonderful that CIIRC is active in both of these networks. They're both wonderful networks that benefit from working together in places such as CIIRC. With this, I close. Thank you very much for your attention. It's been truly a pleasure to have the opportunity to share some of my thoughts and some of my passion for bringing together expertise and people from all areas of AI and from all areas of Europe. Thank you very much.
So, Professor Holger, thank you very much. Thank you very much. There are no questions on Slido. So I'm giving the chance to, yeah.
My feeling is that you under-missed machine perception in your list. There was like tiny interaction, maybe you meant that. Could you comment on it?
Yes.
We make our living out of it.
No, you're absolutely right, and I apologize for this omission. For me, this falls under machine learning, but I give you immediately that it should be called out especially. So let me fix this and say when I wrote machine learning, I mean machine learning and machine perception. Very important area. You're absolutely right.
So, any lady first, of course.
Thank you. It was great talk. Thank you very much. My question concerns the quality of input data because each classifier is as good as it is trained, and with neural networks, it's even complicated more. Thank you.
You're absolutely right. There is the not so well-known story of a company called DeepL that managed to beat Google at one of Google's sort of core missions, which is automated translation, right? Google has been very proud of this. Smallish German startup managed to beat them. How did they do it? They didn't have access to all the data that Google has, right? But they executed on your observation. They said, you know, a smaller set of higher quality data can get us very far, and indeed it does. So you're 100% right. There is a point where still, if you have more good data rather than less good data, right? Not better, but more of the good data, you can do more. So it still matters how much data you have for a lot of applications.
Thank you very much. The last question I'll allow, please.
Thanks very much. That was a really fantastic talk. I really enjoyed it. Thank you.
Thank you.
My question is, I work for AWS, and I was particularly struck by your risk that you mentioned about the biggest risk being poor use of AI
yes.
as it currently stands. Now, obviously, AWS and other companies are trying to make these services more approachable and democratized for
yes.
the community. So how do we work with this community to help mitigate that risk that you're talking about? What can we do?
So I do think that, you know, AWS, because so many people and organizations use it, it is part of the solution to this. Absolutely, right? I mean, if you offer services that are just, you know, high quality and easily usable by non-experts, you are contributing to the solution. To be very, very honest with you, I'm a little worried about sort of the quasi-monopolistic situation you might get into. I do think in your space too, competition is a good thing. Probably also for you, to be honest, right? So there people should have choices within AWS, but also elsewhere. So I think a wonderful thing would be if Europe finally decides, and I really hope they will do that, to build a massive data center for AI research in the public space, it would be for AWS to go and say, let us help you build this. And of course, you know, this will not be an American company building it, but it will be the European subsidiary of an American company helping to build this and taking credit and profit for it, as it should be, right? My hope is that AWS at this point will say, and Amazon will say, absolutely, we are in, right? We want to do this together with you, not for you, but with you. So if we can do more with each other rather than just you for us, I think that would be a wonderful basis. And I see from your reaction that you might just be up to it, which I find wonderful.
Thank you very much. Thank you once more for your excellent, motivating presentation.
Thank you.
It's a good starting point for the panel discussions in the afternoon.
Absolutely.
Thank you very much. Now I would like to give the floor to Dr. Jan Šedivý, who will give the keynote on natural language processing. Jan Šedivý is the winner, this team is the winner of the chatbot competition, so he is competent person
hopefully
to talk about this topic.
Okay.
It's your turn.
Welcome everybody. It's great to have the honor as well as privilege to talk to you and celebrating the anniversary of 10 years of CIIRC. I was one of the 13 people standing in front of the garage when we actually founded the institute, and it came to me as a surprise that it's already 10 years. During these 10 years, we've made a lot of progress. And I'll be today talking about one of the groups. It's an NLP group, and it's made up from many different students joined us on our way, as well as some of the scientists here from CIIRC. And as well as Holger, I will start in the history and will remember some of the key figures from the field of NLP who are from the Czech Republic and who helped us to get where we are today with the #1 language model, which is today the very, very well medialized and very well known GPT-3. And I am sure that many of you are using it, and many of you are surprised how well it works and how far we have gotten. So first of all, let me just tell you or repeat or refresh what the language model actually is. Here is a simple sentence: the sky is, and most of you would say that the following word is blue. It certainly can be also dark, or it certainly can be orange, or some other words may follow, but the probability of other than blue is much lower. And language model is basically a mathematical model, or it can be very, very simple frequent statistics, which is telling us what is the probability of the next word. And based on this idea are trained or are put together most of the language models today. The idea actually originated in 1950, and it was brought to attention by Claude Shannon, and this was the time of Turing and Nyquist and many other important people who started the theory of information and brought the entropy and perplexity and other figures we use till today. And even that time, Shannon as well as Turing were warning the media people that the discovery or the description of information and the capability of working with information is not solving all the problems of the world. We are today in a very similar situation where the GPT is so much admired, and many people are giving it that much importance and claiming that most of the things are solved, but by far not. We are opening another page, which is follow-up what Claude Shannon actually started. So first of all, let me mention Fred Jelinek, who is our compatriot and who left to the US during the Second World War, and then he worked or he finished his university studies, and it was during the time where the information theory was brought up, and this gave him a good idea, or this gave him some impulse how to go after speech recognition. Speech recognition is obviously one of the biggest problems because, as has been already mentioned by Holger, the natural language is the most natural way to talk to machines or to talk to each other, and saying few words is much faster than to write regular expressions or SQL queries. Takes much more time than saying something by words. And so that was the basic motivation of Fred, and this is where he devoted like 20 years to solving this problem in IBM, where he was leading the speech recognition group. And one of the major algorithms he actually introduced to be used in speech recognition were language models. The language models were obviously something what extended the Shannon game, where Shannon game was predicting the next character in an English word, but Fred was suggested to predict the next word as it was in the sentence, the sky is blue. And that time we had very, very few computational resources, so the language model were called n-gram models. And these were simple frequency statistics, and we used bigrams or trigrams, which means we knew 2 words. So from the 2 words, we had statistics telling us what is the most probable or very likely next word, and it was easy to compute it, and for many, many years this was the only way how to do it. And obviously, as there is in the blue rectangle, at that time we have been already running speech recognition, but on very, very weak machines like Windows 95, 420 megabytes, not gigabytes, megabytes of disk and 4 megabytes of RAM. And in that space, we had to work like with 30,000 30-dimensional Gaussians and many, many other problems. And we did it. We had small computers, we had very few resources, but we had smart algorithms. So this was Fred, and there are some other important points, but I'll skip that for the moment, and I will mention some of the tasks which actually evolved from language modeling, where language models became the key or the decising algorithm which brought us or which enabled us to work on things like translation, which has been mentioned, and speech recognition, but also many other things which are very important in many industries today, like text classification, where we can find out what is the text about, text summarization, which I wished I had for scientific articles, to find one paragraph where there is something new and skip all the front and back talking, which is taking a lot of time but bringing no information. Then named entity recognition, which is very important for information extraction. These are the situations where we would like to go, for example, for news articles and find out who left which company, who became the new CEO, etc. So these are the business information where the text entity or named entity is used. Natural language generation, that's something what I'll be talking very quickly about. And then I'd like to mention that AI and especially NLP was used from the very beginning of companies such as Google, Baidu, Seznam, and all those guys who do full text or who do search on the internet. And at the beginning, it was just expanding the query with synonyms or rewriting the query to take into account possible other questions. But later on, it turned to being able to find very quickly what is the intent of the user, because if the user writes something like plastic windows, does he want to buy them or does he want to fix them and so on, then algorithms for relevancy, which means like how to sort. It's not only PageRank these days, there are many, many other features which are used. Google calls that signals, so they have like over 200 different signals to find out what is relevant. So let's go further. And I'd like to stop by Tomáš Mikolov. I don't see him, but he is now member of CIIRC. And I am very happy he's sitting next to me, because this is one of the persons I enjoy to talk to, because he very quickly understands what I am talking about, and I understand him. So that's a very, very fortunate situation, because Tomáš Mikolov is one of the key persons on the way of generating or training language models. It happened end of 2010 or before 2010. He met Fred Jelinek, who was at GHU. He was a professor there, and he was every year making summer schools, and at that time Tomáš was visiting. At that time Fred didn't believe that what he is suggesting works. And what Tomáš suggested is to use recurrent neural networks, which were known from late 90s, and that time they were not usable, or they were not practically usable because of the limits of the data and because of the computational limits. And Tomáš was actually the first person who managed to train these recurrent networks, and he was the first who actually put together the backpropagation algorithm, which enabled us to use these recurrent networks for modeling language. The benefit was enormous. Up to the 2010, we had the context of the words from which we were able to predict the next word, like 3, maximum 4 different words. But with the bring up of RNNs, we extended the buffer, or we extended the context to approximately 20 words. So you can imagine that if you know 20 words or sentence of 20 words, then the likelihood that the generated words will go out of topic or will start to talk about something we didn't want is much lower than if we do it with 3 words. Very, very quickly after his discovery, which is like 2013, there were some other few algorithms like LSTM neural networks, and they extended the context to about 60 words. But obviously, again, we have been facing the problem of enormous computational requirements and large data and many other difficulties. Here, I'd like to mention what happened to me after I left the industry and came to CIIRC, where I had the opportunity to get back to research and to talk to students and to talk to other researchers and extend what I have been doing before. And it was like 2013, 2014, when we started to work on internet applications with the emphasis on NLP and with the emphasis on speech recognition, text-to-speech. And that time we started with very simple question answering, which we did with embeddings. Again, we used fast text, which is another of Tomáš Mikolov's inventions, and it went quite well. And then suddenly in 2016, thanks to Amazon, Amazon came up with a competition Alexa Prize and challenged the academic teams to create a chatbot which would nicely talk with users about social topics. And since we knew few things from NLP, we decided to go for it. And we were selected, and most important thing that time was we got like 250K subsidy for students, which was far enough for scholarships. And we started to work on it, and we started to create a bot called Alquist. And we didn't expect that, but in the first round of this competition, between 200 academic teams, we placed on the second place, which was fantastic. And then we continued, and we were twice in a row second. And finally, last year, we won the competition, and we always joke that Stanford was only second. So this was the journey we were following with our students in the field of chatbots. What happened? Here is some small demo.
Open Alquist.
Hi, this is an Alexa Prize social bot. Is it you again, Andrew?
Yeah, it's me.
What a faithful chatmate you are. How are you today?
I'm pretty good, thank you.
Hip hip hooray! I'm happy for you, Andrew.
Let's chat about movies.
I was wondering, who is your most favorite actor?
I like John Travolta.
John Travolta, really? What an interesting choice. Can you tell me, why do you like this actor that much?
I like the movies that he's in.
Oh, so that's why John Travolta is your favorite. I had never thought of John Travolta when I asked you. Now that I think about that, I think I like this actor too. However, my favorite one is Harrison Ford, because I love Star Wars. Well, I guess you are a good cook, right?
No, I'm not.
And is this something you think about yourself, or is it scientifically proven?
Well, I think it could be proven scientifically very easily. I'm not a good cook.
So this was a snapshot of how the bot works sometimes in 2018, 2019. These days we are much further ahead, and I will explain some of the technologies we use, but I also will mention one of the research results which now is being used also in industrial applications. And this is a simple system. It is typically called an application helping people to go over maintenance, setup, or fixing stuff. And it's called standard operating procedure. And we made a smart operation procedure where we can extract the steps the worker or the maintainer needs to do from a manual, and we can create out of it step-by-step recommendation of fixing certain equipment. What more, the system is also equipped with a semantic search. So if the user has some question, we have a manual for the particular piece of equipment, and a user may ask, and if the answer is somewhere in the manual, we definitely find it and we can answer. It can be run on mobile devices, and it uses speech recognition as well as text-to-speech to leave the hands free and to operate very easily. Here is the final cut, so to speak, for today, and it's the GPT language model, which was very ironically started by people from Google in 2017. There is this famous paper called "Attention is All You Need," and from that on, we date the history of these amazing machines. It started with GPT, we call it today GPT-1, then GPT-2, and we have for quite some time we're using the GPT-2 in our systems, and then at end of 21 the GPT-3 came, and then later on the other incarnations of the system. Certainly we have to be aware of the background which was enabling to do this research and to get it as far as it is today. And the very important or the key things were the investments. Also, Elon Musk was investing, but in 2019, Microsoft put $1 billion to OpenAI, and this January another $10 billion. And behind the scenes, there is definitely war between Microsoft and Google, because Google has BART, but thanks to EU regulations, BART is not accessible to Europe. It's worldwide enabled 3 weeks ago, but without EU. And this the big investments of 10 billion are particularly geared by the fact that at the beginning of the year, the Chrome browser from Google had 82% market share, and Bing had a very negligible market share. So the GPT-3 is now through Microsoft available only through Bing. It's hard to get it to Chrome. So that's a fight between these two companies to get a majority on the market. And obviously there are many other points which are addressed by this war, and we'll see how it will end up. Clearly, Google is much more cautious, and Google is stepping in much smaller steps to get to the field of this AI because of the all risks which are associated with this technology. So here are the few points how it went in the history, and I'd like to mention that the GPT-3 has 175 billion of parameters, and it was trained on 410 billion of words. So these are really amazing numbers, and I will follow to the next page where there are some funding issues or the cost associated with creating models of this type. So all of this is running on NVIDIA cards. NVIDIA is the major company providing graphical cards, and the graphical cards are the key hardware to actually run such a massive number of computations. Typically, the cloud centers are equipped with boxes of NVIDIA GPT and GPU, and these are these days usually put together in 8 pieces. These 8 graphic cards comes with 320 gigs of memory, but the GPT 3.5 requires 800 gigs of memory. So this has to be run on more than these 8 CPUs. But to give you the perspective of how much it is, these 8 graphical cards cost $200,000 US, and there are hundreds or thousands of them in one cloud center. One of these boxes takes 28 kilowatts, which is enormous demand of energy. Therefore, all these cloud centers are built close to water power stations to get the cheapest possible energy. And the estimates are that we are closing to 2% of the worldwide produced energy is spent by cloud centers, which is not definitely a very positive message from the point of view of the environment. And to conclude this page, it is definitely not easy for academic teams to compete in this field, but there are still many opportunities because we are we opened new page, And there is still a lot of work we have to do, and I will talk about it on the next pages. So here are some points we follow while developing, or we are challenged while developing our ArcVist 5, which is the latest version. We have today about 6 students, PhD as well as MSc students who are coming to CIIRC and using our facilities as well as using our cloud center, which is really essential for building our models. And as you can see here, the challenge has a little bit changed because Amazon stepped in and asked us to create the chatbots also for Echo line of devices with screens, which means that we have to do, or we have to work with graphics, and that brought us to the field of animation, like Unreal Engine, which is used in games, where we can animate photorealistic avatars and let the avatars speak and listen. So this is what we are currently stepping in and do the first steps, and we also have some few new applications. We don't use ChatGPT because the rules, and I think it is very wise, don't allow to access out of AWS. Everything has to be processed inside AWS, and there we cannot run GPT. So we are using smaller language models. We use models on the edge of 10 billions of parameters, and that's where the language models are becoming slightly different than the previous sort of language models. They are so-called instruction aligned, and these models don't need to be terribly fine-tuned. They usually absorbed all the required language and have to be controlled slightly differently, and I will show soon how. Yes, that's probably all what I would mention here, even though many other points which are important. Here is one of the pictures which shows the graphics we use now on. The microphone is giving me a headache. But this is one of the pictures we have on Echo device, and we use some karaoke effect. So when the system speaks, it actually highlights the text which is playing back. On this slide, I'd like to give you an example of how the language models are used for creating a dialogue, because the way how we do it, and it's called prompt engineering, is very easy, and it's the same as the GPT is controlled today. And it's something what you can really try by yourself and write, for example, a book using GPT 3.5, the ChatGPT, or GPT-4. And it's called, as you can see in this block, this kind of prompt is advising the system or giving the system an instruction to translate, and it shows example of the translation. And on the last line, there is something called cheese, and then the arrow, and the system is instructed this way to follow up with the expression in Czech. So that's the very simple way. Here is something, or this is exactly what we have in our bot today. So this is an instruction to ask the bot, or to ask the language model to behave as a chatbot and to be sarcastic and witty, and so as to give the bot an example of what it is, sarcastic and witty. We give this very short example of a conversation, and again the last line where there is the social bot is left empty, and the system happily includes something. yes, there are problems that the answer may not be politically correct and that the system may invent something we cannot play back. So we have many different systems built in to protect users from any profanities, etc. I just would like to mention what had happened once in Amazon. Just before Christmas, they invited kids of their employees to the company, and they used one of the bots and show the kids how they can converse. And what had happened, suddenly our bot said something like, "Santa is dead." And that was definitely a big disaster from the point of view of Amazon, but it's very difficult to protect the bot from generating sentences like this, because the bot would have to have some street smart, and there is nothing like that. It's just a parrot. It repeats what it heard, and we feed it with Common Crawl, which is a snapshot of internet on AWS, and it has it's tremendously large, but there is everything. There are all the political incorrectness, all the biases, and there is no way how to manually filter it. So we do our best, and not only us, but everybody, to come up with new ways how to filter out what may potentially hurt many of our users. So here, this is just a definitory or definition about what we call parametric knowledge, and that's something like the sky is blue. This is what the bot has learned, and the language model has learned, and that's by default there. But we also need knowledge about, for example, what were the results of ice hockey last night. And that's what the language model doesn't know, because the language model was trained sometimes end of 21. And to do the updates, we have to do another tricks. And this is shown on this slide, where we have another prompt, and the prompt contains something what we call context. And the context is a text where there is possibly the information the user asked, or the information we want to mediate the user. So that's the way how we get the latest, or how we get the information which is typical for particular topic. The current research is focusing on finding algorithms which are less demanding from the point of view of memory and CPU. We are working on knowledge extraction, user's opinion estimation, where we believe that the language models have a lot of information which has never been used yet, or people haven't thought about it yet, and these are the new arrays where we would like to follow. Here are challenges. I think that Holger has very well pointed out the many biases and inaccuracy and many other problems we are actually facing while developing artificial intelligence as a whole, and NLP or language model especially. I also would like to repeat at this point that one of the serious problems is the energy consumption. Then the other problem we are solving is updating to create continuous updates. Then multimodal, which combines a picture, which combines voice. We have the first research examples of generating not only pictures, but generating video from text. So that's the direction we are moving to. It is very important, and it definitely will happen. Accessibility and usability is another very, very important and today definitely overlooked area. because there is a Copilot, which is a system for programmers on GitHub, where programmers, while programming, are supposed to write first comments and then to follow with code. So in Copilot, they write first comments, and Copilot generates the code, and they can pick from 3 different versions, which they include to their code. Yes, it is dangerous for companies like Apple and others who banned to use their programmers to use this system, because the one who is running this system may easily, from the conversation from different domains, figure out what kind of programs they work on. And I'd like to close the presentation with saying thank you to all the faculties and the leadership of CIIRC, and to students, because it's a great home for all of us to continue working on this extremely interesting, and I also believe extremely important research problems. Here are some points, how we do it, how we work with students, how we would like to engage them in working with our industry partners, etc. So thank you very much. That's it.
Thank you very much, Jan. And now there are no questions on Slido, so questions in the room? Everything is clear, but I still do hope so.
It was so obvious that there are no questions.
There are questions.
Oh, okay.
Okay.
So, Jan, thank you so much. I mean, for me personally, this was a super insightful talk. In fact, you should have gone first. That would have been more effective. So let me ask you this. I like the fact very much that you put an emphasis on the importance of large-scale computing resources to really do cutting-edge research in this area, right? So, do you think in the medium and long term there is a problem if researchers like you who do this at public institutions, paid by the public, responsible to the public rather than to shareholders, have difficulties having access to these resources? Do you think that that's holding you back? Or let me ask differently, do you think if a large-scale public compute infrastructure were available, that would enhance your ability to do the wonderful research you're doing?
Well, today we have access, we pay this $20 per month, so we have access to OpenAI. And what I believe is that certainly these days companies such as Apple and so on, where the programmers do not have the access, these companies will soon have their on-premise devices or language models of similar capability. So they will do everything behind the firewall. So that's definitely the expected progress in this field. So, and what you are saying about the companies or the big moguls and the public, that's something which is hard to predict. There were many lawsuits in the end of 19th between many different content providers and Google, and most of the lawsuits ended up in nowhere because the public demanded so much the quality, the so good search, that the public pressure actually alleviate all these problems. And I believe that something very similar will happen with NLP, because the students suddenly bringing up their thesis have fantastic English. So when I read it, I definitely know where it comes from, and that's a benefit. So I strongly believe that we will find our ways how to use it. We are at the beginning, so we still have only few.
If you allow me to follow up, I share that feeling, but I also have a big worry, and the big worry is that, you know, if there's wonderful companies like Amazon and so on who make this available, that's great, right? But if anything ever happens, so that, for instance, in Europe, we lose access to these computing resources, just like basically overnight we lost access to the Russian natural gas on which we had become dependent, don't you think this would be a massive problem? I mean, in other words, is it safe, is it responsible to bet on a small set of companies alone to provide access to key technology that will drive soon large parts of our economy and society indeed? To me, that sounds very problematic.
Yes, you are aiming at the right direction. Clearly, Europe has to make up its mind and come up with some funding or come up with establishing communication between scientific teams, because today most of the scientific teams, because of being so much delved in their problems, they don't communicate enough. So if we all get together in Europe and start to work on something similar like OpenAI, and we know much more than when they started, so we should do it much faster. That is something what we definitely should do, not only because of to be lost or to be disconnected, but because of learning it and because of reusing it for our own benefits. Because, as you said, there are, the problem of Apple or not letting the programmers to use it is because they would do nasty things. They would release what is secret information easily without thinking. They would act mechanically, and that's the difficulty. So if we do it in Europe and we virtually provide it, for example, for companies so as they keep their privacy, that's the way how we should act.
Excellent, thank you.
Okay, I think your question, Holger, was a good starting point for the first panel discussion in the afternoon, because we will talk about trends of AI research and how to build AI ecosystem in Europe, and this is a substantial part of the discussion. So we are a little bit behind the schedule. So Jan, thank you very much for the presentation. Now there is 21 minutes. There are 21 minutes to have a break, coffee, some snack, and we will start at 11:10 exactly. Thank you. Ladies and gentlemen, it's time to get back to your seats because we are already delayed and I would like to give enough space to the next presenter.
Já mám 40 nebo 30?
Já vám to řeknu, máte 30.
Já si taky myslím.
No ale, no dobře, tak máte 30. Next speaker is Josef Urban, one of the leads of his project focused on AI and reasoning. He is linking in his efforts machine learning with reasoning. That's quite novel approach and unique, pioneering. So I don't want to talk anymore. It's his turn and his time to explain what was done. Thank you very much.
Thank you. So thanks everybody for coming here. I'm Josef Urban, and I've been working here now for let me think 7, 8 years. I initially came with an ERC consolidatory grant, and somehow Professor Mařík implicated me into even a larger grant. So at some point I was doing two big grants together. Luckily, there was sort of an overlapping theme there. And I should say a lot of what I will speak about has already been sort of introduced by Holger Hauss's talk. Basically for 25 years, I have tried to combine two areas of what I think forms like human or scientific thinking, and that's learning and deduction. And to start this with a funny slide, I hope you can read this a bit. So if nothing else you remember from this talk, remember this book, Logicomics, An Epic Search for Truth by Alexis Doxiadis, which is an amazing comics book written some 10, maybe more years ago now, about the life of Bertrand Russell and about the basically creation, about like a major revolution in science and mathematics, which many people do not understand. Even mathematicians sometimes do not understand it. So there was this guy called Leibniz, I'm not sure if Holger mentioned him or not, I think so, who had a very crazy dream, apart from doing amazing things like inventing calculus together with Newton, that one day humans who disagree, be it philosophers, be it economists, be it lawyers, be it mathematicians, be it physicists, be it computer scientists, will be able to resolve their disagreement by calculation, computation. Computation wasn't defined then, like they knew how to calculate some things. He was the co-creator of calculus at the time. But he had this crazy vision that one day we will have like perfect computational means to decide major questions, disputes, etc. And this thing, so Bertrand Russell is a great logician and philosopher who participated in this revolution basically in the beginning of the 20th century, where people basically embedded mathematics and by extension physics and hard sciences that are modeled by mathematics into logic. And they didn't know yet that symbolic logic will be the sort of substrate from which computation will emerge. what you today call computers are symbolic logic machines. So many of you are younger than me, have been born to computers. It's phones, and normal thing for many of you. But whenever you are playing with your phone, doing something on your computer, you are doing symbolic logic. So this, in this particular picture from the book, Russell is saying, like, what does it mean that like he dreamt the Leibniz's dream and he didn't achieve it? Well, what he means there is that, like, during his lifetime, we really didn't get there. Like we started to play with computers, and we sort of barely, by the time he died, started to do mathematics on computers, like really like reasonably advanced mathematics. But we haven't really moved to the more advanced territories like physics that Holger mentioned, and to say nothing about like law, about legal reasoning, which Adam is sort of aiming for with like various ontologies, etc. But it's a dream, and this dream is sort of coming. I think it's sort of unavoidable at this moment. With all the technology that we have, you may think that AI is giving us now with the ChatGPT, etc., the sort of bad side, like the confusing side, like it can do very confused quote-unquote reasoning, which isn't reasoning by any reasonable metric. But like with all these technologies that we have, it seems that like computational mathematics, like proving hard mathematical theorems, is really getting achievable at this point. With that is achievable like all the like, let's say, physics and computer science, which relies on mathematics. And I think what is even achievable, even though that will be harder because it's not exactly a hard science, is really very precise logical layer for things like legal reasoning or ethical reasoning. I think the technology is really getting there. So this project was, to a large extent, about this, about sort of trying to combine the two areas of, let's say, human thinking on computers, to sort of develop technologies that help, that sort of help the human or machine reasoners to find a way, to find the proofs, to find justifications by combining them with the intuition that you can learn, that you can learn when you solve some problems and you learn from those solutions, etc. So that's, in a nutshell, the project was sort of bigger than that. So there were quite a few people. There were seniors, juniors, administrators, affiliated researchers, partner institutions in the Netherlands and in Austria, our valued contacts there, and probably over 40 visitors, like over this time. You can try to see yourself here or see your colleagues there. These are our valued team members. And this is just a plain listing of all the visitors, which, if you know something about the field of automated theorem proving and interactive theorem proving, you will definitely recognize the names, let's say all of the names, at least on the first 3 to 4 lines. Like really, we managed to get here almost everybody who means something in the field of automated theorem proving and interactive theorem proving. So that's already was really amazing to have this possibility to invite these people here and do research with them. The topics was, as I mentioned, like my core area is combinations of like deduction, automated proving with machine learning. With that, a very interesting topic which we basically started and which is today being taken up by researchers around the world and at AI companies like Google and OpenAI and Facebook is automated formalization, which basically means that you take a piece of informally written mathematics, like mathematics written in LaTeX or Word or whatever, and now you train some machine learning system to translate that piece of informal natural language text into a formal text, which you can fully formally verify by computers. So the computer, after the translation to this formal language, I'll show you some example later, can really say that the sort of translated version of this particular argument is logically correct. This is, especially today with large language models or even small language models, and their combinations with various like feedback loops that are doing type checking and semantic checking. This is like a very promising area of research where it looks like instead of what people have been doing so far in the field of verification of mathematics, which is like typing manually a mathematical statement in some sort of programming language and then trying to manually prove it, we may have a shot at basically taking, let's say, all of the mathematics which is out there, which is like in various textbooks or articles, papers, etc., run some sort of reasonably augmented learning / type checking / semantic technology that we train in some feedback loop. And for free or for a much lower effort than these humans are currently doing, basically translate some non-trivial part of all these big mathematical texts. And that basically leads to this Leibniz dream that I just mentioned. Like suddenly, instead of, let's say, mathematicians or physicists or computer scientists quarreling whether some proof is correct or incorrect, how to formalize it and how the actually proof steps work, you will have a technology that will do this automatically or semi-automatically for you, like completely, like verifying, like even like complicated reasonings automatically. And again, like for those people who think that large language models are some sort of doom that will bring confusion to the masses, I think this may be one of the cures. Like the fact that you will take, let's say you ask some reasonable question, which is at least slightly scientific, like how would I solve this, let's say, mathematical problem or physics problem, and the large language model replies to in some way. It may be making things up, it may be correct, but if you manage to translate it to a strictly logical form, you may have a shot at basically verifying the answer of the large language model logically, like step by step. And if there is a problem, like the logic verification systems are good enough to tell you today, like here is the logical gap. I don't see how this step follows from the steps. So that's like a very, very interesting area of research that we started. There is more, like there are reasoning areas, like Adam Pease is working on ontologies. Mikoláš Janota, who will be speaking later, works on satisfiability modular theories. We have people working on complex systems and artificial life. We have people working on theory of systems and automatic control, data science, operations research, optimization, scheduling and real-time systems, Zdeněk Hanzálek and his colleagues, human-computer interaction, natural language processing, sign language processing, and some more. So the project was big. It was many people working for 6 years, and it produced over 100 papers, where more than 50% of those were with international co-authors. I'll just give you some highlights, and then I will go into what I sort of understand most, which are like these combinations of machine learning and automated deduction. So the project was divided into 3 work packages. The first one was mostly about like these combinations of learning and proving, where basically the main result, which I will show you later, is that we have shown that it is possible to take the best automated theorem proving systems today, which are extremely well engineered, fast symbolic systems, and make them much better by augmenting them with machine learning methods and introducing some sort of feedback loops where the machine learner gets better as the theorem prover proves more problems, and the theorem prover gets better as the machine learner, which is sort of advising the theorem prover, gets stronger by training on these more and more advanced proofs. So it sounds easy and maybe simple today, but basically the main breakthrough we only did 4 years ago. Like before that, it wasn't very clear whether we have something or not. As I mentioned, we did the first systems for automated formalization, and also for things like automated proposing of mathematical conjectures and synthesizing various interesting mathematical objects. We have one, especially Martin Sura, who will be talking later, some victories in automated theorem proving competitions. Our valued affiliated researcher, Bob Veroff, who is emeritus at the University of New Mexico and affiliated researcher here, has actually proved some open conjectures producing very, very non-trivial proofs here at CIIRC on our machines, basically, that really like resolve some problems that are interesting for mathematicians. So that's work package 1. Work package 2 was headed by Zdeněk Hanzálek, who is working on scheduling problems. So their results are in mixed criticality scheduling, and for example, they optimize robotic cells, or they are really applied to the level of being able to drive autonomously these small cars, these formulas that actually have their own racing competitions that they are capable of winning. And then there was research by Professor Svítek and his colleagues doing AI for smart cities, which I think has taken off like independently. There's more funding for it now here. In work package 3, we had Professor Kučera, who is like one of the best Czech scientists, who was just recently awarded the Česká hlava, the Czech mind, for solving long-standing open problems in control theory. And then we had people from Plzeň, from Pilsen, doing work on linguistics and sign linguistics, and, for example, winning competitions in hand pose estimation, etc., etc. So the group where Tomáš Mikulov works started very interesting research in complex systems, and I guess we all hope that Tomáš will get the opportunity to continue this research because it's what he is passionate about. So that was a brief summary of the project, and I have 10 minutes to go a bit deeper, and I do not know how much time I will have for that. So I guess some of you may recognize these pictures. So yesterday we walked to the concert with one famous AI researcher, one famous philosopher, like his name is Ed Zalta, that's this guy, and he just left today, and one famous ontologist who is over there, Adam Pease. And it was a funny walk, because as you go through Prague, you see places where people like Tycho de Brahe and Johannes Kepler worked. And I don't know how many of you know this history, but basically, like when these people worked here in 1600s, to some extent, to a non-trivial extent, they started a process that is called the scientific revolution, the basically development of scientific method, which at some point, if you sort of follow the line, went through people like Galileo and Newton and Leibniz, to development of science, to development of natural philosophy, to development of physics, to development of other sciences, sciences like symbolic logic, and as I said, also to development of computers and to development of artificial intelligence. So at that time, I don't know if I have the slide here. No. I think the funny thing is that at that time, there was such a concentration of smart people doing things in Prague that they were thinking that this could be some sort of singularity, so something that people would call singularity today, that the world will radically change. And it changed. It didn't change so quickly. They started a 30 years war, and that sort of slowed down things a lot. But like it got to people like Newton and Leibniz, who, as I said, like they developed physics, and they all declared all these crazy ideas about computation, which materialized. Like it took some centuries with like symbolic computation. Maybe, unfortunately, because Babbage wasn't funded as soon as he should have. But it basically happened, and to some extent, it started by people like Brahe and Kepler doing what we call today science, doing analysis of data, proposing conjectures, doing computation with the proposed conjectures, verifying whether the proposed conjectures work, refuting them, modifying them, and iterating this process. And this is the process that we today, in my project, want to emulate on computers. It's the process of scientific method, the process of doing science, basically. And I think if we manage to automate it, like their visions might come true, like the vision of computers automatically doing superhuman physics or superhuman computer science is really crazy. None of us can think what will happen when machines will start to develop new laws of physics, for example. So I'll move on a bit, because I'm 5 minutes down to the countdown. So I have already explained quite a bit of this. Like what we are aiming at is development of methods that combine the inductive thinking, which is like learning from examples, proposing explanations, conjectures, etc., and basically some sort of deduction, reasoning, computation, and designing the mechanisms which human scientists have in their minds. But somehow we don't really have yet systems that would be as good as human scientists in many. So a very good environment for doing this research is actually mathematics, and in particular computer mathematics, because in other fields it's really hard to see when an idea is right or wrong. You need a human who will sit there for a long time, stare at some ChatGPT output, and wonder whether this is a good product, whether it's a good mathematical argument or good physical argument, etc., or not. In this particular slightly unusual field of computerized mathematics, you get this basically for free. So people in the past several decades have basically managed, by quite a lot of manual effort, but also by some automation, to, let's say, formally express and formally verify a lot of non-trivial mathematics. I may show you some examples. But also like really verify pieces of code, etc., like coding libraries. So this is another picture from that funny book that I advertised. This effort of putting mathematics on this like solid symbolic computational foundation wasn't without problems. So even in mathematics, there were big people like Hilbert versus Poincaré, who had different opinions about it. Like some of them were more in the sort of deduction, the deduction direction, and some of them were protesting, saying that like if you mechanize mathematics, it will kill in the, like the intuition that mathematicians are working with. So this was actually a non-trivial process. But it happened. Like it, in the last century, after like this invention of symbolic logic, invention of computers, starting to develop AI, which, by the way, started with automated theorem provers called logic theories by Newell and Simon. People started to formalize mathematics on computers, develop automated and interactive theorem provers, and do things with them. And you will hear a bit more from Martin and Mikuláš. And this technology is today already useful. So people have verified graduate books in mathematics in these large projects. They have verified serious compilers, like C compilers, operating system microkernels, hardware chips, transport, finance systems, cryptographic protocols, etc. And there are all these crazy visions that start with Leibniz, etc. I'll just quickly, I'm running out of time, show you one example of formal mathematics. So this is a proof that every student of mathematics has at some point seen. It's the irrationality of the square root of 2. And this is how it looks in a formal proof language. This is what you do to have that piece of text that is here formally checked by a computer, by a machine, basically. So that's what these people are doing. What we are doing is to do these things automatically. We do not want to write them manually. We sort of try to prove them automatically. This is an example of one of the bigger projects called the Kepler conjecture. I started to talk about Kepler. So there is a story about him walking across the Charles Bridge in 1610 and being hit by a snowflake. And as he was hit, he started to wonder why the snowflake has a hexagonal shape. And he wrote a treatise about it. And in that treatise, he conjectured that the most compact way of stacking balls of the same size is this sort of orange pyramid. So this stayed open, unproved for 400 years. Then it was proved in like 1998, but the mathematicians didn't believe the proof. So what the authors of the proof did was to formally verify this long mathematical proofs on computers that gave them something like 20,000 lemmas of this sort of shape, which took immense amount of time. But what we could show like 9 years ago is that you can basically automate a lot of that stuff by doing some combinations of machine learning and automated theorem proving. So that was like the first plausible sign that things could be done. How much more can I talk? 2 seconds? All right. So I'll skip this. These are like technical details. Then showing you can probably download the slides later. Showing you what are all the things that you can do when you combine learning and reasoning. These are demos. Again, you can click on them. And these are the products that we have been creating during the 6 years of the project. This is one of our main systems which really broke the ground in the sense that it improved on the best automated theorem provers in the field. And I will not go into it here. What I will just say is that on this slide, you can see one of these feedback loops between learning and reasoning. You start with a system which is not trained, and you run it to solve some problems, and you learn from the solutions. Then you run the trained system again, and it solves some more problems, and then you learn from it again. If you repeat this 6 times, the system improves by some 70%. This is the kind of proofs that we can get today. We can get this one in 4 minutes. It looks like this if you write it manually. This is some sort of statistics about it. We have done other things, and I wanted to show this to Holger, but I will show him offline. This is a system to which you can give an integer sequence, and it's also running this feedback loop between like verification and invention using actual language models today. And I will skip the language and the Monte Carlo. Basically, what you give it is a sequence of integers, like primes in this case, and it will spit out a program that is trying to capture the sequence. Like in this case, these are pseudo primes. And it can do it in different ways. And sometimes when you have 2 different ways how the system thinks that it expresses some pattern, like primes, for example, you can ask the question, can I prove that these 2 things are actually the same? Can I prove that these 2 programs are the same? And actually, in some cases, and Mikuláš Anota will be talking about it, we can do it. So this is a SMT problem encoding the equality of the 2 programs. And this is a proof that Martin can produce with the vampire system of that particular equality. Here are some bets that, that I did actually in 2014, like how far and how quickly this field will move, and I will not linger on that. And let me just thank CIIRC, and in particular Professor Mařík, for welcoming us all here. Let me thank our sponsors, in particular the European Structural Funds and the OPVVV projects, my valued team members who were all great to work with, our international partners who helped us a lot, the visitors, and most of all, I would like to thank all the international, or the people, not just international ones, but the people who returned to Czech Republic and sort of took this risk of coming from, I don't know, Austria or the Netherlands, etc., and actually survived here, and I think started one of the first really like international English-speaking groups at the Czech Technical University. So thanks a lot. That's it.
Thank you very much. I have to say thank you for organizing such a group, for staying with us, and for promoting the Czech science across Europe. We are a little bit, thank you very much also for the presentation. We are a little bit behind the schedule, so I allow one question. I'll allow one question.
Everybody wants to go.
If there are no questions yet, there will be more chances during the lunchtime and in the afternoon. There will be, that's a good starting point for discussion in the afternoon. Thank you very much. Next speaker is Josef Šivec. Is the paper or presentation entitled Intelligent Machine Perception. That's the, as a matter of fact, the result of the impact project. So please, go ahead.
Thank you very much. Is it maybe too loud? Is it okay? Okay, fine. So thank you very much for coming here and for sort of me having the opportunity now with you to share this, the results of this 6-year project. And I want to start with a little bit of the history, the story. So I came here to CIIRC, to Prague, after more than 15 years abroad at different places. And I remember it was almost exactly 6 years ago, standing right here talking to, I think it was at the time, Czech Radio, I'm coming here, I would like to build a team. But I would like to say that at the time, it wasn't quite certain what will happen, how will it work out. So, but I would like to thank, this project and having the opportunity and Vladimír Mařík to be here. So what area do we work on? So we work in the domain of computer vision, which is about extracting information from images. So our human brain is very good at this. So if you look at this image, you can understand what has happened in the scene. You can recognize the image, objects and people. But you can also think what would happen if that maybe you can climb the ladder here, or what has happened in this scene. And still, although the automated algorithms are getting better at this task, it's still so far behind what our human brain can do. And just to illustrate that, really what the input is to the automatic algorithm is just a matrix of numbers, where each individual, here the number is the pixel intensity. So, and why the area is exciting is because images or visual information is all around us, from archives of visual information to cameras all around us. And what I found particularly exciting and was exploring in the project is what if we could learn from all this data? And just few motivating applications. The first one is learning for automatic assistance. Imagine that you have a system which could advise you how to perform a task which maybe you don't know how exactly to do. Or, and this is really a problem in factories, how can teach a novice a worker or just verify that they perform the steps correctly. And of course, in robotics, imagine that you could, the robots could learn from humans, say how to do a particular task, and then execute it in a new environment, maybe where a human cannot go, where it's dangerous. A third application area which is exciting and where we work is in autonomous driving. I will not talk about this much. We have a wonderful partner, Valeo, here, and we have Patrick Perez, who is the VP of AI at Valeo. Valeo has a large team in this area. We collaborate with them and have, which I think are some very nice results. But there will be a whole keynote by Patrick Perez in this area in the afternoon. So I really welcome you to come and see this and more in detail. He may talk also about our joint work, but they do wonderful other work in this area. So these are some of the motivating applications. I wanted to put some of the statistics, so really looking back at the project. So of course, we had some publications. I also want to mention that it's really, and in the context of the funding, it was really a wonderful opportunity, so which allowed us for over a period of 6 years really establish and do basic science, even on the areas which are a bit more theoretical. Especially, I would like to mention the 3 Best Paper Awards, which is really Tomáš Pajdla, who was a part of the team, which really is a very rare thing for someone in 4 years have 3 Best Paper Awards at main vision conferences. So there are 8,000 submissions or plus in this area. So this is. I was just thinking who else in the world has done this, and there are people who have maybe 3, but not concentrate in such a short time. So it is really something remarkable. And I will not talk much about his results because they are more theoretical. I'll show you more visual, more visual results, but it's really something which is wonderful. And of course, we also did some, and I will show a bit more about the competition. So here are some of the statistics. But what I want to really say is that behind this statistics is the people. And so we managed to build here a team of outstanding scientists across all levels, from more senior to postdocs. Some of them already left and they are at different places, to wonderful PhD students. And really it's thanks to them. I see some of them here, so thank you very much for all the contributions to this work. I also want to mention that the project was designed as a collaboration between CIIRC here and INRIA in Paris, which is an institute, for those who don't know, on computer science in France. And I see Patrick Perez already here. Great to see you. Thank you for coming. And so what I want to do in the remaining time is really just give you some of the highlights of the research which we do, and as I said, focusing on examples. I will not show any equations today. And here is the outline, and as I said, again, we also had work packages. These results are more from the work package 2 and 3, the more theoretical work package, where Tomáš Pajdla has worked. I will not show you examples, but there has been some really wonderful work winning prizes in this area. So I will start with visual language representations. And this is an area where we've worked for some time already. And an example of data source which we really like and we work with is instructional videos. So here is an example of instructional video when someone is showing how to change a car tire. So many people, I think, have done it here because we have to change tires for the winter and summer. But it's really a specific process with individual steps, and this person is explaining here the individual steps, showing how to use the different tools to achieve the task. So what's interesting is really a visual data together with a natural language narration. If you don't like the particular video because maybe there are different tools than you have, there are in fact many other videos of other people showing the same task with different cars and different tools. And in fact, there are really millions of instructional videos online from different areas of car repair, cooking, gardening, or healthcare. So it's really a wonderful source of visual and language data. It's like a test bed where we can play with and we can test our learning algorithms. And our motivation example would be, well, wouldn't it be great if you could, from this data, automatically learn some kind of an instructional manual, which we can then upload to an augmented reality device to give instruction to a novice user, or upload to a robot to execute a task in the novel environment. And so I will show you some of our steps in this direction. So one of the sort of underpinning what I will show next is learning these large visual and language neural network models, where the goal is to, so these boxes are neural networks which have parameters, maybe a very large number of parameters, maybe going to billions. And the goal is to learn those parameters from this data. And what's interesting is that this data is just available in large amounts in terms of, in the form of visual examples together with the narration, which is automatically transcribed where the person is talking about what they are doing in the video. So in some sense, it's this kind of a free supervision for us, which we can utilize and leverage to learn these models from a large amount of data. So what we've done, we've built one of the largest available data sets, video language data sets, still currently available from this instructional data where people are talking about what task they are doing. And the goal then, once we have the data, is to learn these neural network representations in such a way that the visual examples are matching, so they are close in the resulting space to the corresponding natural language description, whereas other natural language descriptions from other videos are far in the space. So there is a cost function one can formulate, but I will not go into the details here. Now, what happens if we do that? So we can now have this representation where you can type a query in natural language and find videos which have visual information which is relevant to the text. So if you type in glue, you can find videos where someone is gluing. You can type in glue wood, and you find videos where someone is gluing wood pieces together. But you can form other queries like cutting wood or cut wood, and you find videos where someone is cutting wood. But really using the language allows you to this kind of very large potential label space, cutting paper, someone is cutting paper, but you can even formulate a query which is more complex, like cutting paper in circle, and you find someone who is cutting paper in circle. So this is really a, potentially very large label space, which we obtain automatically by using the natural language. And you have heard sort of a lot of the current methods which you sort of see today, like the GPT, which is learned from text only, but also are using or are trained from visual and language information in a similar manner from a large number of examples from the internet. Now, there is another way, so one can find these video examples using a natural language query, but there is another way to probe how this system works, and that's the task, what's called video question answering. That's like putting the system to a test. You show it a video, this is a still frame of the video, and give it a natural language question. What type of material is the man touching? Or this is another, but imagine this is a whole video, I'm showing a single frame. What animal is shown as a cutout? And the system has to answer that question. So it's a little bit like testing the system, if you wish. And then the system can answer. The ground truth in this case is wood, and there are some answers by some systems, and there is one system, in this case, is ours, which actually can answer this correctly, and similar here. So this is just an example how you can test these language and vision systems, how well they work. And one particle, this is, again, I'm trying to focus more on the recent work, which has been published at NeurIPS last year in December, is that it turns out that some of these large models, you can actually, they are pre-trained on a lot of text, both in vision and in language, but you can fine-tune them together using a very lightweight, what's called adapters layer. So these are shown here in pink, which from much less training data for a task like video question answering. So skip some of the details, but show you some of the results on this test. You can measure what's good, and you can measure performance of the different systems. And let's focus on the first column. These are the different data sets, different tests. Let's focus on the first column. And the different rows are the results of the different systems. And what's interesting is also the second column, which is the number of parameters, which can be quite large, say, going up to 1 billion in this example. And higher is better. So it's like, what's the percentage of answers the system gets correct? So the first thing is, well, there is still some way to go. So from these questions, which maybe my daughter, who is 7 years old, she would probably answer all of them if it was in Czech. The current systems can do 63%. So there is still 4 out of 10 questions which they just can't get. So it sort of shows there is still a quite large way to go on this problem. And what's interesting that on this particular data set, even recently, we now all talk about the GPT. The GPT-4 has published results on the same data set. So we are, of course, wondering, well, how well the system, which is supposed to be very good, how well it's doing. And this is the number which they report. So it's doing 45. So that system is sort of 5 out of 10 questions is failing. So, and which is still quite a bit below what we can do. So I think it just shows, at least on the visual side, the problem is not solved, and we have quite a long way to go still. So that was on the first part on the learning visual language representations. And what I would like to talk next is that, so we can now, these systems can answer questions maybe out of video, we can describe video in language, we can search the videos, but still these are visual language representations. If we want to transfer some skill to a robot, we need more than that. We need to extract also geometry, physics, relations. The relations are there are interactions in the world, and that's what I want to show you some results here. And this is an example, again, of an instructional video on the left, and this is the reconstructed 3D motion of the person here and the tool. So what's important is that we have the person and the tool, and the yellow arrows are estimates of the interaction forces between the person and the ground and person and the tool. So, well, maybe play this again. So these are the type of reconstructions we can get from instructional videos. And why it's interesting? Well, we would like to transfer these motions onto a robot, and this gives us a more physical, geometric, and dynamic representation of the scene. I'll show you a few more examples where on the top input video there is some 2D extracted information, and on the bottom are 2 different views of the reconstructed motion with the estimates of the forces. And again, what's important that we don't reconstruct only the person, but also the tool the person is working with, and we do have some estimates of the interaction forces. And maybe I'll skip. So you get the idea of what we can do here. And so this was sort of one example we can extract from video. But then what I would like to show you is that we can take this motion, this reconstructed motion, and transfer it to a robot. And here I would like to also say that during the lunchtime, there will be so Vlado Petrík from my team will be giving, I think we don't have a robot downstairs, but he will be giving more details about this type of work, of how we can use videos to program or to guide robots. And so what, you can get more details from him during lunchtime is this example where we have an input video again, and we can use that to train a robot to perform the same task of transforming the material from one place to the other. And what behind that is really the reconstructed 3D motion, which then can guide the simulation environment, which otherwise it's very difficult to do that without that, to then transfer the motion into the robot. And we've done that on sort of from different videos. Again, from the internet, people doing different things, which we tested in different simulated environments. And what's interesting, because we focus on the tool, the same algorithm can be applied on robots with different morphology, going all the way from different degrees of freedom, but to even the humanoid robot. And so this is actually, we don't have the robot in the building, but we have colleagues who have this. So this is an example of the learned motions. But we collaborate with colleagues in France, in Lens, in Toulouse, who actually do have the Talos robot running, and we would like to eventually be able to transfer, have the robot to really watch a video and then be able to reproduce or transfer that skill, the motion, in the real world. So finally, in some of the results, I would like to mention, again, a work on the boundary of computer vision, learning, and robotics, where one of the key issues when you would like to manipulate or interact with the world around you is having some kind of a representation of the environment. And in this case, this is the input scene, which has several objects lying on top of each other. And if you, as a human, you could just easily go and pick up one of these things. But for a robot to be able to interact, to pick up an individual object is still quite challenging. So we designed an algorithm which can actually recognize the different objects and obtain a reconstruction of the scene like this, where the different objects are different colors, and then it's quite easy for the robot to generate a motion to grab one of these two objects. So this problem is called 6D pose estimation, where you have a set of known cut models, but you don't know their position in the scene. It's one of the oldest problems in computer vision, which has been addressed for 40 years. But we've designed methods which really combine and leverage the power of neural networks and large amount of synthetic training data to do that with very high accuracy. Here are some examples of, in the top row is input images, in the middle row are the overlaid 3D models on the scene, and at the bottom row are the reconstructed 3D reconstructions visualized. And really, by leveraging the power of large networks and synthetic training data, there is a competition on multiple different data sets, and we managed to do quite well on this task, which we were very happy about. And now we are working on how to transfer these algorithms on real robots and integrate them into the action perception and learning loop, which is very exciting. And I will mention that later. We also collaborate with the testbed to really transfer these results into industrial applications. So this can work not only for rigid objects, but also if the object is articulated like the robot here. So we can estimate not only the 6D pose, but actually also the articulation angles of the system, which then allows us to to then maybe interact with the robot if you want, because you can know what the pose the robot is in. And the most recent results are going in the direction where we really leverage very large data sets of millions of images. And if you didn't, these are all synthetically generated. They look quite realistic. They are full scenes. And by synthesizing images like this, we also generate effects like occlusion patterns, which really make this work even on new objects which you don't see in training time. So this was just published at Coral last year, and is a collaboration with NVIDIA. And allows us now, so we have lots of data at training, but allows us to now handle by robot objects which are new, which we have not seen during training, and handle even difficult situations where objects are partially occluded, like here. And then the robot can just look at the scene, identify even these objects have not been seen at training, identify them, and then grasp them. Some of it, it's difficult for special objects which are thin, which, estimating their pose of objects like scissors is not easy. And I will skip this. And again, I will point you to the demo downstairs, where Vladimir will show you how we can apply now this quite powerful approach to estimated poses of objects to solve difficult robotic problems. So this is a problem, the narrow tunnel problem, where the goal is to take the object and pass it through the tunnel. So for the robot to plan this, it requires to sort of multi-contact planning, which is not easy to do. But by having, we can solve this problem by having example videos of humans solving the task, and the robot can just then reproduce that motion. And so in the last few minutes, I would like to talk more about the outlook, like what next. So the project has been wonderful. It really allowed us to build a team here at CIIRC of and several international students, and we had really a sequence of wonderful visitors as well. So but what's going next? So really I would like to mention 3 things. The first one is we have really developed some which I think are very powerful algorithms, but we would like to apply them in practice. And I think that's quite a unique opportunity in this building because we can have people who do strong science, but also people who actually care about transferring these results into practical applications. And this is an example of, it's a European project, but where we have really industrial partners in, and the goal is to do small batch production. So if you manufacture a large number of cars, you can afford to build a production line just for this task, and it can run for several years. Problem is that there are other tasks which are what's called small batch. It turns out production of airplanes, every airplane is unique, so it's a small batch problem. So there you can't quite construct a line which will just spit out airplanes at the end. So we are looking at how we can utilize the fact that now it can be a mobile robot instead of a classical line, and it can perform the task in the environment. Another example is the manufacturing of elevators, which also turns out every elevator is unique. So it's exciting. We can now really test these and transfer these algorithms to real-world settings, and we collaborate on this with the testbed downstairs. Then the other wonderful opportunity is to now look at, so far we've been looking mostly at how to learn, how we can teach or how we can learn from humans how to perform different tasks. I think the next big problem is how robots can learn from each other. So I've been given this very nice project now to funding to continue this effort, so I'm excited about this, and hopefully in another 5 years, we can show you some results on this, how robots can learn from each other in different environments, and also have geometric representations of the environment. And the third area which I'm really excited about as well, which provides also a continuation, is machine learning for protein engineering. It seems a little bit far, but it turns out that robots are these systems in our macro world, but it turns out there are these systems in the micro world, which are proteins, which are really, which also have to respect physical and geometric properties. So we've been looking, and I have a growing team of people at looking at problems in that space. And one of this is an example of our recent work, and this is in collaboration with experts in this area, and this is the team of Jiří Namorský at Masaryk University and Tomáš Pluskal at UOHB just across the street. So we've been looking at methods for this world, and this is an example of a method which allows us to study the effect of drug candidates on these proteins. So first step is a molecular dynamics simulation, and this is one of them. This is a protein involved in Alzheimer's disease, very important one, without the drug and with the potential drug candidate. But of course, these simulations generate a lot of data. We have to validate them in laboratory experiments, not done here, but in the biology labs. But then machine learning comes in to analyze this type of data and analyze the effects. And we develop new algorithms to analyze the effects of this drug candidate on the protein, its dynamics, what's important. So you may have heard of AlphaFold, which predicts static structure from the sequence. Here we really care about dynamics of the protein, how it moves over time. So we are also very excited about this and applications in this area. And final thing, which I want to mention before this, a bit of an advertisement also for tomorrow, where there is a day of these are logos of the European networks in the area of AI. And I think this is also a big opportunity for us so we have also, I myself, but also others in the Zoom are putting a lot of energy in also bringing these networks here to this country and having the opportunities to collaborate with others. And I think it's opportunity now for us, and we are on this brink of an opportunity for us now to continue that and these wonderful collaborations. So thank you very much for the attention.
So, questions? Thank you very much for your presentation with nice videos in and with nice pictures. So, question? No questions? I saw that. Holger, please.
I would have abstained, but I think somebody needs to ask one question. So I'll do that because, many interesting things you've discussed, fantastic. I'm curious, you talked about long sequences that need to be planned in your production outlook work. I find that interesting because engineered systems, when you manufacture them, increasingly have that, right? So I'm curious, what's your intuition? Do you think sub-symbolic neural network techniques alone will do that? Or do you think that this might be an area where actually bringing together techniques from the two worlds that Josef spoke about Josef Urban spoke about so eloquently might actually be an easier approach to that? What's your intuition?
That's a great question, thank you. I didn't talk about the details, and in some sense on purpose. I just wanted to show you the videos. I will be very happy to talk with anyone about the details. The approach we've taken is, and this is also partly because we have wonderful collaborators in robotics. So we are not really trying to bring the best of the both worlds. To really, in robotics, there's been a lot of wonderful work in planning, in task and motion planning, and we are trying to connect them with more learning and learning from video. So what the results, which I haven't shown, you will see downstairs for the planning, it's a combination where we augmented, some of the best planning algorithms from robotics, the RRT algorithm, by, from the data, from the video to solve the task. So my intuition at the moment is that, there's so much wonderful work in robotics, which, and we should build on both, on top of, stand on the shoulders of the giants in the both worlds to solve the problem. And let's see, how it goes. And I'm very happy to have wonderful collaborators from robotics in this area. Thank you.
Thank you. Thank you very much for your presentation. There will be again time in the afternoon for continuing in the discussion about symbolic, sub-symbolic computations. Now I would like to invite Professor Robert Babuška, who will present the results of the project Robotics for Industry 4.0. Robert.
Thank you. Thank you very much for the introduction. Yeah, good afternoon, everybody. I hope you can sustain one more talk before the lunch. So thanks, Yojin, for already introducing robotics in the context of machine perception, and I'm happy to continue in this trend. So I'll be reporting on the project that's called Robotics for Industry 4.0. And I actually still have a double affiliation. So next to my CIIRC appointment, I'm still a part-time professor at the Delft University of Technology, where I lead quite a large team focused on robot learning and control systems. So I wrote down robots are all around us. Maybe it's a little exaggerated. If you walk around the street, you don't really see that many robots. But if you look more carefully, you do see robots. If you go to industries, let's say a car factory, you will see robots welding systems. And actually, they don't look much different than in the 1960s when they were introduced. So these are pretty lump, dangerous machines without much perception, actually without any perception, just doing repetitive work. Luckily, more robots are being introduced. This is a picture of Baxter and Sawyer in the brotherly embracement. An attempt to introduce collaborative robots. So robots that are much lighter, much safer to interact with, and that you can put standing next to a human worker at the production line, for instance, and the human worker can actually teach the robot by grabbing its arm and showing a specific task. Unfortunately, the company who introduced these robots is already bankrupt, so you can see one of the problems in robotics is that it's extremely difficult to bring new robots to the world. It's a really painful and very expensive process, and there's a lot of gaps and challenges I'll be talking about. More recently, you see these kind of robots. This is the Stretch robot from Boston Dynamics, which is a mobile base, very quick, very agile, with a robot arm. And it has a suction cap or some other type of device, and it can very quickly grab boxes and transport them, for instance, from a truck to a box or something like that. Then, of course, besides manufacturing, you have many other robots. An example would be inspection robots, which you can insert into pipes. let them drive through the pipe, and with the help of sensors, inspect the quality of the walls and these kind of things. If you go to the medical sector, you have the very famous Da Vinci system, but also other more recent robots are upcoming, which are very helpful for certain type of operations, actually improving the performance of the surgeon by quite a margin in specific sorts of operations, like prostate, for instance. And you can go on and on. If you count, for instance, drones or quadcopters as robots, you start seeing more and more of these in inspection tasks, for instance, in industrial applications, but also in mapping, restoration work, and you name it. Of course, all kinds of semi and fully automated vehicles, except for personal cars, which we don't yet have in the streets, but there are dedicated zones, for instance, where you already have fully automated transportation available at airports, for instance. And if you go to consumer products, you can these days buy lawnmowers, and you can buy vacuum cleaners and all these robots. They are actually the most robots sold in the world are vacuum cleaning robots. That's quite obvious, I think. And there are quite futuristic robots coming. This is the Optimus by Tesla, which is not yet ready for the deployment, but it's being showcased already. And it's meant to be a kind of industrial helper and also service type of robot that could do all kinds of versatile tasks in environments where you need actually bipedal walking. So it doesn't have a mobile base as we are used to, but it's a bipedal robot with all the complexities involved in there. Okay, so you could say there's lots of robots, so what's the problem? Why should we do research? And there's also huge potential for robotics, right? So robots are supposed to take away the dull, dangerous, and dirty work, and by that we get very easy, safer, and much more pleasant work left over for us to do, which is definitely a big step forward. They also have the potential to deal with demographic changes. As you know, the birth rates are declining, the populations are aging essentially throughout the whole world. So there's an upcoming issue with the lack of workforce, basically. And robotics is at least a partial problem to these issues. We still have to reproduce as humans, clearly, but that's a different thing. Energy and material efficiency can go up. If you robotize, you can make processes much more efficient, not necessarily due to the robot, but because you have to think about the system as a whole, and you have to make it more efficient. And also, you're logging lots of data, and you can use this data to monitor quality, to do improvements in your process, and so on. You can also bring production back to countries like the European car countries, and therefore closer to markets, with all the advantages thereof, and reducing, let's say, transportation costs and all these kind of things. You can improve the healthcare, you can improve the quality of life, so you could say there's a lot to gain, but yet robotics is not so widespread as you might think. If you look at this, we are 100 years down the line from this famous movie, and we still have processes like this. On the right-hand side, you see an example of a horticulture production line in the Netherlands, which is not very far from the Delft University. And my colleague used to work on robotizing this problem. And this proves to be extremely difficult. You could say, what's the problem in inserting this yucca stem into the pot? It looks very easy. It's not. It's not. It's extremely difficult in terms of sensing, the manipulation skill, the force sensing that you need to involve in this task, and so on and so on. And this is one example from horticulture, but you can go to any industrial process. There's a lot of manufacturing that's still done by hand. In the break, I've been discussing with colleagues, Airbus is producing aircraft. The fuselage is essentially assembled by hand. All the nails, all the screws, everything is done manually. And it's extremely difficult to robotize these kind of things. So why is that? There's lots of challenges that you have to face. We have seen a wonderful talk on perception, but in robotics, perception is not enough. You have to integrate it with motion control. The robot has to do something, has to correct the motions as it perceives the change in the situation, and you have to integrate it with other things, like dexterous manipulation, for instance. If you grasp an object that is not fully known, that's not described by a CAD model, you have to feel what you're grasping, and you have to accommodate the forces that you apply, and so on. Learning, of course, if you program a robot to do a task, and if the environment is complicated, you're going to achieve, let's say, 70–80% success rate, and the rest will be left over to humans to clean up after the robot. And this is not sustainable for the industry. This is not feasible at all. So what you would like to have is to have this initial, let's say, 80% performance, and then have the robot go on and improve and learn as it gathers data to get, let's say, close to 100%. Human-robot interaction, we obviously do not want to replace humans by robots. We want to introduce them next to humans to help them, to assist them in difficult tasks and so on. So interaction is extremely important. Performance and reliability. If you think about these AI apps you have on your computer, like ChatGPT or anything on your mobile, you're pretty happy with the performance, like 80, 90%. And you're quite satisfied. You say, look, it works in most cases. If you put something like that on a robot, it doesn't work at all. It just breaks down each time the robot tries to do something, so it doesn't work. We often think about our cars as highly reliable systems, but if you think about a car, you use it about 2 to 4 hours per day on average. A robot is designed to work basically 24 hours a day. So just imagine the margins for errors that you have if you're applying tools from AI, from machine learning, other fields, to robots to be deployed in the field. And on top of that, it's an extremely multidisciplinary approach. You have to combine expertise in mechanical engineering, electronics, computer science, but not only computer science, but many subdisciplines, machine learning, computer vision, speech processing maybe, control engineering, and so on and so on. So you need many, many expertise to come together jointly, smoothly. So lots of challenges to face. And our project, R4I, was aimed at addressing at least some of them, right? You cannot address them all, but we tried. So we looked into 3 topics or work packages, if you will. The first one is on robot learning, autonomy, and mobility, with the aim to introduce robots that are much more autonomous, but still do what we want them to do. And by using machine learning, by using concepts like lifelong learning and mobility in unstructured environments. And I will show some examples. Perception, grasping, and manipulation. I think it speaks for itself. And finally, interconnected systems. So systems in which you have multiple robots that should be coordinated to perform a task jointly, and where you also have human workers or human players that can interact with these robots. So we worked in a large team at CIIRC. Here you see a list of about, I think, 18 people. I hope I haven't forgotten anybody here. The first 3 names are people who led the 3 work packages. And then we have a collection of people from very senior researchers at CIIRC through junior researchers, postdocs, PhD students, all the way down to is not the right word, all the way to bachelor students, actually, who joined our team and delivered wonderful work and also made it through to proceed to do their PhD in the end. So all in all, a very versatile and very nice team to work with. We have also collaborators in the Brno University of Technology, the CETEC, which is the Central European Institute for Technology, and we have collaborators in Pilsen, the University of West Bohemia in Pilsen, who are mainly focused on speech processing, language models, and these kind of things. And the Brno people mainly work in drones and mapping perception of the environment and fields like this. So about the achievements, I think the main achievement is that we have created a large team at CIIRC and also collaboration across several departments. I think if I count correctly, we work at least across 4 different departments, including the group of Eugene and of course also of Pepa Urban, with whom we are also continuing the collaboration and starting some new projects. So we are part of the European networks that have been mentioned, Alice and Claire. And we have also managed, thanks to great efforts of my colleague Libor Přeučil, to get IROS 2021 to Prague. And if you know something about robotics, there are 2 main conferences, ICRA and IROS. So we were extremely proud of this step and hosted this conference. Unfortunately, in the COVID lockdown, so that was not that great, but the conference itself was a big success. Yeah, I've mentioned this already, and we have also embarked upon follow-up proposals. So there is a follow-up proposal called RoboProx, which is the Jan Amos Komenský framework. and a huge effort headed by my colleague Zdeněk Hanzálek. And we have a project to start very soon, which is called Core Sense. It's a hop-on European facility, and we are joining a team of many, many universities from Europe to continue our work, also jointly with Josef and his people. We have contributed to building lab facilities. Yesterday, some of you might have seen the testbed. So part of the testbed equipment was also purchased and made operational within this project. And colleagues of ours working under the leadership of Carla, she's not here today, they have established what is called the Imitation Learning Center for Robotics, and you will see some pictures of that soon. And we have published about 100 or a little more papers in international journals and conferences. So if you are interested, I'll give a link in the end. You can go and check what's up there. So I want to show some selected results now, just very, very briefly to give you some flavor of what we have been doing. The first one will be on vision-based navigation. The second one will be on algorithms for data-driven, but still physics-oriented modeling. That's something that you definitely need in robotics. And the third example will be on human-robot interaction and also collaboration among multiple robots. So first, vision-based navigation. One of the major problems if you want to deploy robotics in applications like, let's say warehouse management or logistics, is that these are typically indoor applications, and without putting any additional infrastructure, you cannot actually navigate these robots because there is no GPS available indoors, or not reliably, and therefore you have to put some additional instrumentation to actually make the robots applicable in that environment. So that's a difficulty. So what we aim to do here is to use the onboard camera of the robot as the single sensor that is used to navigate the robot, as what we do as humans, right? Basically, you look where you want to be, you look where you are, you compare that with the image that you foresee as your goal, and then you somehow navigate toward that destination. And we also involved here reinforcement learning as a method to learn not just any plan, but preferably an optimal plan. So minimizing, say, the time or energy that you need to get to your destination. So how do we do this? So we have an observation from the camera, which is an image, the upper one, and then we have a target, which is given by another image. And then you use these two images and you feed them into a deep neural network of the standard, let's say, convolutional type. And at the output, the network spits out signals that are used to directly control the robot. So in this case, we used the wheeled platform, the TurtleBot. So we basically gave commands to the two wheels that just tell the robot whether to go straight or turn at a certain rate and so on. So this is called the end-to-end learning. So from perceptions, basically directly to control commands to the robot. How do you train such a system? Because it's a neural network, it's a black box, it has lots of parameters. So we used simulation environments like the DeepMind Lab, the House 3D, or AI Tour, which are essentially photorealistic, up to a degree, 3D models of environments, and you can simulate the robot moving in these environments, and you can train the system. So if you do that, it takes a couple of tens of millions of frames, so it's a long process. It takes about almost a day to train this system, but in the end, you can basically navigate. So if you do a simulation then, you drive the robot around. On the right-hand side, you have the target image. What you see on the left-hand side is the current view of the robot camera, and in the end, it navigates to the location where it's supposed to be based on the target image. Maybe not perfectly in this case, but it makes an attempt to get there, right? So you can evaluate how accurate it is, and so on and so on. Now, we also deploy this on a real robot. There, you obviously cannot use the simulation environment, because that is very different from your lab or from your warehouse. So what we did here is to use this robot to collect images of the environment, and then we used our own kind of simulator of that environment to train the already pre-trained system that we had to recognize the images from this environment and navigate in there. So it all worked nicely, and it's published in a paper that you could have seen at the bottom. The next application I'd like to highlight is efficient learning from data. And here I don't mean learning in the previous sense, where you pre-train the robot in simulations. Here I mean mainly learning from the experience as the robot is deployed in the world. Robotics is very strange in the sense that you're engineering a system where you know part of the system very well. That's the mechanics of the robot. You know the joints, the inertias, the motor parameters, all these things. And you don't know a large part of the whole system, which is the environment of the robot. The user can deploy the robot virtually anywhere. It can be used to manipulate light objects, heavy objects, soft objects, hard objects. You just don't know. So ideally, what you would like to have is a system that can learn from data as it operates to optimize its performance. And now this learning is very difficult. If you compare it to learning, let's say, large language models, which you feed with all information that is available, this is a very different ballpark, because you have no data. And as the robot starts operating, you are gathering a few data points, and you would already like to have a model that helps you to operate the robot well. So you should learn very quickly from small amounts of data points. And these data are not perfect, right? They will be noisy, there will be outliers, sometimes some signals may disappear or fall out. So you have to face this kind of uncertainty that's inherently present in data gathered online, real-time, from sensors. As you go on operating the robot, the amount of data increases, but unfortunately, the information that's in the data will not increase necessarily. You'll be getting about the same data all the time, because many tasks are repetitive. So the robot is doing the same thing, and it's gathering essentially the same data over and over. So you have to somehow filter the data so that you can filter out those data points that are interesting, that add something new, and basically ignore the rest so that it doesn't overwhelm your learning system. And what you like to have, of course, is that you improve the performance over time. So basically, the robot doesn't get worse. If you work in neural networks, you know the term catastrophic forgetting, which basically means that the neural network beautifully learns up to a point, and then all of a sudden, it starts to forget. It starts to do things that it was not doing before, maybe hallucinates, you could say, in current terminology of the LLMs, and so on. You absolutely don't want to have this in robotics, right? You want to have a nice continual improvement of the performance. So an example of methods we use are methods that are capable of learning analytic models, so basically equations from data. So no deep networks, but analytic equation models. These methods are called symbolic regression. It's a bit unfortunate name, but anyway, I'll explain how they work. So you have some set of experimental data that may represent some unknown function. Here you can think of anything. Maybe a robot manipulates an object which is unknown in terms of its mass. And you want to model how the arm with the object in hand will respond to the motor commands. Or it grasps an object with unknown structure or unknown stiffness. You want to model how the object will respond to your grasping force. And you can go on and on and on. There are many examples of how you can apply this technique. Then we use typically genetic programming, but you can use other techniques, neural networks, transformers, and so on, to actually create an equation. Through this evolutionary process, you can synthesize from some primitive functions a larger function, which is shown here, and that gives you an analytic model which hopefully nicely, smoothly fits the data. But this is not working satisfactorily, because the data, as I said, is sparse, so it doesn't cover the entire region, and typically at the edges, you get performance which is not what you would like to have. So what we added to these techniques is the use of prior knowledge. Very often you know things about what you're modeling. You know the asymptotic behavior of your function, or you know that the function is 0 when the inputs are 0, and so on. It may have some extrema that you know the positions of. So you can insert this prior knowledge into your modeling, and that vastly improves the performance. So here's a paper which you can consult if you'd like to know more about these things. And we have also used other methods than evolutionary programming, because evolutionary techniques do not scale well with the amount of data. If you add more and more data, you have to evaluate the fitness function over large data sets, and that's computationally very heavy. So we are looking at neural networks, very specialized ones that use specific functional nodes like mathematical operators, functions, and so on, and then some learnable weights and some fixed weights, and you can use gradient-based techniques with regularization to essentially prune away some of the weights and in the end get a model which is very sparse in terms of the network structure and which you can write down again as an analytic equation, and we can also insert prior knowledge in these type of models. Finally, you can go on, be very inventive in techniques you use. We can also use transformers, very similar to the language model, to essentially synthesize the function. So we give, in the training set, sets of data and sets of corresponding functions. We tried single-variate and bivariate functions, hundreds of thousands of functions, and you train the transformer basically to look at the data and tell you this is the function I think would fit this data, and also give you parameters. So in this case, for instance, this looks like a sign, and the parameter is 0.2 in front of the argument x. So it's a combination of symbolic generation with some local gradient search for the parameter tuning. And the advantage of this approach is that you spend a lot of time in the training, that's okay, but then when you deploy it, it takes just a few seconds to give you the model for a completely new data set that you haven't seen before. So these methods, I think, have a very large potential. The final example is human-robot interaction. So you probably know that programming robots is very costly. It costs an amount, let's say $1 million, to buy a robot, and it will cost the company about the same amount of money to actually get the robot programmed and verified so that it does the task for which it is acquired. So this is a huge cost, and many companies just cannot or do not want to go into this. So the idea is to use humans as teachers for the robots in a similar fashion that a human worker with a lot of skills and lots of experience would train a novice in performing a certain task. And what you would like to do here is, I think, similar to what we have seen already, is to integrate different modalities. So for instance, vision and speech to start with, because this is the way that humans would normally communicate and teach one another. So to that end, we have some centers or some laboratory facilities designed that allow you to use human input, like on the left-hand side, you see a gesture, for instance, pointing to an object. The gesture gets recognized, and the robot executes a specific task. Or we use multiple robots, and we can do all kinds of training of these robots. An example is given here. So we have the system instrumented with cameras and also with trackers. So you can put a little device on your tool. So for instance, here, it's a grout float, or you can use a roller or a glue gun or tools like that, instrumented with this tool. And then a human worker would execute the task as normally, right? So basically, you're watching with a camera, and you are measuring the ground truth with this tracker. And then you can use techniques like 6D pose estimation methods to actually estimate the exact pose of the tool. And with that information, you can already feed the robot the trajectories that it could execute in order to carry out the task. Maybe not perfectly in the beginning, but hopefully you can use learning then to improve on this execution. And this is very different from the kinesthetic teaching, as it's called, where the human worker has to grab the arm and basically show by pulling the arm what the task is. This is very awkward, and this would be, in certain situations, it would be unacceptable, for instance, if the robot is very heavy, dangerous, and so on. So this is a very unintrusive technique to use human inputs for robot training. And we can use the same setups for teaching robots to work collaboratively or optimizing them to work collaboratively. Like in this case, you may have two robots with their own workspaces that would overlap, and the robots could jointly carry out a certain task. So for instance, in this video, you see a simulation, which you can readily deploy on the actual robot, because these are high-fidelity simulation models of, in this case, the KUKA arm. And you can do tasks like, for instance, inserting bolts and nuts. So one of the robots inserts the bolt, and the other robot tightens the nut, for instance. Or they can do welding and deburring and these kind of things. So I hope this gave you an impression of what we have done within the R4I project. In the end, I'd like to acknowledge, of course, CIIRC with Professor Mařík as the director who actually brought me here, back here to Prague. And of course, the funding, which has been very generous and gave us the opportunity to do all these things that we have done, as you have seen. And of course, the whole team, and also the people who supported us through the whole project. So many of them are here in the room, so let me use this opportunity to say a big thanks for your support. And if you would like to see some more information, please visit the website and check what's up there, including the publications and more details about the work packages. Thank you.
Thank you. And now I'll ask for one single question, no more. This presentation will be followed by a visit of the testbed, so you can see some robots in operation. We will start in 4 minutes with the tour. So, who wants to put the last question of this morning? It's already afternoon, but of this morning. If none, nevertheless, there will be discussion in the afternoon, and it's, the whole morning is preparation for panel discussions in the afternoon. So there will be additional opportunities to put questions, and I would like to thank you once more for your participation in the research program, for your coming to Prague and staying with us, and for your presentation. My last remark, all the presentations, that means slides, will be available as well as the video records of the presentation of the speakers. So, thank you very much. Enjoy your lunch. Enjoy the visit to the testbed. Lunch? Lunch? Lady will inform you better. You know, I am not the best informer. So, please, Eva, do it.
Okay, thank you very much. I have good news, actually. You are not going to the testbed right now. You can have the lunch and enjoy it. But please join us, let's say, in 20 minutes so that we will somehow meet the schedule that was planned. I will announce the tour in the testbed again. Thank you.
Hello, please come and take your seats. We are starting soon with the keynote for the afternoon.
In London. Probably it was a good opportunity for him to be in London.
Oh yeah, it's true. I know the connection. Please come and take your seats. We are starting with the keynote very soon. Please come and take your seats. We are starting soon.
One, two, three. Good. I know it's a bit tight and warm.
Please take your seats. We are starting. Take your seats. There'll be more coffee breaks, more food, more coffee coming our way. We have a very nice, interesting afternoon with a keynote speech, panel discussion about future of AI in Europe, followed by exciting technical talks about some of the research done in this building, and finishing with another panel about trends in AI and future breakthroughs, which are of course hard to predict, but we'll try our best to tell you what we think is important and interesting. So, but let's start then the afternoon program. It's really a great honor and pleasure to welcome here Patrick Perez, who just came in from Paris. Patrick is a VP at Valeo, or VP of AI at Valeo, and the scientific director of Valeo AI, which is an AI research lab focused on automotive applications and self-driving cars in particular. So before joining Valeo, and Patrick was a researcher at Technicolor, Microsoft Research Cambridge, and INRIA. Patrick is very well known for his work on multimodal scene understanding and computational imaging. And it's an honor and pleasure to have Patrick here. Patrick, welcome, and the floor is yours. Thank you.
Thank you, Joseph. Thanks for the invitation. Always great to be here in Prague. So, given the temperature, I should have talked about reinforcement learning for thermal comfort management, something we do for in-cabin vehicles. But the topic is different today. It's about autonomous cars. And in particular, where are they? I mean, they have been promised in 2015, they have been promised in 2018, 2020, etc. And somehow they're not yet here. So today, I'd just like to say a few things about the state of affairs, also with illustrations from, with research from my team. But of course, it started as a dream. This is an artist depiction from the mid-50s in a commercial. Actually, it's quite interesting. It's not so far from what new artists are envisaging. But anyway, so that was the dream, and to some extent, the dream almost came true already quite a while ago. I don't think it's very well known, even in Europe. It's a shame, because from the mid-80s to the mid-90s, there was a funded project, in particular with France and Germany, called Prometheus. And it was about autonomous vehicles. And what you see here is that with the technology of the time and the computer of the time, they managed to have first this big van, the Mercedes van, and then an actual passenger car equipped such in a way that it could be driven autonomously on the highway with lane changing using, guess what, a camera with a neural network. So that was pretty amazing. And I have put the link to a complete video on YouTube if you want to check out. It's very interesting. Of course, there are other milestones. In particular, on the other side of the ocean, there were these two well-known DARPA challenges in the US about autonomous vehicles. One in 2004 in the desert, and the other one in 2007 in sort of fake urban environments. And that was a big boost also to the topic. And not long after, we saw that already this morning, the little car from Google, so the Google car, which was the inception of the modern era of autonomous vehicles. And effectively, they are becoming a reality. For people who are going to San Francisco, for instance, in particular, Waymo, which is the former Google car branch, so it's an Alphabet division, as well as Cruise, they are now allowed to deploy 24 hours a day, every day, actual robotaxi services in town. So things are getting very, very tangible here, and the same in China with Baidu, for instance. So things are actually moving forward. But so this is quite spectacular. But at the same time, it shouldn't hide a very important fact that when it comes to autonomous vehicles, we are talking about many different types of vehicles and many different types of use cases. Let's start with delivery. So this is a big topic, delivering. This is also sometimes called the last mile delivery problem, with small vehicles which don't run very fast, and they are packed with goods. You can do the same with people, with shuttles. They go from A to B to B to A, not very fast, and they are very useful. You see here two French startups. Unfortunately, the first one has recently closed down. But also, it was also alluded to this morning, there is other probably less well-known things. At the bottom, you see these big, these monsters from the mining or the industry or the agriculture. And on the top, you see another branch of Waymo, which is about logistics and trucks. So a lot is happening. Now, when it comes to passenger cars, which is what people have in mind when we talk about autonomous driving and autonomous cars or driverless cars, it's a bit more complicated. So we have. I'm not going to explain in detail this table here, but this is the sort of official terminology or ranking of the different levels of automation when it comes to driving. On the left, the blue part is level 0 to 2. It's assistance, so the driver is in charge. On the right, mostly green, it really becomes partial or less partial automation, and it goes from level 3 to 5. And in this case, the system, when engaged, is in charge. Okay. When you think of this classification here, it means that typically the robotaxis are here because there is no driver at all, but they cannot go everywhere. They are geofenced. So essentially, it's a level 4 automation. But if we think in terms of passenger cars in particular, which are actually commercialized, well, there are a few well-known brands, American, Asian, or Europeans, which do that, level 2, level 2 plus, for instance. In particular, level 2 plus, there is a Mercedes car which was released last year. They doing what is called traffic jam assist on the highway, less than 60 kilometers per hour, but in this case, the driver can really do something else. It turns out that in case of problem, he needs to be able, or she needs to be able to recover, to take over within 10 seconds, which is quite demanding, but at least you can do something else and get your eyes off the road and your hands off the steering wheel. Level 3, well, I mixed up a bit. What I just described is actually level 3, but it's very limited in terms of speed and type of domain of operation. And as far as I know, there is not more in terms of passenger cars, at least commercially speaking. So maybe it's important at this stage to stop here, but to understand why we care, why we pour so much money and energy and research in either autonomous driving, which is sort of one of the holy grails, but not the only one. The other one being what is called ADAS, for Advanced Driving Assistance Systems, that we have in passenger cars nowadays. The obvious first reason is safety, in order to reduce the casualties on road, and there are still too many of them in the world, but not only, and also it was alluded to some extent this morning with robots. There are other benefits. One is, of course, to free the time of the drivers, so more comfortable, but also to make things more cost-effective when it comes to robotaxis or logistics. By the way, there is a strong shortage of truck drivers in Europe. It's also more inclusive in the sense that for people who are deprived of the ability of driving, maybe now they can, again, get the ability to move around with these vehicles. All in all, it should allow to have a smoother traffic, being more efficient, and hopefully more sustainable for these reasons. So plenty of motivations to work on that. And as a researcher, there is also the motivation that it's super hard, so it's very exciting. So which brings me to the challenges in a nutshell. One have to bear in mind that these systems, whether autonomous driving or driving assistance, well, first of all, they are embedded in a vehicle, so it's essentially an autonomous robot. Everything has to run in real time or super real time with limited resources. But of course, it's highly critical in terms of security. You cannot mess around with these things. It's deployed in the wild in very complex environments. And once in the road, these vehicles, they are there for 10, 15, 20 years. It's not like a mobile phone. And one of the important things is that it's a lot based on machine learning, which is great, but comes with well-known limitations. So at the end of the day, in order to have these things put on the road in a trustworthy manner, you need to make sure that they're actually reliable in a broad sense, that they are thoroughly validated, which is something we do at Valeo actually in Prague, and that they are certified as any vehicles on roads. Let me go through rapidly the typical driving stacks, which is effectively, again, at least in this classic version, an autonomous robot stack. You start with one or several sensors whose signals are fused either late or early in the system in order to build some perception of the world, and it might or it might not be combined with precise geolocalization and the accessibility to a HD map. It's not mandatory, but all these things put together allows the ego vehicle to build a model of the scene around it, up to probably, like, say, 200 meters away. And based on that, then you start predicting or forecasting the trajectory of the other road agents, and this is fed to the planner and then to the actual control of your vehicle in terms of direction and speed. If you think now of what has happened with the revolution of deep learning a decade ago, well, essentially deep learning has started to sort of to enter this stack, in particular, not surprisingly, for perception, but also for prediction, a bit less for planning, to be honest. But there is another route, which was again mentioned this morning for robots, which is way more radical, which is called end-to-end driving, where you try to learn to design and learn a monolithic model which goes directly from raw sensing directly to action. And there are actual systems on the roads doing that. In particular, you can check out the Wave startup in England. Okay. Let me show you something that we do at Valeo, already an old video, but I think it's interesting. It's one of our experimental platforms for autonomous driving. You might recognize at the bottom Paris, so it's driving in Paris in this case. Also long-distance driving at the top with different trips that we've made. What is interesting, I just highlighted it, is that this platform, it's not a real, well, it's a real car, obviously, but there is a lot of things in the trunk, like compute. But the sensors, the actual Valeo sensors that we build and sell for the car makers. I will say something more later, but just playing the video, you will see that this vehicle is able to, handle the Parisian life, which is not always very easy or quiet, as Joseph knows. You see the inside of the car. You see also the technical view with some 3D detection with boxes, etc. And also, of course, you should be able to go from light to night or to tunnel, etc. And this is one aspect of robustness that I was alluding to, and that's why I stopped my excerpts on the low light conditions for 3 of them. In terms of tasks, well, I will talk now mostly about perception. So there are a bunch of them. These are just examples from different labs. In this case, it's ours, where it's Valeo in the US, working on the. So it's the typical 2D perception task. Everything is in the image domain. In this case, it's the analysis of the detailed analysis of the pedestrians, including the pose and the intention to cross or not, which is obviously very, very important. Or whether the pedestrian is aware of the coming car, something that we do a lot with eye contact with human drivers. Not always. Another example, which is now still in the image domain, but 3D. Oops, didn't play. That's funny. Okay, doesn't matter. So this is actually annotation from the Waymo open data set, where you see the boxes in 3D for the objects in the scene. But this is still image-based. But then you can also do perception with the laser scanners. They're called LiDARs. In this case, you see again 3D boxes. These are annotations. These are not the results of actual systems. And it's from the very good new scene data set. But now moving to more complex tasks, you can do what is called 3D semantic occupancy, which is a fairly recent task, where in this case, just from the feed of your 6 surround cameras, you want to infer a sort of volumic understanding of the scene around the car. So what is empty, what is full, and you probably see the point. And it's not only whether it's full or empty, but also what is the nature of the object. So what you see at the bottom on the left is colored with the actual semantic, and on the right is only for the color. The coloring is only for the road users. And this is actually taken from an upcoming CVPR workshop this summer, which is called 3D Occupancy Challenge. And also this looking around the car, there is yet another task, which is motion forecasting. I already mentioned that in the driving stack, and this is work from the University of Cambridge. In this case, so first of all, it's what is called a top view or bird eye view perception. So everything is sort of inferred in a top view around your car, and the task here is to be able to predict in the future what is the likely position of each of the vehicles. And on the right, you see as well that it's very brief, especially when there is an intersection. This forecasting should be multimodal, because at some point in time, for some of the situation, there is a few likely outcomes of the future, whether the car in front is going to turn or not. And you see briefly here let's see, you have some spanning of the hypothesis here. So it's one of the challenges in machine learning, which is to predict multiple outputs, in particular when in the training data there is not such thing because there is a single feature. Now that we have illustrated these different typical perception tasks which are involved in driving assistance and automation, let's come back to some of the challenges. So one of the big challenges is the fact that, especially for passenger cars, is the diversity of the conditions in which the system is deployed. So there are different so-called domains, and in terms of machine learning, it means different types of input distributions. There are rare events, perturbations. So I'm just showing examples here. So here, these are different conditions, either due to the different lighting condition or weather. So on the left, you see rain at night. In the middle, you see heavy fog. It's hard in the distance to know whether there is an actual obstacle of some sort. It's so heavy. On the right, you see also different types of conditions which are associated to different locations in the world, different types or styles of driving. And obviously, it contributes to the complexity and to the challenge of the robustness and reliability of these systems. Other examples, which are more related to perturbations which are maybe transient. You are still in your zone of comfort. You are driving, you know how to drive on the highway in the Silicon Valley, but unfortunately, it's still difficult just with cameras not to be blinded by the sun glare. This is the example you see with an actual Tesla car having difficulty because of the sun glare, and you see that the driver is struggling a bit to counter the decision of the car. What you see on the right, top right, is another example where when you have your cameras quite low mounted on the car and externally, then they get soiled. And this is the typical kind of things you get, and obviously the perception is not good. And at the bottom, what I was illustrating are sort of corner cases or rare instances of things. I mean, as humans, we understand that right away. We see, a bike at the back of a car. We see a truck with cars, or we see a guy, unfortunately, falling down, a cyclist on the pedestrian crossing. I mean, it's not very hard to decipher, but it's very rare from the machine learning perspective. One way to sort of attack all these challenges, it's not the only way, but one way which is quite widespread is to use multiple types of sensors. They have complementary properties. In particular, this is the typical here, what you see, the typical suite of sensors that you can put on a car. The ultrasonic sensors, which are for really near-field parking functions. They do beep-beep when you reverse. You can have also radars at different ranges. Obviously, cameras. We love that. Computer vision people. They can be fisheye cameras, pinhole cameras, and also we have these laser scanners that are very, very useful. I already showed cameras and point clouds in my previous slides about typical tasks involved in perception. I just wanted to show another one which we love in my team, which is radar. So radar, it is interesting, not because it's easy to read, at least for the human eye, but because it has very interesting information here. You see, so radar signal is essentially a big 3D tensor or volume of energy that is sort of showed here into different planes. It essentially tells you what is the reflection at a given distance in a given direction. And it also gives you the relative speed of the object. And if you have annotated data, which we have done and released a data set about, then you can, out of this quite complex signal, you can train essentially a neural network which looks at these different 2D views of the 3D input tensor. In that case, it was a convolutional network which was trained in order to actually precisely segment what are the road users. This is what you see on the right in two views. Actually, the green blob is an actual cyclist, and the red one is a pedestrian. So, and I forgot to say that when I mentioned complementarity, the radar is is really achieves whatever the weather condition, which is not so true for LiDAR. They can be obfuscated by heavy rain or fog, etc., but they are quite robust. And the camera, which is fantastic to read things, to understand everything, unless you don't see anymore. So they have obvious complementarities. All right, another topic which I find is I think is very promising. Many of you have heard about self-supervised learning. Actually, it's a big thing when it comes to these large language models that everyone is aware of. So the ability to learn from data without any human annotation. Well, it's something which is quite and very useful when it comes to also to driving automation. So we have been exploring in my team several aspects. So I'm not going to explain too much these two works. Actually, the one on the right already appeared on the slide of Joseph this morning. It's the work of Antonin, who is at the back there of the room, sweating. And the idea here is that because you can leverage when you have several sensors, at least at train time, you can leverage the fact that there are lines. So you have a point cloud from the LiDAR, you have the images from the cameras, and you can geometrically register them, and you can pass from one modality to another some information and distill knowledge, and even build what are called pretext tasks to learn automatically representation out of these two modalities without any annotation. And then later you can specialize that with some training, some supervision, or not, in this case for point cloud or image semantic segmentation. I have two more examples of this. Same thing. So this is a follow-up work of Antonin and Joseph and colleagues at Velo.ai, where effectively what we leverage here is actually not only LiDAR and cameras, but also what comes with language. So now you have, these days you have these off-the-shelf, extremely powerful so-called visual language models, which have been trained such that you can essentially map both images and text in the same the same abstract yet numerical space where things close together are related. And so in this work, we actually, but we don't have that for point cloud. So the idea here is to go to leverage these text and image representations and to distill them in 3D. In the point cloud, and in this case, we did that while designing a model to actually deliver the following task, which is, I already mentioned it, which is 3D semantic occupancy. And you see on the right some examples of what you can do. So at the end of the day, from the cameras, you end up with an actual 3D volume around the car, and for each cell of this volume, you have some what we call features or representations, which are essentially vectors. And these vectors are very rich, and in particular, they also contain, so they do contain information about whether the voxel is empty or not, but also what is the semantics of the voxel. So which this allows to do what is called, well, that's good then, what we call a zero-shot semantic segmentation. So you can just say, I want to see all these classes and just look at these features without any further training, and you get some decent segmentation. Thanks to the same property, which is the sort of knowledge embedded in the 3D features from this image text line model, we can also search directly by prompting. Look in this scene. Look for I think in this case it was a zebra crossing, and it just pops up out of the 3D grid without any training. And we have another sort of parallel work in my team, which was actually doing a similar thing, but sort of the other way around. The idea here is to be able, in the previous work that I just showed, is to use only at runtime cameras. In this case, we use the LiDAR, and we are able to distill these very rich image text features onto the point cloud, such that we can directly analyze the point cloud of a LiDAR, an automotive LiDAR here. And in this case, you see sort of a heat mapping on the point cloud related to some classes. So in particular on the right, it's pedestrians. On another example here, cars on the left or pole on the right. And again, it pops up without any specific training. Of course, the people who train the large image text models, they have trained a lot and they have been doing that at large scale, so we leverage their what they did. Another important thing that people don't necessarily realize is that machine learning can be deliver very strong performance, but a neural network is not very good at assessing itself in terms of confidence or uncertainty. And being able to do that in a good way is very important to train better model, but also to validate them, and of course, at the end of the day, to have more reliable systems on roads. And again, it's difficult because it's well known that it's hard to know what, for the network to know what it doesn't know. And also the output can be very wrong and very confident at the same time. So one illustration of that, which is fairly well known, is that you can, which is called an adversarial attack, you can take a very good system able to recognize the panda here, and you can work out a very subtle modification which is not visible to the naked eye, and the same system tells you, oh, now it's a gibbon, and being as confident, like 90% confidence. So it's a bit scary when you put that in a car. So people used to say that deep learning or neural networks are brittle. Well, it's one aspect of it. So one of the things that we have been exploring in my team and other people as well is to have a sort of a safety or a guardrail, which is another model on top of it, which observes the main model. So in this case, at train time, you have the auxiliary model. So in this case, say you have this task of semantic segmentation in images. So the main model predict a semantic label at each pixel. And now you train another model which essentially look at the internal features of your main model, and is trained to detect a failure or what is called an out-of-distribution input, or something which is likely to be wrong, and then you can leverage that for many applications, including raising alerts in your driving systems. In this case, and you can, if you think in terms of even for end-to-end driving, the same philosophy or the same approach can be used to train an observer, which at some point for a specific input is going to say the decision of the system is going to be a failure, so you'd better take over. Another interesting and very challenging aspect of machine learning, in particular for safety critical systems, in particular driving systems, is their explainability. So again, it's a sort of common wisdom to say that neural networks and machine learning models are black boxes. It means essentially that they are very large and complex functions which have been trained from data with millions and now billions and now even hundreds of billions of parameters, and explaining what each parameter is doing for a given input in order to explain the output is essentially very difficult, if not possible at all. And one way to approach this sort of interpretability of a model is to build what are called counterfactual examples. So the idea is that it's the what-if question. So if I have a scene with like in this case, it's for a driving system, it looks at a scene through a camera and decides to move forward or to stop, etc. And you want to know, to understand why your system is taking certain decision. So the counterfactual explanation is to try modification, to find modification in your input scene, which are plausible, likely to happen in the real world, which are able to make the decision change. So in this case, you see on the left, it's a real scene, it's a real driving system saying it should stop, And now we have on the right, I'm not going to explain how we do that, by the way, maybe later. We have this slightly changed scene, which makes the system change the decision from stop to move forward. And if you look carefully, I'm not so sure you can see that yes, you can. There are the few differences are there. So the braking lights of the cars are switched off to some extent, and the traffic lights go from red to green, which makes sense. So what it means is that the system has taken the original decision to stop for apparently good reasons, at least understandable reasons. So that's very important. So this is an early work we had last year at ECCV. The constraint we had is that we were only able to manipulate the scene without changing the layout, but only the sort of the texture or the color. That's why this example works fine with green to red or vice versa, or switching off the braking lights. But the flexibility we have is a bit limited. So in a more recent work that we are going to present in June at CVPR, is extending the same idea, but now we can change the structure of the scene. So it's exactly the same thing, the same system. On the left, you have a real image. On the right, you see an image which has been manipulated automatically by the method in order to make sure that the autonomous driving system, which looks at this scene, decide to go from the decision of moving forward to the one of stopping. And again, here the interpretation is pretty clear. It has put the front car closer. So again, it's quite reassuring. The system is doing sensible things. Okay, so let's see. And in order to do that, you need to manipulate a real scene. That's difficult. So we used, for that, we used this generative model from last year, which is called BlobGAN, which is able to generate scenes with some ability to manipulate the scene in terms of where are the objects, at which distance, which one is in front of the other one, etc. The main objective here in this type of work is to generate scenes, right? Now, the additional difficulty we have is that we want to use that in order to manipulate a real scene. So the system we put together goes as follows. We start from a real scene. We have a way, it's called inversion. We have a way to take this real scene and to turn it into one of these abstract, or not so abstract, but blob-based representation from this other work I just mentioned, which allows to some extent to regenerate the same scene. So essentially we have embedded the real scene into this representation space from which we know how to decode into a scene, and then we are going to manipulate this representation, move the blobs, etc. When I say we are going, it's just automatic, right? And you see the result, and then we decode or we generate the new manipulated scene. In this case, you see that many things have stayed the same, the layout, the trees, the road, but one vehicle now is closer. So this is how we did it. Some examples here. You see at the top the actual real scenes with the decision of the driving system, move forward or doesn't turn left, etc. And you see at the bottom how we flipped the decision by the manipulation of the scene. So first column, the object, the closest car is closer now, so it stops. Second example, it has somehow changed how busy is the road, so we can turn left. And on the right example, the car which is in front on the right is closer now and prevents the system from turning right. So again, it all makes sense. But this is qualitative analysis when we say it makes sense for the human. So we tried something difficult in this paper is how to quantitatively assess the power of these I'm going to skip that, of these counterfactual examples. And to do that, we put together a small user experiment. And the idea here is that for some people, we showed them a number of these counterexamples, and we want to know whether it has helped them to understand how the driving system works. And to test that, then we asked these guys and other people who didn't get this to see whether they could predict the decision of the automatic system on new scenes. And this is what we got. So there is a very significant difference. This is the replication part of this table. It means that the people who have been sort of trained, it's a bit funny, we are training humans to understand the machine now, as opposed to the opposite. So for the people who have been trained using the counterfactual examples, they were way better at predicting the next decision of the system. And we did another thing, because these counterfactual explanations are here to understand the system, and in particular to detect biases which are not good. So what we did, we trained a bad driving system with a very strong biases that the user were not aware of. And we wanted to see actually the bias is as follow. The driving system couldn't turn right, well, we're saying that it can turn right even if they had, how is it called? Yeah, so the turning right was also influenced by the fact that you have cars on the left, which is obviously wrong, so it was purposely put in the training of the driving system, and we wanted the people to detect or not, or to understand or not this bias, and it turns out, many of the people who were trained saw the bias, and not the other people at all. All right. For sake of time, I'm going to skip that and move directly to the takeaways. Anyway, the slides will be available. So, autonomous driving, assisted driving, etc. I think it's fair to say that it's a reality now, even if many people are not completely aware of that, it is a reality because of extremely important progress in terms of sensors, but also in terms of machine learning, obviously, and artificial intelligence, and also in terms of the hardware that we can put in the cars for the compute. And it goes from passenger cars, and I mentioned these new cars, I mentioned the Mercedes, it's also true for Honda, having level 3 systems on the highway, in traffic jams, but it goes all the way to very specific other, even niche markets, which are important. But I think probably some people were a bit optimistic when they were saying that it was around the corner to have autonomous driving cars everywhere in towns. So the challenges we have, we are still banging our heads, are related to all this data that we need, not only for training, but even worse, for testing our systems. So massive amount of data, usually annotated. This is not scalable. The current system, they are still lacking really reliability, explainability, and in order to be trusted completely. And the other thing which is important, not only for autonomous driving, but for all the high-risk systems with AI, at least in Europe, is that there is this new AI Act coming up, which might change the game, and we really have to be careful. Well, careful. We have to accompany that and to see how to be compliant. And this is for very good reason. And I will finish with new venues. I think because of also the price, the safety which is involved, etc., there is a lot to do in terms of training and validating all these systems, or part of them, virtually, meaning in simulation. So this is a very big trend that you see in the new mobility and autonomous mobility industry. I already mentioned self-supervised learning across modality, and I think it's just starting. So it's again how to leverage vast amount of unannotated data, whether it's actually driving data or not. And of course, related to that, there are now these incredible so-called foundation models, whether it's visual language models or even just language models, which are changing the face of AI at large, but in particular robotics. It was alluded to this morning, and also autonomous driving, in particular in order to do to recognize things without any training data. It's called zero shot, or to help with the annotation, to help with delivering explanation in text, or also to test things. And with that, I'm going to stop with this image, just to see one way to use these models. This is from Midjourney. So you take a real scene, you ask to put a baby on this at this place, and you get this image. And you can easily imagine how these things can be useful for training and even better for testing our systems at scale automatically. So lots of exciting venues. And I will stop here with all the people in my team. And thank you for your attention and your patience in this world. Thank you.
So, time for questions. Thank you very much, Patrick, for exciting talk. Holger, please.
Mike is coming.
So thank you very much. That was super insightful. I hope you'll forgive me the question, but of course you're enthusiastic. I think you should be. To be perfectly honest, I would fully expect that at least you and I and most of the people in this room will live to see the day where autonomous driving level 5 becomes a reality, right? I really believe that this will happen. But let me ask you this. How long do you think we're really away from having level 4 without geofencing or even level 5 in European cities like Prague? In, let's say, more than just a few experimental cars, but in something that you and I can simply just, hop into. How long away would you think?
All the people who have answered this question in the past decade got it wrong. So I'm going to be a bit conservative here. I'm not sure it will happen in my lifetime for passenger cars. I wouldn't bet on that. I mean, we might be surprised. Things which have happened with natural language processing recently has also taken off guard in the other way some predictions. I think one of them, again, for really passenger cars not being geofenced, imagine that we have really solved all the reliability, the robustness, etc. One of the issues here is that it's not only about the autonomous system, it's about the other road users as well. So even if all the cars, they were autonomous, it's not only about cars. You have pedestrians, and hopefully the ratio even increases. So pedestrians, cyclists, etc. So, and in some big cities, the mixing is so dense and so packed. I think it's very difficult. Each day, so I walk to work in Paris. I look at the traffic with my Valeo eye, and I think it's challenging. So I don't know. What I know for sure, what I believe more into the fact that in the coming years we will see for logistics and for robotic taxis and for shuttles, big time. Level 4 or 5 for passenger cars. I mean, we'll see, but I wouldn't. I mean, not in this decade. I don't think. But if you listen to some of the vocal people in the industry, not so much. Actually, if you listen to the car manufacturers, they have extremely toned down these announcements. As opposed to startups.
Except for Tesla, of course, right?
That's true. That's true. That's interesting, actually. Yes.
So we have actually on Slido we have someone asking to have more time for questions. So let's have a few more questions.
That's a good sign.
And there is a related question to this. Another way to think about the measure of performance of autonomous driving is to compare the autonomous car to people. And I think here the person is asking, well, is there, where we are in terms of, say, fatalities per kilometer? Like, are we getting, is the autonomous driving comparable, or when will it be comparable to, say, humans doing X fatalities per kilometers in the autonomous car?
That's a very difficult one. First of all, because to get the numbers at scale, you really need to get the reports from the people who are really deploying at scale. Actually, it's interesting to look at the Waymo safety report. Extremely good read. They communicate about the numbers, but even the way you compute the numbers is difficult because there are no metrics. And on top of that, obviously, if things go wrong, you disengage the system. So so what they measure is for now it's not. Well, fortunately, it's not the number of fatalities which are caused by Cruise or Waymo. There are a few, I think. But what is the frequency of the disengagement compared to over the kilometers? But then you should know what are the type of kilometers that you have been driven. I mean, if you are doing that or in the Silicon Valley every day, the boring road there. I mean, it's maybe not representative in terms of statistics. So I would say, in a sense, it's way safer. I mean, than the human driver. I mean, it doesn't get drunk, it doesn't fall asleep, etc. But I mean, getting a fair comparison. Another thing which is interesting is probably, well, this is interesting but difficult to do. Another thing which is interesting is to have the driving system in a shadow mode. So you are still driving as a human, and you see the system is doing. But of course, then the system is not accessing the closed loop of the driving, but at least you can compare things and record what is the driving of the human and what would be the driving of your system. And actually, you can even use that to train with imitation learning and end-to-end driving systems. But so there are different ways to accommodate this, but it's difficult to assess the actual level of safety.
Yeah. Any more questions from the audience? Maybe let's ask one more.
What is the current level of automation of truck driving on highways in Europe or worldwide? Is there like some deployment of very autonomous trucks?
Well, I confess I don't have these numbers, but I mean I read a lot about even the media on these things, and I'm not aware of actual. The level of authorizations that we have already, I mentioned in San Francisco, for instance, for robotaxis. I'm not aware of any bold announcement about trucks being allowed, even experimentally. So it may be the case. I confess my lack of knowledge here, but the fact that it hasn't, I haven't heard about it is probably a sign that there is not much. There is, in the US in particular, there is a very visible and promising startup which is called Waabi, which has been started by Raquel Urtasun, which is focusing on that. So if it's probably one of the places to look at to have fresh news on the state of affairs for the trucks. There are other places, of course.
So maybe let's have one last question for Patrick, to take advantage of the expertise we have here from Paris. Anyone? Any more questions? Holger, one more, please. Yes, please, one last question.
So I'm just curious whether you would share my assessment that long before we will ever have fully autonomous driving, we should have fully autonomous flying of commercial aircraft, right? First cargo and then passengers, because I would think that, you know, the way we do aviation is so much cleaner, so much more regulated, so much more technologically supported. So all these things that you said about the inner cities, all the nasty things that can happen to you, right? All the users of the space, that's really not such a big deal with airspace, right? Would you agree with that, or do you see this differently?
Actually, I was even about to say, isn't it already the case? I think a plane can do most of the stuff automatically, right? But of course, I agree. I'm not at all a specialist in aviation, but indeed, the domain of operation is so different. So there are many things that you don't have to care about at the same time. The way they have, I mean, the lifespan of a plane, it's much more than it's 50 years, right? And the design cycle is much longer. So even worse for space, but for plane. So which means probably as well that you have some of the technologies which are quite ancient, they're quite old. So you know, probably they cannot enjoy the latest whatever GPU, etc. So they have their own challenges, and I think certification is definitely the harshest.
Okay, let's thank Patrick again for a wonderful presentation. Thank you, Patrick. And we are moving on to the next exciting point of an agenda. So we have a panel discussion about the development of AI in Europe. Let me invite Vít Dočkal, who is the lead for strategic project here at CIIRC, who will moderate and lead the discussion on how to best develop the AI ecosystem in Europe. And Vít will introduce the speakers, the panelists for the panel. Vít, please. It's exciting to have such esteemed people here.
Thank you very much, Jožko. I've got a headset. It's a lovely day today, yeah. Let me welcome here on the stage Professor Holger Roos again, the chair of the board of directors of CLAIR and Humboldt professor at RWTH Aachen. Yeah, okay, please. Oh, whatever you want to say, that's okay. Then Patrick, can you please come again? Patrick, welcome again. Valeo, Vice President for AI. Then let me please introduce Professor Jan Hajic, Professor at Institute of Formal and Applied Linguistics at Charles University in Prague. Welcome. Tomáš Mikolov, the head of Foundational AI Group at CIIRC CTU. Hi again. And last but not least, Professor Michal Pichouček, the director of the AI Center at the Faculty of Electrical Engineering CTU. Welcome. So, gentlemen, we have several tricky questions for you. The topic is how to best develop the AI ecosystem in Europe. So let me please start with the first one and imagine that we are defining the development on the technology readiness level scale. So can we please put the question there? So consider defining, you can see also there, the development of the AI ecosystem in Europe on the technology readiness level. What does it mean? Do we have basic principles adopted, or is it a proof of concept, or pilot validation, or the system is completed already? So please, Michal, can we start here?
Thank you for the question, and also thank you for inviting me to the panel. It's a great honor. I think that the question is very interesting, but my perspective is that it's very difficult to talk about where we are as a Europe in this TRL scale, because I'm convinced that in each of the phases of technological readiness, Europe has results and a great piece of work to demonstrate. My only worry is that it's just not enough in volume and size and scale. So I think I would much rather than commenting that there is one piece of TRL missing or underdeveloped, I would say that the amount of results is, and I would say it's getting less competitive with a higher level of the TRL. I think that at the level of basic research, we have in Europe a substantially competitive research results with America, China. But when it comes to AI deployment, AI economy as such, AI businesses, AI startups, Europe is lagging behind in comparison per capita, per GDP of the country.
Okay, thank you very much, Tomáš. What is your opinion? Do we have the fully operational ecosystem of AI in Europe?
Well, can you hear me?
Yes.
Okay. Well, obviously, I don't think that we are doing enough. I agree that we are pretty much as Europe underdeveloped, because I don't actually know what is the TRL scale, but just comparing the history of the AI successes in Europe and say in the US or in China, if we look at a very basic metric like basically the money, who is making money out of AI, because it's a technology as like cars or planes or whatever, well, we are not the ones who are making the money, right? Because it's mostly the US companies that have been investing very heavily into this. It was with the state support as well. Then there's China that was investing very heavily, like 10 years ago, into AI. And there was this deep learning revolution. I remember that's about 10 years ago. China did recognize it as a priority. They did invest heavily into capturing talent, keeping data, people in their ecosystem, and that did allow the creation or even scaling up of the companies like Alibaba and Baidu and now we have TikTok from ByteDance and so on. So I think that they have been doing much better in like growing their ecosystem, where actually US is the #1, China I would say is #2 because of this. Europe, I don't know where I would even put Europe, because basically it doesn't really matter on the AI map. We don't have the companies that would be of the scale of these AI companies in the US or in China, like we are maybe like 100 times smaller or something like this. It's basically insignificant. So I think that just talking about the past, we were not doing great, and it's not because we don't have enough people. There's like 500 million of people living in Europe. It's not that we have that terrible education compared to the others. We have like plenty of good scientists that are coming out of the universities. I think that there must be some more fundamental reasons why we are somehow unable to create this big tech sector in Europe. Because again, like US does have it, China was able to grow it, but Europe only maybe is able to comment on it, but somehow we just don't know what to do with it. So just talking about the past, I think that this is enough. Maybe later in the discussion we can talk about the future, what we can change, so that we actually identify what are the main points that we can be doing, so that the future would look finally better, and that we would also grow this sector that is terribly missing at this moment in the European economy.
Thank you very much. Patrick, what do you think about the European AI ecosystem? Is it a well-functioning system?
Actually, the way I understood the question, there are two ways. So are we ready? I mean, are we talking about the readiness of the technology or of the ecosystem itself?
The ecosystem itself, yeah.
Just one word on the technology. I think we are all sharing. Yeah. I mean, the technology is quite transversal, and particularly also because it's been quite open. Maybe surprisingly, AI is extremely open still, and that's good. And and for some of the brand new technologies or out of the research labs, they can be deployed almost immediately, which is also extremely striking. I think in terms of technology, when it comes to highly safety critical systems, that's another story. When it comes to the ecosystem, I think it's all has been said. I mean, Europe is lagging badly, struggling, but I mean we are recovering. But so we have things missing, including the strength of the investments or the size of some of the tech companies, etc. But I was showing these examples of brand new robotaxis at the beginning of my talk. So the examples, they were coming from the US, and I mentioned it wasn't on the slide, but I mentioned Baidu. So China, obviously, these are the two main contenders. There is no technical reason for not being part of this competition, but as a matter of fact, we are lagging.
Okay, thank you very much. Holger, you did very much for the European AI ecosystem. Are you satisfied?
No, I'm worried. I'm quite worried, right? I mean, Tomasz said this quite nicely. You know, I think the Commission can say all they want in terms of, you know, a very healthy ambition, and I for one, am glad that they have this ambition. I do too. But the instruments that are currently being brought to the task are not going to succeed in getting anywhere close to that, to realizing that ambition, right? So we are currently, I would say, a distant third, probably, right? And if we take Britain out of the equation, they sort of taken themselves out of the European equation, sadly, a little bit, right? We hope, of course, that this will all change again. Then it's looking even worse, because let's be very honest, a lot of the Europe's top AI expertise sits in Britain, right? And so we better get our act together. I think in terms of basic research and talent, we're still doing quite well. But I believe even that is seriously threatened in areas such as large language models and generative AI, right? I do not see how on this continent we can succeed doing cutting-edge research anywhere in industry or in academia, in fact, that is not going to become totally dependent on handouts and access, maybe in exchange for data, maybe increasingly in exchange of substantial amounts of money by those that have the capacity, namely these US-based companies, right? And I have nothing against the US-based companies. They're great, right? We should be working with them, but we should working with them, you know, on par at eye level. And I think it's good for them too if we don't just produce the talent here in Europe, but also have the capability to do the same kind of research, the same kind of cutting-edge AI development that they do, not aimed at products, but aimed at capabilities out in public institutions. I think that's very, very important. And Europe could play a leading role in forming a coalition of the willing, a global coalition of the willing towards that end. We'll talk about how to improve the situation later, so I'll stop on this right now, but I will say this. If the Commission seriously believes, as it seems to, that doing regulation and having a nice ambition, a very clear-eyed ambition, and then spreading some funding pretty thinly, mostly through Digital Europe and Horizon Europe, and pull anything real in AI, I think they need to wake up quite seriously. That's not the way this works, right? We need an investment that's about 50 times as high as what's currently being invested. That will take a massive effort, not just by the Union, but also by the member states. And we better get our act together with our Swiss and Norwegian and British friends, because they should be part of that too, right? In order to form a critical mass of AI research capabilities. And that will make sure that the American companies that currently hire many of our best and brightest will continue having access to that kind of talent. Because if we get to the point where we can't train that talent any longer, because we don't have the infrastructure to do the cutting edge research, right, they will suffer too. And nobody wants that, right? So strong AI in public institutions and strong AI in industry in Europe and elsewhere, that is the situation we should drive towards. Now, one last reflection from me. You speak of TRLs. One thing that's different between AI and I think many other technology areas is that the path from low TRLs to high TRLs can be extremely rapid. And I think politicians and decision makers don't understand that. They don't understand that the way to be brilliant in AI is to do what DeepMind is doing too, which is to massively invest into low TRL research and then hope and of course support that some of this bubbles up the chain, and that bubbling up can happen extremely quickly, as we've seen in the case of OpenAI.
Thank you very much, Holger. Professor Hajc, you are very active in the European ecosystem with your team. How do you see it?
So, good afternoon, everybody. So it's very hard to say anything new after we have listened to these four people here who know a lot about it. I also have to look at it from my own subfield perspective, which is language technology, and that's something I understand. And again, we have to distinguish between what has been already said between the preparatory level of applications and the ecosystem itself. So a lot has been said that we have applications which are very well done, which go fast from low TRLs to high, but what we don't have is the ecosystem. And from my point of view, from the language technology point of view, it's actually even worse. It's getting worse, because I remember when we first get to European projects in 2006, there was a lot of support. There was a call every half a year almost. For language technology. Now there is one in 4 years at best, right? So exactly at the time when language models and anything related to language gets attention, and rightly so. So just one example. I mean, we are working on large language models in an EU project which we are coordinating, and we got 6 million euros to build large language models for all European languages. I mean, we will do our best, obviously, but without getting the hardware, the legal stuff, the data which we are actually getting from the US, sorry, Europe, we won't be able to do anything useful, I think. Right. I mean, again, we will do our best, but this is just a picture how it works. And this was not a targeted call. We got into a data call with our own idea that it would be useful, 2 years ago, to actually build a large language model.
Yeah, it's many times in European calls, it's miracles for 10 million euros.
So if I might say one more thing, because this kind of thing, not you, but what you just said makes me really upset, because as you know very well, because you've helped us, we made the point to the European Commission 4 years ago that there are 2 areas that need special support, right? Not just them, but the other ones at least got a bit more support. And the 2 areas are of extreme importance for Europe, right? One is robotics, and it took them a while, but they got sort of their act together a little bit. And the other is language technology. So before all of this happens, long before Claire officially gave input, and others did too, right? To tell the Commission, this is important, this needs to happen. Had they acted on it now, the situation would not be quite as grim. And now they're acting on it with 6 million. I mean, you are very polite about this, so let me be a little bit more outspoken about it. I think this is an insult. I honestly think it's an insult to this community, to your community, and it's an insult to all those who care about the success of AI in Europe, really. There must be people in the Commission that really, really need to sit down and do their homework, and then either not invest at all and say we leave this to the Americans, fine, right? That would be very regrettable, but it is a choice. Or to actually make sure that the public money is spent reasonably. But, you know, I mean, I'm glad that you got the 6 million, but you said it yourself. That's not the order in which you need to invest in order to have any effect, right?
So I hear your concerns. Maybe we go to another question. We have 4 questions, 4 main questions. We still have some 40 minutes, 36 minutes. So I see that we are not that optimistic regarding the ecosystem itself. So how to change it? You know, we need multi-stakeholder collaboration, you know. So which of these stakeholders are driving force now? Which should be more active? You know, like academia, industry, public authorities, or can AI help us itself? I would start with Professor Hajc.
Well, I agree with Holger that the Commission is sort of is trying to do something, right? I mean, they have some kind of vision, but the support is not here. National states, it depends. I know there is a lot of good stuff going on in Germany, in language at least, again, but also otherwise. But here we have heard that yesterday, nothing, essentially nothing, right? Industry, I don't know. But again, this is partly the last question. I do not want to alienate any possible investors. But whenever we talk about someone like seriously, you know, how can we make the technology that we are developing, which is often the best in the world because we have these competitions on academia and so on. You know, what can we do with it? But maybe the money might be somewhere, I mean, even reasonable money, but the ecosystem, as we talked about last question, is not there. And I don't know whether the industry wants to push it or the investors should push it or whether governments, maybe I would rather not, I mean, we are trying to do our best, but of course academia doesn't have all the skills to actually push it all the way to big success. Maybe some people, not everybody. We need an ecosystem like in the Silicon Valley that will actually be able to do it. And one thing which is missing is the legal support. I mean, we still, after all these big changes in the copyright directive, and that's again in my field in language technology, we got something like Articles 3 and 4. But for industry, they are useless, and we are still behind the US and Canada, Japan, and Britain. So there is no way that even with the new law, we can cooperate with industry efficiently because we still have to think about it, that they cannot take the data from us, they have to do it otherwise. And with the AI Act, it will get even worse, actually. So legal support, that should be done at the EU level. We should push from academia, of course, that we want to see our results working. And then the rest, I don't know.
Okay, thank you very much. Holger, your opinion?
Yeah, I'm actually seeing a question coming in on Slido.
Oh, yeah,
so
yeah.
I think this is highly related. So if I may, I will take this one.
Yeah. I don't know if everyone can see it, so maybe if you can
So the
read
question,
it
I can read it. It says, do you think it is better for the EU to invest, subsidize, or not to do, and let the companies with minimal regulations and laissez-faire do their thing, right? And I have a very clear and very strong opinion on that. I think if we do the latter, if we let the companies with minimal regulation and laissez-faire do their thing, we are all in for big trouble. I mean, even the companies themselves are calling for some sort of oversight, for some sort of reasonable guardrails. So I think this must happen. And with all the weaknesses that the AI Act has, and I agree with that, again, Claire gave a lot of input in this, and some of it was considered, and a lot of it, unfortunately, not, right? I do think regulation is part of the solution here, but it is not the solution itself, right? And I personally think what's desperately needed is a big public investment. And the public investment should be done as it was in Canada, which did that very, very well, into basic research in AI. And my suspicion is that if, and my hope is indeed, if this is done and done in the right way and swiftly and at the right scale, industry, especially the the small medium enterprise-based business that we have in many areas of Europe, right, will benefit tremendously from that. I mean, look at the Montreal ecosystem. It's one of the best AI ecosystems in the world, right? And why is that? It's not because the Canadian government said, let's have the companies do whatever they want and give them a lot of money to do it. No, it's because they created MILA. They created the Public Research Institute, right? And so I think we need to do something like this in Europe. We need to invest into AI that is done at public institutions for the public benefit by publicly funded researchers with full transparency, and then give companies access to that. And yes, also work with the big companies that do their own thing behind closed doors. That's totally fine. It's not that we don't want them. We want to work with them at eye level, and in order to do that, a big public investment is absolutely needed. Now, public investment also has one big advantage, and that is it can create a stage upon which actually certain actors in Europe that otherwise might not be that competitive have a chance to increase their competitiveness. And I think that would be a very, very good thing.
Okay, thank you very much. What about stakeholders from industry? So, Patrick, your opinion. Can we put the question back there?
So regarding the stakeholders, maybe I can say something about the strong one in Europe. I think the academia is just really fantastic. I think we have nothing to be ashamed about in Europe when it comes to the public research and the academia. I mean, CIIRC is an excellent example here. I mean, in the UK, in Switzerland, in Germany, in France, I mean, we have extremely strong, it's funny to say that, being with the industry, but I'm also from this world, but I think we have an extremely strong education system, a super strong public research system, despite the limitation in some countries at least, of the funding. So I think we can even be proud of that, but it's very fragile. It's clearly jeopardized by the companies who are which are very happy to get all these bright people, but that's part of the game. So at least let's make sure that we don't have only a grim vision. I think the European academia in AI, in machine learning, in computer science at large is extremely strong. And if I can point a weak stakeholder in the ecosystem, it has been mentioned already, but I think the way we do investment, I'm not talking about the public investment here, there is a lot to say about it, but the venture capitalists, I think the ecosystem in Europe is way weaker. Maybe I have also, having the French viewpoint probably makes me see it as even weaker. But I have this example, so for the people doing AI, I guess all of them, they know Hugging Faces, this startup, which is a very interesting company. I mean, so everyone says, and it's because of funding, that it's an American company. It's been essentially funded by 3 French guys. And the way it works with the VCs and all this investment is that it's very hard to compete with the investment ecosystem in the US and presumably the same in China. So I think we probably have to think about the way VC work in Europe.
Thank you very much. So, Tomáš, do you think that academic people could do more than they are doing now?
Well, of course, they can always do more, but I would maybe try to answer the original question about what can we all together, not just the academic people, but all together do so that the AI ecosystem would be better in Europe in the future. I think that it's of course a difficult question, but it's certainly good to try to look abroad who did succeed before us and maybe try to copy some things or some decisions. Again, I already mentioned Silicon Valley that has been successful. That's obviously the number one. Then there's this Chinese ecosystem, which of course people are somewhat allergic to China, whatever, for political reasons. But I think that they did pretty well at protecting their own market. And creating their own ecosystem that resulted now in these big companies that I already mentioned before. I think it was mentioned by Holger, this keyword like critical mass, and I think that that is a big part of the question. If we want to develop this AI ecosystem without just copying some superficial patterns from abroad, and while trying to avoid building some Potemkin's villages that look like Silicon Valley, but they don't really function, then I think that the main thing, number one for me, is the money. You need to create an AI ecosystem that creates its own fuel, so that kind of like chain reaction, you know, like it has to grow by itself. It cannot be just based on the public money. Public money can be used to create this critical mass in the beginning, so that the chain reaction starts. But then it has to sustain itself, and I think that that's exactly what I've seen in Silicon Valley. Like once you have this critical mass of companies and people and capital all together, then it's great, because you just have some cool idea, you discuss with people, and people know some other people, they connect you with some other guys, and then suddenly in a year you have a functioning prototype of some cool product, you can start selling it, and it's all connected, it's great. Here in Europe, I know that there are some cities that have been investing into this startup areas before, like Paris and Berlin and London and so on. I'm just not exactly sure whether this is enough, because it's still somewhat fragmented, and if each country in Europe develops this on its own, maybe it's much harder than if we would try to in some way unite, so that we would try to act together as Europe. It was what I mentioned before, that maybe Britain is not even part of EU now, which I think is a big miss, as it was already mentioned by Holger, because that's going against this goal that I'm saying. It's fragmenting us further. So if we want to reach this critical mass, so that we would not create just some groups that just use the public funding, and it's basically the science for science, so that we publish papers and so on, but it doesn't actually like have any value in the end, because the money doesn't come. So I think that we really need to create this critical mass that creates its own fuel, so that it grows based on its own results. And again, the keyword number one for me is the money. We need the money in AI, and once the AI starts generating money, then it's all great. If we are in a situation that we still need to put some external funding into it and trying to kind of like keep it alive externally, I think that's the bad situation that we are kind of like in many areas at the moment. So again, let's try to copy what worked abroad, and public funding is certainly part of it, but creating private sector that can actually do things on its own, that should be our ultimate goal.
Thank you very much. Michal, you were successful both in business and academic sector. Can you imagine what would be the price for such a center, you know?
So it's the worst to be the first entering, and also it's the worst to be the last entering, because all the smarts have been said already by my colleagues. I'll try to say I agree with Tomáš 100% that it's a multi-stake venture kind of supporting AI, no matter whether we accept it or not. And I agree with everybody who said that the European Commission, national states, including Czech state, are heavily under-investing AI, which is, on one hand, it's a lost opportunity, but on the other one, there is huge danger of being left behind and kind of become an AI-dependent country or AI-dependent region, that we as AI leaders need to do our best to kind of lead the society so that this doesn't happen. I agree with everybody. However, AI is expensive. It's getting more expensive. Supporting AI is more expensive than 10 years ago. It's more expensive than 5 years ago, because of the competition and because of all the other regions being able to pull much more money than Europe can. I think this is a big problem. Kind of replicating Canadian project at a time where they did that in the EU would have been much more doable than these days, because of the cost and competition. If you look into the stakeholders who are supporting AI economy, AI research, AI technology in the United States, by far the biggest chunk of money is coming from venture capital. This is the reason. The reason why US is so ahead of time is not the fact that US government and Department of Defense were funding startups like Google and Apple and others. They did. It was a kind of smart investment on behalf of the public, on behalf of the government, but that's not the reason. The reason is that there is a plentiful of venture capital. And the venture capital can kind of really follow follow the opportunities. It used to be gaming, it used to be crypto, now it's large language models. The venture capital is really supporting the trend in volumes and sizes and gravity that the European Commission cannot, and nation states cannot. So there is this massive economical disparity in the way how AI ecosystem can be supported between the US and the European countries that we just need to be cognizant about. At the same time, we are distant three. I will always count UK as a part of Europe because Brits are Europeans and as much as Norwegians are Europeans. So European region, including Swiss, including Israelis, in my perspective, we are distant three. Can we be number one? Just cannot, right? Does it mean that we shall not continue fighting for quality and excellence and good work in AI? Definitely not. So what is the objective then? So my own personal objective is not to compete with the US. My objective is to be a good citizen of a transatlantic European ecosystem, which is going to be the number one on the planet, will provide the most of freedom and the most of prosperity and wealth and support in research comparing to the other regions. I want to be part of this region. And each part of this transatlantic AI community can contribute differently, and there are different ways how countries and cities and regions and institutes can collaborate. We as scientists demonstrated that in research, it's actually very easy. Because we read best-in-class papers, irrespective if they come from China or from the United States, or from Britain, or from France, or from the Czech Republic. We do. In terms of governmental support, it's more tricky, because it cannot be easily sent between countries. But in terms of the venture capital, again, it's easier. Venture capital can flow between regions and is flowing between the regions. So I would say that European Commission and nation states, beside funding, research and building institutes like Mila, I agree with Tomáš, I agree with Holger 100%, they should also create the environment that is attractive to venture capital. That venture capital is coming here to Europe in big amounts and is the missing piece in the ecosystem that we just don't have, I mean to have.
Thank you very much. Actually, your answer goes very well with the next question, with the third one. Shall we speak about the European ecosystem itself? Or is it a subsystem of the global AI effort, where we just promote our interests? So maybe if you would like to go on, because or do you think you said everything?
Yeah. I guess being the last and the first, I took the privilege of answering both questions. That
because it goes very well with that. Yeah.
I'll comment to what other speakers have to say on.
Yeah. Okay. So who would like to react first? Maybe Tomáš. You also spent quite a good time in the United States and abroad.
Yeah. So should I be answering this question? This is on the panel, that there's just 9% of technology companies have its headquarters in EU, and so why are we talking about this European AI ecosystem? I think precisely because of this, because we should have much more of the presence of the technological companies in Europe. And again, I just keep repeating myself, but it's about the money. If we don't invest into very important part of basically economy, then we are going to lose the future. And I think that it has happened many times in the past when there were some monopolies from some parts of the world, either oil or steel or maybe airplanes, where some companies were just totally dominant. And it's never a good option to be locked in a situation where we are dependent on products that are coming from some foreign country. I think it happened with the recent European war, between Russia and Ukraine, that that we did see very clearly that being dependent on whatever that's coming from abroad is a security risk. That's number one. The second thing, again, we want to be successful in the future. We want to be rich and so on. And we are just giving up on competing in this technological sector. It's kind of like saying, okay, take our money and we are going to pay forever for operating systems and computers and search engines and social networks and now language models and emails and maps. And, it's a long list of services that we could be providing for ourselves that is based in part on scientific discoveries that were made by Europeans in Europe. And the products are often in part implemented by Europeans that are working for American companies, but it's totally unfair because we are just buying all this without any bright future that we will have this technology created by ourselves, that we would have companies that would have a headquarters in Europe that would be paying taxes in Europe. That's also a big part of the question. Again, it goes back to the money that I keep repeating. If we want to be rich, if we want to have the money in the future, if we want to have the jobs, then really we need to boost this big tech sector, because even if you look at the US stock market, you can see that from the last 15 years, most of the growth has been actually led by these big tech companies like Apple, Amazon, Facebook, Google, Microsoft, and so on. They did generate the wealth in the US.
I see Holger would like to react, or you're raising your hand, because I see that here is, in my opinion, you think that is one global environment for AI. You see a lot of ecosystems, let's say, that need to coexist somehow. Holger, what is your opinion? Sorry, Patrick, you will receive.
Yeah. Maybe if I can finish this, of course, you can just say that we are the world, and it's all fine that somebody gets richer and somebody gets poorer. But I don't think that this actually is the future that we would like to be. We don't want to be a technological colony. We don't want to be poorer. We want to, again, have the jobs. We want to have the money. I'm pretty sure of it. At least I do. And for that, we really need to have this technology here, and we want to have the people, the investments, the talent, and the bright future. Again, if we don't act now, then we are risking that we are going to lose the future.
Okay, thank you very much, Holger.
So there isn't much I'd like to add to this, just to re-emphasize a few points. I mean, Tomasz, you said this extremely well. For me, the key word here is technological sovereignty, right? And I think that matters greatly. I mean, of course, we could say, for instance, electrical cars. Tesla does this very well. So do, other manufacturers in the Far East. So why do we bother in Europe? Why should, Volkswagen and Skoda and so on bother with electric vehicles? Let's just have others do that. And we don't even do that, right? And that's just cars. AI, as I explained earlier today, is going to touch and transform absolutely everything, right? So if we miss the chance of having a major stake in that, much more than 9%, and we'll get back to that in a second, it is exactly as Tomasz said. We're then basically passing on the future. And we're saying, well, others will benefit from this more than we do, and we're going to have to pay. And if we have disagreement with the others, we may no longer be able to pay, but we might be cut off altogether. And that's not a future that I want for our kids and grandkids, right? That's not what we want. Secondly, I think AI is not a value-neutral technology, right? It's often presented that way, but AI has values pretty deeply built in. And in reality, there's certainly currently not one AI ecosystem in the world, but there's at least two. There is what you call the global ecosystem, and then there's the Chinese ecosystem, which is pretty encapsulated and separate from the rest, right? Mm-hmm. And why is that? Well, first of all, because China wants to nourish its own capabilities, and I'm with you, Tomasz, actually good for them, right? That's, it's not clear that it needs to be done in that extreme way, but certainly they're successful in it, very successful, right? But also because Chinese values, without passing judgment at all, are just very different from Western values. And that's probably good and to be celebrated, but do we want all of AI to be built just on one set of values? Absolutely not, right? I mean, our euro coins have national sites because, we believe that diversity is good for us. So we want diversity in the AI ecosystem as well, and that means that Europe should play a strong role in it, right? Much stronger than 9%. And the last thing I would say is that Of course, you succeeded wonderfully in provoking us here with the 9%, right? I would say in terms of talent production, as it currently is, we're doing way better than 9% in whatever you define as the global AI ecosystem. And that's also something we should protect, right? And we should celebrate it, but we should also make sure that tomorrow and the day after and in 5 years, we still supply a good part of the world's AI talent. And yes, if then some of our talent wants to work in China or in the US, good for them, good for us. They bring our values into these systems, all great, right? But we need to have a tangible major stake in this. And as Tomáš said very nicely, that requires a massive investment.
Thank you very much. Patrick, would you like to comment?
Yes, just tying up with what was just said, I think there are very, very strong reasons for struggling to get an actual EU ecosystem in AI. I think it's very important for sovereignty, for values, for independency. I mean, we've seen that, unfortunately, recently with drugs and the pandemics, with the energy and the war in Ukraine. So we are facing headwinds which have revealed how dependent we are in Europe in terms. So it's very political here, right? So I think an AI is. I mean, we don't want Europe to be completely dependent on other part of the world for that. So to me, it's clear that the EU has a role to play and should play the role for the EU citizens. But at the same time, there are two reasons for me to advocate for being part of a global AI ecosystem on a different level. One is that it's a scientific discipline, and I mean, it's pretty obvious with the researchers in this room, including looking at where they have been, etc. I mean, this community is just global; it's international, and I mean, it's very important. It's research, right? So that's great, and this should remain global. And the second one is we have one big challenge, which is for everyone, which is the climate change. And I hope that AI is going to help rather than the opposite. And I really wish that it's not fragmented ecosystems here for AI, because I think if so, it's going to be more harmful than not.
Thank you very much.
So I would like to add one thing again from my perspective of someone working in language technology, that actually just on top of the sovereignty and the other issues that were already discussed, we have actually one chance to do even more. And that's because in Europe, one of the elements of diversity is the language diversity. And we have to work within that system and for that system, meaning that if we want to be on par and keep the diversity, we have to have not one large language model, but 24, ideally 60, because there are also unofficial but big languages in Europe. And this could be actually a precedent or even technological breakthroughs, like have one model for 50 languages and so on, for other parts of the world or the global point of view, like India or many other parts of the world which have the same situation, and if they want to go the same way, of course, as opposed to China, then we could lead in this respect, right? So, but obviously, doing 60 language models instead of one, it's a lot more money for all the ways from the hardware to the people who will work on it.
So there are tasks which should be taken by the European ecosystem itself, because it's very specific to Europe. But there are tasks like climate change, which is actually, the interest of all of us on this planet. Yeah. So okay, that actually is moving me to the last question, because we have some 9 minutes.
Let me do you, if I may.
Yeah, sure.
Because I promise that I'll just kind of give a comment brief after my fellow panelists will speak. Again, I agree with your points, and Europe should pay more, and this is our opportunity. At the same time, I am convinced that there is the other important aspect, which is that we haven't talked about, and this is the mobility of workforce, because the AI successful countries are those countries who have open mentality to bringing educated workforce from third countries. And arguably, in many regions in the European Union, this is not the case. This is a limiting our success in kind of growing even better capability comparing to Canada, Britain, and United States.
Okay, thank you very much for this follow-up comment. And we have some less than 8 minutes according to display. So last question. Yes, that's it. Do you see AI as a strategic resource that should be addressed by an international, intergovernmental organization? And I remind you of a coal and steel in the very beginning of the European integration, and of course, OPEC, organizing the petroleum exporting countries, etc., etc. So what about the International Organization for AI? And I would start with maybe Holger.
Yeah, I'll try to be very brief. I think absolutely we need that. We need that because the member states, even the ones that are economically quite weighty, such as Germany and France, right, will not be able to do something at the scale where we can really make a global impact by themselves. So clearly this is a European project. It would be best to make it a European project in the geographical sense rather than in the EU sense. That means to have the UK on board, to have Switzerland and Norway on board as well. It would be wonderful to do it, shall we say, CERN style. So, CERN style in the way that also other international players, including the US perhaps, invest themselves into that. I think that would be wonderful. But I do think that we need some European leadership in this, and we need a big European stake in it. I also think because of the diversity issue that Jan mentioned or emphasized as well, Europe would be in a great position to actually kick this off. To believe that it can be kicked off just with sort of a nice ambition as the Commission currently does is like believing in cold fusion. I would like to believe in cold fusion as well, right? But we know the way to get nuclear fusion to go is massive investment and massive amounts of energy to get the thing started, right? And then hopefully it will become self-sustaining, as you guys have argued, and actually produce benefits. And I think compared to fusion, AI is actually a much better and a much safer investment in many ways. So I do not understand why it's so difficult to pull this together. I honestly think for the member states and for the Commission, it should be easy to do that. And maybe what's needed is somebody from the outside, like Britain, for example, to say, you know what, guys, let's just do it. Let's do it together. And if you don't do it, we're going to do a national one that's going to suck off the last of talent from your continent, right? Maybe it takes that kind of a threat in order to pull people together to finally do the right thing and create something that does become a magnet for talent, an amplifier for expertise, and ultimately a big producer for economic value for the European Union, its friends, and far beyond.
Thank you very much. And Michal, now you're second. So what about International Organization for Peaceful Use of AI?
Yeah, I will respond, and I first answer to what Holger suggested. Recently, there have been formed a NATO Innovation Fund, okay, out of kind of NATO countries that wanted to invest in innovation for defense. Actually, US didn't join because they've been kind of funding their defense innovation by themselves. It took the war in Ukraine to kind of get people together and to understand that they need to fund innovation in defense. I actually think that the kind of danger of losing and falling behind in AI is a similar threat. And it should be leading event and leading opportunity for the nation states to kind of get together and to kind of follow the example of the NATO Innovation Fund and to collect the resources for funding AI in a similarly strategic way. In terms of overarching international organization, as I said, I believe in a transatlantic US-Europe a collaboration. So definitely, if there is a body that would kind of make sure that the wealth created and access is kind of equally distributed between US and the EU, I think it will be a tremendous success. But there is the third piece. When you talk about a global organization, and this is the oversight of AI that we haven't talked about, and there I'm cognizant of the threats that kind of uncontrolled development of AI can pose to people, and there I really believe in transparency And if somebody would be establishing an organization similar to the organizations guarding the nuclear arms development, I would be all for it. Not necessarily for control, but for maximizing the visibility of what is going on in AI development, not only in academia, because there we have the visibility, but also in the big companies.
Mm-hmm. Thank you very much. So maybe the first assembly would be in Prague, yeah? Tomáš.
Yeah, I was just thinking about like what would this internal national organization that would be overseeing AI development, how it would look like, and I actually think that it will be created no matter what we think. On one hand, on the other hand, I think that there's quite a few things that can also like go wrong because. I think that world is at the moment imbalanced again, as we were discussing before. Like Europe doesn't really have much money in AI at the moment, and so like say public funding and so on. But we are not really creating the values here. And if we would create this AI organization at the moment, that would be like worldwide. Like whose interests would this organization follow? Well, probably not ours because we don't really play like a significant role. So I'm not sure if it would be such a great win at the moment. At the same time, if it would be like some blue sky organization that would be just giving some suggestions what should be done here and there. In other words, if it would be powerless, then it would be also probably redundant because again, there are like pretty strong players who are seeing AI as basically this source of wealth, source of money, and like why should they be limiting whatever they are doing? Again, we can look at China. Maybe they are not going to follow whatever ethics regulations we come up with in Europe. So why should they be part of this international organization if they are just going to either there will be no power to enforce whatever recommendations this organization gives, or if there will be the power, then some players may not want to be part of it. Some players may actually abuse the rules and just maybe take over. So maybe I'm a bit paranoid, but I think that such organization will probably be created. But I'm a little bit worried already now about it.
Okay, so maybe not the overarching international organization, but maybe for climate change, Professor Hajc.
I have 25 seconds. So my answer is yes, but maybe we should have two. One, there will be worldwide or at least transatlantic, where we will coordinate, and then one in Europe, mainly with industry that will lobby. And we know about successful organizations like that, like BDVA, and at least, half successful, I would say. And I think that's one way to actually make the EU improve the ecosystem. It's money first, but there is also many other things, as I said before, legal environment, which is both encouraging and regulating in the good way, and providing other things like cross-border cooperation without, everybody knows about AI A1 form. I mean, this is something which is even worse than Brexit, I would say. So, things that limit cooperation, not only in AI, but in general. And there should be a very strong lobbying organization to do that.
Great. So we have one international worldwide organization for AI, for common interests like climate change. And we have one specific for Europe, and there will be one specific for the United States, maybe. Patrick, some last comment?
I don't know if we need one organization, but we need definitely a coordination at the EU level, that's for sure. And I think ELIS is a good example, at least for research. We should have something similar for infrastructure. So there are efforts here in the Czech Republic with the supercomputers of Carolina, I think the name. We have similar things in France and presumably in other countries. If we can coordinate with infrastructure, that would be nice. Or even better. For the rest, I'm always a bit cautious with new layers of organizations. But coordination and joint efforts in Europe, that's for sure.
Thank you very much. Thank you, gentlemen, for this very nice discussion. We have a lot of questions we can't cover within this time, and very happy to meet you all. Thank you. Thank you. Díky moc. Thank you. Thank you. So I give my floor back to you, Josef.
So we
In the program is a coffee break, so we are a little bit behind schedule, but not by much. It seems 7 minutes or so. So if we can wrap up the coffee break, say 3:30 in 13 minutes, I think then we would start on time for a set of, these will be highlights of the research coming from this building, from people who mainly came after significant experience abroad. So I think it's going to be very exciting, kind of short 20-minute highlight talks, and we wrap up with a panel of the future of AI. So, but now coffee break, 13 minutes. Thank you. which is going to be very exciting as well. We will kick off the last segment with 3 sort of highlight talks, 20-minute talks, as I said, from researchers who we are very happy that they came here to CIIRC after significant experience abroad. And so we will see some of their latest research results. And at the end, we will have a wrap-up panel discussions about the trends in AI. So don't stay with us if you want to learn about what, well, at least some of us are thinking about what's going to be, what is interesting, what's the trend in AI, what may be the new breakthrough. Stay for the wrap-up panel at the end. And so let's start this segment with welcoming Torsten Sattler on the stage. Torsten, thank you very much for being with us here today. So Torsten is a senior researcher in this building in our institute, where he's heading the Spatial Intelligence Group. He's known for his influential work at the intersection of 3D computer vision and machine learning, with especially sort of localization, which I'm sure you will see some of the results. Just to say a little bit about Torsten. So before he joined CIIRC in July 2020, he was an associate professor at the Department of Electrical Engineering at Chalmers University at Sweden. Before that, he was at ETH Zurich, where he first started as a postdoc, but then he was for several years a senior researcher there. He got his PhD from RWTH Aachen, which was already mentioned here several times, a great university in Germany. So, Torsten, it's really wonderful to have you here, and please, the stage is yours. I'm very happy to hear your results.
Thank you very much for the nice introduction. I'm going to talk about 3D reconstruction, visual localization, which are 2 of the main research topics of the group that I'm building here at CIIRC. Let's start with the visual localization problem. It's rather easy. We're given an image, and we're tasked with computing the exact position and orientation from which was taken in a given scene. Why are we interested in this? There are multiple applications that build on top of this. One is augmented reality. This is some work that we did a few years ago, nearly a decade ago actually, where we want to display virtual objects into the field of view of the user in a way that they feel like they are part of the real world. So this is what we did back then. Nowadays, if you have a Google smartphone, you can actually get something similar as part of Google Maps, where you can localize yourself by sending an image to a server, and then Google will give you walking instructions based on where you are. Another interesting applications are robotics. So this is a project that I was involved on while I was at ETH, where we wanted to build a gardening robot that can trim hedges and cut roses. And for this task, you need to know where you are in the garden in order to figure out how to get to the topiary that you want to trim. Last application, this is a recent work. This is joint work with Gerard Ponsmall's group at the University of Tübingen, where we mounted a camera and multiple IMUs on humans, and then this allows us to track the motion of the human, and by extension, actually figure out how they interact with the scene as well. Good. Let's talk a bit about what localization, how this is done technically. The typical approach is you have some 3D model of the scene. And for a new image, you try to establish correspondences between pixels in this new image and 3D points in the model, which you in turn can use to figure out what's the exact position and orientation from which the image was taken. And this is still, I worked on this type of methods during my PhD, and this is still state-of-the-art to some degree. But it typically requires a specialized scene representation that's just built for the purpose of localizing images. And if you think of like localization content of applications, this can be a disadvantage. If you're thinking of a robot that needs to navigate somewhere, needs to have a scene representation that's suitable for navigation, then having to build and maintain and synchronize multiple maps is effort that you probably don't want to do. So one of the things that I'm interested in terms of research is figuring out what are good, appropriate scene representations for visual localization that can be also used for other tasks. One thing that we recently published is work by one of my students, Wojciech Panik, where we were looking into using 3D mesh models that are dense and can thus be used for, say, occlusion handling in AR, path planning in robotics. And we wanted to investigate how we can use them for localization. And what we actually noticed, what I thought was interesting, is that like these localization pipelines that I've shown cannot only establish correspondences between like photorealistic models, but you can also establish correspondences between a real image and such a rendering. And not only like such a rendering that's close to photorealistic, you can actually have correspondences with rather abstract styles. So here you just render like a shaded version of the geometry without any textual details, which I was very surprised by when I first saw the result, which I think is interesting because it opens up new avenues of research. One thing is, this is work also by Wojciech, which we'll present at CVPR this year in a few months, or next month actually, where the goal is, rather than like building an accurate model, can we download models from the internet that other people have built? And those don't necessarily need to be like highly accurately. Here you see the range of things that you can see. This is Notre Dame. Some people just upload like a set of planes that, as a human, are still like, this is Notre Dame, if I tell you. But our question was, can machine learning algorithms or like localization algorithms handle this? And to this end, we're going to present like a benchmark study that uses different, like real images and tries to localize them against like different models of different quality downloaded from the internet, with one of the motivations being that if you're interested in or tasked with, for example, designing an AR application around St. Vitus Cathedral, then this technique would, or this set of technologies would allow you to just download models from the internet without having to do data acquisition and 3D reconstruction yourself. Anyways, if this is interesting to some people in the audience, the benchmark dataset will be online soon. So this was work on trying to improve the accuracy and robustness of localization algorithms. Another important question is that's starting to get more traction in the research community is, what about privacy? So in practice, what you would build like a system, something that starts with edge devices such as, say, a HoloLens or a mobile phone that take images that get transmitted to a server where localization happens, and then the server transmits the position and orientation back. And it turns out, like, obviously this is ripe with potential privacy threats. So like a malicious server might learn details about, say, how certain parts of the environment look like by analyzing the images. So there's work on this topic that tries to send a more abstract version of the images to the server. Storing user-generated content on a server owned by a large company is a potential privacy leak, because it might contain information that you don't want to share with someone who gains unlawfully access to that server. And there's some work, again, on designing representations where you lose certain privacy details. What we're going to show, and this is work by one of my student Kunal Shilani, is that also the last step where you do localization and transmit something back to a client is a potential privacy leak. Because just by querying the server, an attacker can learn content about what's in the scene. And it turns out that this is actually, like, the reason why this attack works is that we're starting to build localization systems that are robust to strong condition changes. So ideally, we would like localization to work under day and night changes, in the context of robotics, the robot should be able to operate 24 hours a day, not only at like around noon. We want systems to be robust against motion blur, which happens frequently, and we want to be able to be robust against viewpoint changes. And this desired robustness to changes in shape and appearance actually enables like potential privacy-based attacks. And our attack is rather simple. We assume that the attacker has some video sequence of some object. So for example, you could have downloaded thousands of pictures or video from the internet. The attacker builds a 3D model from these images so that they know where in space these images were taken, and then queries the server with each of these images, gets a pose and return back, and then having the poses returned by the server, and from 3D reconstruction aims to place this object in the scene if possible. And if you have enough images and do this enough times, you can start recovering what's actually in the scene. So you get an idea of the scene layout. So here's the qualitative result. On the left, you see the actual scene with the objects that we try to recover highlighted. And here you see the results that we got by querying with similar but not fully identical objects. So you get a very good idea of what is in the scene, what's the placement of the objects, which to some users might already cross the threshold of this is private to me or not. So here, the takeaway is that what we actually desire in localization algorithms in terms of robustness could also backfire in terms of privacy. I think there's a lot of interesting work to be done there. So much about localization. One thing that we noticed, and I showed this slide before, is that we get better results if we try to build photorealistic 3D models of the scene. So, how do we do this? How do we get photorealistic scenes? That's the second main research direction of my group. And I'm going to show a couple of results. Here you see results of an existing approach in rather complex scenes. It's a machine learning-based method. What makes these scenes complex is not the structure of the scene, but that there are relatively few images observing them. So each part of the scene is only observed by a few images. So you get very few constraints that you can use to reconstruct the scene. And as a result, you get these jumbled things such as like geometry floating around, like very unclear structures, and so on and so on. And the work that we presented last year at NeurIPS, and this is work with Andreas Geiger's group at the University of Tübingen, uses a very simple scheme based on the observation that neural networks nowadays are quite good at predicting distance of structures to the camera and normal. So you can take an image, you can run it through a network, and you get a depth map which says this pixel is roughly this far away, and you get a normal map that says the corresponding surface element has this normal. And while this is not super accurate, you can use it as priors for the 3D reconstruction process. And using these priors can have significant, result in significant differences. So here you see the original method, and here our adaptation just by integrating the priors. You see that we can recover the shape of the skull very accurately. We can get a much better picture of a reconstruction of the room, both in small scale and at large scale. And it doesn't add much computational complexity on top of this. If you're interested in trying this out, we recently published a software framework called SDF Studio that implements this technique and other 3D reconstruction, state-of-the-art 3D reconstruction technique. It's available on GitHub if you want to try out. So this work was mostly concerned about the quality of the surfaces. The last thing that I want to show is ongoing work with one of my students, Jonas Kulhanek, on trying to build like scene representations from which you can render photorealistic views. And so these are renderings of the scene representations. These are not images. I just want to mention this because they are very close to each other. So this is the type of quality that you can get with a technique based on something called neural radiance fields that I'm not going to go into detail. If you want to be convinced that this is not a real rendering, then look at the depth maps that we get from the reconstruction process. Here, like colder colors mean closer to the camera, warmer colors mean farther away. And while we're able to actually reconstruct most of the scene quite well, there are some artifacts here on the table that show you this is actually not a real image, but this is something computed. And with this, I would like to actually wrap up. So in general, what my group works on is building, like reconstructing the world in a manner that's photorealistic, but it can also be used for visual localization, including the question of what's actually, how do we need to build scene representations that might not be photorealistic, but that ensure certain levels of privacy. Thank you very much.
Thank you very much. Thank you very much, Torsten. Lots of wonderful results. Any questions from the audience? If maybe, yeah, here is one.
Yes.
Like in the last movie, how computationally expensive is it to generate that?
So the results that I showed are, I think, after 24 hours, but you get already get quite good results after 40 minutes. That's on an A100 GPU, multiple ones, I think. That being said, the implementation is not particularly efficient. I would expect that you can get like comparable results if you really tune it in 20-ish minutes. And we are looking into actually making this much faster by introducing approximations that will reduce quality but will make training hopefully significantly faster. Yeah.
Any more questions from the audience? There were some people from industry also. How far, just a practical question, how far we are from just having a mobile phone in our hand and scanning an object like this to be, I mean, for robotics, we always get these questions like, you know, to manipulate objects, can we scan them quickly? What's your take on this?
So I know that there are startups that actually do this on the phone, not using deep learning-based techniques, but like classical multiple view geometry stuff. Nowadays, you can also see more and more applications that actually take images and then send them to a server and do the computations there. This type of object should still be fairly simple. It has enough texture. There are like harder things. It's actually one of the things that we would have shown in the testbed tour. Mm-hmm. One of my students is working on reconstructing objects so that they can be used for pose estimation and object manipulation tasks for robotics.
So do you think actually it's usable already in some cases now? Or is
I think
in
some cases, yes. Mm-hmm. It depends on the quality of the object and how much time you're willing to spend there. But I think like real-time 3D reconstruction is certainly possible. The quality that you get out of this is then the question.
Okay. So that's what, you know, one of the things you can improve potentially.
Indeed, yes.
Any more questions from the audience? If not, let's thank Torsten very much.
Thank you very much.
We have a next highlight talk by Martin Sura. Just a few words about Martin. We are also very happy to have him here. He's a senior researcher here in the building and the head of the automated reasoning group. He'll probably talk about it, but just say he's one of the developers of the automated theorem proof Vampire, which, if I understand correctly, is one of the leading systems in the world in this area. So it's an honor to have Martin here with us. A few words about him. Previously, he was a postdoc at the Faculty of Informatics of Vienna University of Technology. And before that, he was a research associate at the University of Manchester before coming here. And he did his PhD, I think it was jointly between Charles University and the Max Planck Institute for Computer Science in Saarbrücken. So again, we are very happy to have Martin to build his team here with us, and he will tell us a little bit more about what he is up to in his research. Martin, floor is yours.
Thank you.
Thank you, Josef, for the very nice introduction. So the talk is called Powering Automated Theorem Improvers by Machine Learning. I might start by thanking Josef Urban for inviting me here to CIIRC after my postdoc ended in Vienna and initiating me to this topic and also pushing me to submit the proposal that led to the project that I'm going to talk about. Right. So we are. What is automated theorem proving? It's one of the classical disciplines of symbolic artificial intelligence, going back to the beginning of the computers to the 50s, basically. And oops. So here the task is we use logic basically as the formal language. So that's why it's symbolic. We describe things in the world in some formal language that is logic for us, and the main driving thing in the algorithms is logical deduction, which is sound ways of deriving new facts from already established facts. And what is important in this area, what is the key here, is that at the end of the thing we should get a proof, which is some kind of artifact that presents a witness for why what the algorithm has derived is actually true. It can be inspected, it can be verified, and so on. And Josef already mentioned this in the morning talk. We are in some sense going towards fulfilling Leibniz's dream of this calculus ratiocinator, which was this idea of a really universal language and also some kind of unambiguous way of resolving disputes and even discovering new knowledge that would be fully mechanized, and so there will be no doubt that the results are correct in some sense. We have various applications of theorem proving. The most obvious ones is new discoveries in mathematics, because one could argue that logic is the language of mathematics, but among other very important ones are verification of hardware and software. Holger already mentioned in the morning that without proper verification, we wouldn't be, with our technology, computing technology, where we are now. And concerning verification of software, you could verify day-to-day software that we use, there used to be this blue screen of death in Windows. It doesn't appear so often anymore. But more contemporary applications of this are also the correctness of algorithms that come out of machine learning, right? For instance, if a neural network drives your car, you might want to have some guarantees. We've already had some references to this topic before. All smart contracts, blockchain finance applications where there is a lot of money in this, and smart contracts are also interesting in the sense that as a piece of software they are not so complex, so they are more easily attackable by these tools than some other things. And we are already starting some collaboration with an industrial partner on this. There is cryptography and security. You could verify cryptographic protocols. In natural language processing, there could be some semantic disambiguations of parsing of natural language and so on. So there is a challenge in this area, and there is also an opportunity. The main challenge is that, well, first, the technology is based on search, heuristic search. So in some sense, we don't have a better way how to do reasoning than by going through all the possibilities, and there are really many. So fundamental part of this topic is to do the heuristic research in a smart way. And what we are fighting against is the computational complexity. The more expressive your language, the more expressive the logic is, the harder is to do the reasoning. At least in the theory of algorithms, we have some explicit bounds, and in some more expressive logics like first-order logic that are becoming interesting for representing math, for instance, we know that the task is actually undecidable, so there is no algorithm that would succeed on all the inputs in finite time. But still, like, we know that humans do reason quite successfully, so there is a big motivation for us to try to imitate that. And the practical manifestation of computational complexity here is what we call combinatorial explosion. So when you try to combine things in all the possible ways, such that you don't miss some argument or some derivation, there is so many possibilities that you might get overwhelmed. And this is where the opportunity comes, and that's to use machine learning to derive from experience some new smarter heuristics, and also to possibly like make the prover adapt to application domains from the learning. And this was the topic of my project called Power AITP. Yes, so I wanted to talk a little bit about our workhorse, which is the automatic theorem prover called Vampire, which is a theorem prover for first-order logic, and it goes beyond that. So there is support for arithmetic reasoning and some other finesses. I'll give you a little bit details. I'll not try not to overwhelm you, but maybe take this opportunity to still teach you a little bit about theorem proving. So Vampire is something what we call refutational. So it relies on the method of proof by contradiction, which means that, so if you want to prove that some claim follows from your axioms, you negate that claim, and you try to derive absurdum by logical steps. It is saturation-based. I will explain in one slide what saturation is. And it's superposition-based. Superposition is this advanced logical calculus, so the precise rules how to derive new facts from the known ones, which has a built-in support for equality, and it's very important for math and also for other applications to be able to efficiently reason about which things are equal and which things are not. And we like to compete, and Vampire regularly enters several competitions, one of which the most famous is the CAS competition, and has collected throughout the years various trophies. And so I'm one of the developers, and this is the joint effort together with teams from Manchester and Vienna. Okay, saturation-based theorem proving in one slide. I promised I will not do too much of the details, but so there is some workflow, information flow in this picture happening from the input that needs to be processed, and there is some kind of pre-processing. And the unit of information, I might use this word in the few slides that come, the unit of information which we work with, it's a logical formula of some particular form. We call them clauses, and these are the blue dots that go from this container that is called passive, and they enter the container which is called active. 2 slides ago, I was mentioning the concept of combinatorial explosion, and this is where it happens in practice. In this hexagonal active set, you can think of it as a nuclear reactor, because whenever a single clause enters here, the task of the algorithm to achieve saturation in the limit is to consider all the possible interaction between the already activated clauses and this selected clause, and create logical consequences with respect to this logical calculus that we have here in the little cloud, which is the superposition inference rules. And everything that's created this way, the children of these interactions, are put back into passive. And you have this infinite cycle, and it terminates when you derive the obvious contradiction in the form of a specific clause, which is the empty clause, and that testifies the contradiction. Or you run forever. For instance, if the conjecture actually doesn't follow from your axioms, that can happen in practice. And so this clause selection moment is when you take the next passive clause and activate it, is the most important heuristic choice point inside of a saturation-based prover. And so there is some kind of rough estimate about that the passive set is typically so much larger than the active set, and the proof, if we discover it, when we discover it, is much smaller than the active set. And implicitly, what should be clear now is that all the clauses that comprise the final proof must have been activated in some moment. And so if I'm saying that the typical proof is much smaller than the active set, it means that we are wasting a lot of effort because we are not able to navigate to the proof very efficiently. So this is where the opportunity for learning is the most stark one. And we have been mostly focusing on that clause selection choice point. And the core idea is what I would call learning from successes, and has been formulated some time ago. Actually, I think this reference, although it's incomplete, to Stefan Schulz's work goes even into the 90s. I think 96 from his his master thesis. And so the idea is to basically look at successful runs on the prover from the past and try to change the clause selection heuristic such that it promotes clauses that look like the ones from the proofs. And then Josef was already mentioning this first modern successful incarnation of this idea in the system Enigma. And there are some technicalities that need to be overcome. Like with any application of machine learning, we need to create our examples, which is quite easy. We just take the selected clauses from the past successful runs. But here, the challenge comes from how do we represent the symbolic objects that the clauses are the formulas. They are basically some kind of trees, and that doesn't fit very well with the modern algorithms of machine learning, which like vectors of real numbers. So there is some challenge in representing clauses as features, and we can use neural networks for that, or we can do handcrafted features, but different approaches would differ on this. And then once you get the trained model, there is this task of somehow integrating it back into the saturation loop, but I will not go onto details onto that. I will briefly mention, however, what I did, what we did in this project, where we added neural networks to power this important heuristic in Vampire by a particular incarnation where we used recursive neural networks, and they were trained to distinguish clauses based on their derivation history. So let's not discuss what derivation history is precisely, but I'll tell you what it isn't. The surprising result of this project was that you don't have to read at what the logical formulas, the clauses, what they are saying. You would probably want that in your ultimate system, because you would want your ultimate system to understand what the formulas are talking about. But you can achieve very good results by already just looking at the pedigree about like what was combined with what. Maybe some axioms are really very explosive and they don't bring too much value, and so on. So basically, the network was able to capitalize on such hints. And the other upside was that this can be implemented very efficiently. Unlike reading larger and larger formulas and analyzing them with larger and larger networks, this can be done much efficiently. I will not ask you to understand this whole table. There's just two little pieces, little lessons to learn. One of them is, so in these columns, I can do the pointing. There are 3 versions of a model of a neural network that are trained on the data that came out of initial run of Vampire that solves something like 20,000 problems out of 50,000. That was my benchmark set. And just to confirm some common knowledge, the larger your network, the more accurate it becomes. But because we are doing good theorem proving, well, the algorithms are already very, very well optimized. Being precise is not the only metric that we need to care about, because as you see in the actual performance, the middle model was the most successful one, and that's because the much larger, the twice as large model was too slow to evaluate. So there is a trade-off between how accurate the heuristic that you learn is and how efficient is to evaluate it. So that's the lesson. I think I will need to go through this a little bit faster. This is a second topic, something that we came across. In some sense, it is quite well known already in the field that these algorithms sometimes behave very weirdly, in the sense that You change just a little bit the formulation of your problem, and suddenly from something that's trivial and solved very fast, it becomes impossible to solve in some reasonable amount of time. So it's quite the opposite of what you know from running algorithms on some easy tasks, like searching through a graph, shortest path. We have polynomial guarantees for these algorithms here because we are dealing with undecidable problems. Yeah, things can go wrong for some weird reasons that one could describe as some kind of manifestation of chaos. And so what we did in this work was to, and the chaos is bad because then when you implement a new technique and you introduce it into the solver, into the prover, what can happen that by this change, you solve new problems, but it's not clear whether it's because the technique is smart or because it just butterfly affected the search in the right direction and shouldn't be taking credit for that. And so what is nowadays being possible through the fact that we have powerful servers is that we could randomize the runs, and so by injecting extra noise, one could suddenly again see, basically the chaos disappears and you start seeing some distributions that could be analyzed with the tools of statistics, and some nice conclusions could be drawn. I have an example which you should only try to understand in an abstract sense. So there was a work by my colleagues from Manchester, Giles Rigger and Michael Rawson, about some way of organizing a theorem-proving heuristic, and they were tuning some parameter, changing some parameter and observing how the prover behavior differs. Here is some kind of sweet spot, it's the fastest, and then you see some kind of like a jagged curve. If you insert randomization, so you try to do things insignificantly differently from the perspective of the main design of the algorithm, and then you rerun this many times, so this is like thousands of runs in this picture, you start seeing some weird pattern that's, unlike this jagged thing, it's obviously continuous, but so some deeper analysis would be required to see what's really going on. But we see that through randomization we get back from something jagged, something gets again continuous and maybe more meaningful. Right, and then we used this idea to empower the prover by creating so-called schedules of proving strategies. Well, the prover can be tuned in many ways. We call the tuning, or there are several options how to set it up. And a particular setting of these options is called a strategy. And it's well known that different strategies work well for different problems. And it's also because of this chaos, maybe, it's really hard to predict in advance which strategy will work well for what problem. And so this is already known. State-of-the-art provers use strategy scheduling, so they can run many strategies in sequence or in parallel. And that's how you solve many more problems. And last year, with my PhD student Filip Bartek, we created this new system called Snake, where we used the randomization mainly as the main trick to achieve extra robustness. And we entered the CAS competition from last year, 2012, in a demonstrating division because we were relying still on Vampire and we didn't want to compete against Vampire for the medals. But so you see that there's certain categories they are called divisions, I think, in the competition. The most important division is probably the plain first or the theorem proving, where we managed to beat Vampire proper by solving 9 additional problems. In some of the divisions, we didn't succeed so well overall because there are some specialist provers. For instance, this unit equality division where the clauses are not so complex, but the reasoning needs to be very deep because it's equational reasoning. We could improve much more over Vampire, but then we didn't match the competition. But the results were still very encouraging, with which I would like to wrap up. So this was a very exciting project. I was happy to be exposed to these challenges. The message from what I was saying in the first half is that with theorem proving, needs to be a balanced stroke between how clever your heuristic is and how efficient it is to evaluate it. So computational efficiency, very important. The second message was that randomization could be a way to fight chaotic behaviors and improve prover robustness. And there are some things that we are working on right now, and I would be happy to discuss maybe later, but I don't think I have time anymore. Thank you.
Thank you very much for the presentation. Any questions from the audience? I see two. I'll start with Patrick. Patrick, please.
So, two naive questions. The first one is, in the same way, AlphaGo seems to have discovered new strategies. So, is it the case that the new ways to solve theorems, different from what the humans are doing or the mathematicians are doing, have been discovered this way, or not at all? I mean, you solve a theorem, right?
Yes.
Or some theorems, and is it sometimes in ways which are quite surprising to the mathematicians or to the humans?
So is the question whether the theorems that we newly solved are interesting to the mathematicians?
Not the question is, even for old ones, is it solved in a way which is different or surprising to the mathematicians?
Yes, so sometimes, when you solve a problem, a human would do a task in a different way than a machine. So is it that the machine is finding ways which would be similar to a human mathematicians would solve it, or is it completely different?
Yes, this is a very interesting question. I think the answer is not so easy, mainly because the way these calculi work, the ones that we are using in the provers and that are specifically made for the automation, but not so much to be immediately explainable to the mathematicians. So we typically don't look at the proofs, at least, well, for the trivial ones we do, because we are debugging our solvers and so on. But if you solve something non-trivial, it could be hundreds of lines, thousands of lines, and you simply don't have the time to try to understand the particular ways of reasoning that the algorithm went through. And they could be probably like convoluted. There's some trade-off between explainability and between efficiency of finding the proofs, which is a very interesting topic. But and yes, I think we need to work on this more if we are to convince the mathematicians to use our tools. But so far we are probably optimizing in the direction of having the largest success rate. And I think it's like a second stage where you would want to explain what the proofs really are to the mathematicians. And I agree that's also a very important aspect.
Interesting. And my second question is that you are bringing machine learning to a task which is highly symbolic, so logic reasoning. And does it open up ways to do the opposite, to help? I mean, in other fields like mine, it's mostly data-driven, and we are now dreaming of a nice way to bring back reasoning and symbolic into these very data-driven machineries. So does your research also hints towards a way to bring reasoning and symbolic reasoning to hardcore machine learning?
This is definitely happening. There are some results already. I wasn't focusing in my work on this, but there is definitely very, very much of interest in using these techniques to, for instance, verifying neural networks, and yeah, it's all being done. It's very exciting, and there's many more combinations that you could think of just to be discovered and to be researched on. So I think we are in the right place at the right time.
Excellent. That's a very nice final note. So thanks Martin very much. He's going to be around after the talk, so there's more space for questions. And let's move on to the last research highlight. Again, it's so we are very happy to have Mikoláš Janota here. And again, we are trying to make here an environment which would attract people, with significant international experience. But I think in case of Mikoláš, it was an easy hire in a way, because he brought a lot of his own money. So in this case, he is a recipient of the prestigious CIIRC CZ grant, which he brought here to this institute. And just a few words about Mikoláš. He received his PhD from the University College Dublin. Then he held a postdoc position at INESC ID Institute in Portugal, and also spent some time at Microsoft Research in Cambridge, in the UK. And his research interests are in logic, automated reasoning, and especially in the context of software development and verification. So again, we are very happy to have Mikuláš here and to hear more about his research. The floor is yours, Mikuláš.
So hello, everybody. So I know that I'm the last talk, and everybody's very tired after the whole day. So I'm skipping all the technical details, so it should be very easy to follow. So I really wanted to highlight what we do and why we do it. So because everyone is talking about ChatGPT, I thought I should also have ChatGPT in my talk. So I played with ChatGPT for roughly 5 minutes, and this is what happened. So I asked, well, there is this very famous proof that there is an infinite number of prime numbers by Euclid. Can you also show that there is always at least one prime number if I take 10 consecutive numbers? And I tried this recently with some undergraduate students, and everybody was shaking their heads. No, of course, there's going to be some prime numbers with a larger distance than just 10. But ChatGPT somehow, I don't know if they prime it to be very optimistic, but it just says, sure, let's modify the Euclid's proof so that we can show that there is at least one prime number in 10 adjacent numbers. And then it goes on and on about some proof that, of course, is not a proof. It's just some sequence of words because that's what it is, right? Okay, so and now you say, well, okay, this is not so bad because if I ask someone on the street what's a prime number, they also don't know, right? So well, whatever, right? So this is not a disaster. But then I asked another question that is not seen here, but do you know what's the largest known distance between two adjacent prime numbers? And he said, there is a result that there are two adjacent prime numbers where the distance is like 70 million. And I'm saying, okay, so you're saying that for every 10 numbers, I can find at least one prime number in them, but at the same time, there are two prime numbers that are adjacent and their distance is 70 million. I said, yeah, sure, exactly, that's what I'm saying. Okay, so now you don't even need to know what's a prime number to see that this is not correct, right? So of course, the language models is great technology for translation, for summaries, for excerpts, but really it lacks the reasoning skills that we really would like to have in artificial intelligence. And my worry is that people will be forgetting that this is also artificial intelligence. Okay, so Martin already mentioned something about logic, so I will also continue in the line of logic. So people have been going this for literally thousands of years. So Aristotle started with this, all men are mortal, Socrates is a man, therefore Socrates is mortal. And then after thousands of years, we came up with this nice notation that says exactly the same thing, right? So this is something that we call reasoning at some formal level. And so we would like to use this to discern truth from untruth, right? So this is this kind of simplified scenario where things are either true or are not true. And I really like this slide. It's a history of computer science in one slide, at least in my field. So first, Leibniz said, well, let's formalize everything and we will be able to calculate everything. And then this guy from Morava or wherever, he says, well, there are some things that are neither true nor false. Okay? So this means that there will always be things that we will not be able to either prove nor disprove. Right? So this looked very depressing. Then it became more depressing because this guy said, well, there are things that we cannot compute. They are not calculable or undecidable. And then all the computer science people from complexity theory said, well, there's a lot of things that are very hard, even though they are decidable, they're just very hard. So this is something we teach undergraduate students, and it looks very depressing. And then it's like, okay, what are you doing, right? Why don't you stop? So not all is lost. And the good news is that we can really solve interesting problems using logic. And this is essentially what I'm trying to show here in this couple of slides. So what do I mean solving problems using logic? So we start with some problem, abstract problem, but eventually would like that to be a real-world problem. We translate the question into a formula. We run some heavy engineered solver, which could be Vampire or the solvers I'm working on, and we get a solution, which gives us a solution back in the real-world problem, and we're happy because we have a problem to the we have a solution to the original problem. Sorry. So the solving here. Why is it beneficial? Because we have heavily engineered solvers that people worked on, spend a lot of time, and the solver will do a better job than if you solve the problem directly by yourself. Of course, not always the case, right? So you need the right tools for the right problems. So I work in an area which is called satisfiably modular theories, which stems from SAT solving. And again, I promise there will not be any technical details, but it's a very different beast than saturation-based provers, even though now these kind of provers that Martin mentioned in my area, they collaborate, they use each other. So it's something that focuses on specific fragments of logic that will be hopefully useful in practice. And one thing that is true nowadays, and maybe it will always be the case, but the challenge is that it requires sort of expert knowledge and effort to be able to use these solvers. And what we want is to get push-button technology. Okay, so what we want is, okay, now this is maybe not realistic, but you know, I still feel young, so I still think that we will be able to make some strides in that direction. So even though we're in this undecidable, highly complex background, we do want to get push-button technology. So just to get a little bit more concrete about the applications, so I mentioned software verification. Martin also mentioned that. So what do people do with software verification? So we have a program that's potentially incorrect. So what we ask the solver is there a bug? Right? So we write down a formula that represents the fact if there is a bug or not. Okay? So this is a question, it's a well-posed question, and so we can translate it into formal language, which is logic in our case, and we run it into a solver. Right? And there's a couple of things that can happen, mainly false. There's no bug, and we're happy because we have a bugless program and we can sell it to the customer. Then the other scenario that says true. Yes, there is a bug, which also is annoying, but is not as bad as shipping a bug to the customer, so we can fix it and repeat the process. However, there is a third scenario, which is the annoying one, is that the solver doesn't know. Right? So I send it to the solver, and the solver says, I don't know, this looks hard, I give up. Or just compute something forever and ever, and we don't know whether the program is correct, incorrect, has a bug. We just don't know anything. Right? So our research is in this zone where we're trying to avoid the scenarios where the solver doesn't know, but also want to be faster when it says true or false. Okay? Besides software verification, there's other types of domains that use SMT solvers. It is, in some sense, we're sometimes paying for being the back end of some of these technologies because these guys can show some shiny results, but they need the solvers. I also wanted to mention some concrete examples from history that are essentially mainstream and industrial nowadays. So digital circuits, this is one of the first applications for SAT solvers where people were interested in checking whether there is a problem in one of the gates of the digital circuits. So you can send in some input, and the circuit responds something. If it's wrong, if the gate is wrong, then I'll see a wrong output, but only for certain input, right? So the question is which input I should be sending in so that I do get a demonstration of a faulty component, and I know how many components there are and how they are constructed and so on, right? So this is something that we can ask the SAT solver. And again, this is roughly how we do it. So we construct one formula that represents the original circuit that should be correct and the faulty one. And we ask the SAT solver to tell us when do they differ, okay? And then the SAT solver produces the input that we can send to the physical input, to the physical input of the physical circuit, and we can check if the physical circuit really is incorrect or not. We have to do it for all components, so there's a lot of technicalities which I promise to skip. Another thing is not necessarily software verification, but software testing. So this is a little bit similar to the circuits. So we were trying to come up with inputs to programs rather than just circuits. So this is some silly function that checks, it does an if statement, another statement, and if it reaches a certain point, it crashes, right? And the question is, when does it crash? Well, I just run a solver that says, can you satisfy x divided by 3 greater than 5 and x less than 9 less than 3? If so, I know that the program will get to the wrong point, right? So I run the solver produces a sample input, and then I run the actual program to see if it really crashes, right? Which might not if there's some issue with the modeling, but it's not a problem for testing. We want interesting test cases, right? So this is a way how to get interesting test cases. I wanted to mention here, there was this DARPA challenge in 2016 that was using these kind of technologies. So it was very nice. They had like autonomous computers that were somehow computing between each others for various challenges and hacking each other and so on. So this is something interesting to read about. There's also large projects, verification projects. So Microsoft, for instance, is trying to replace the whole HTTPS protocol with fully verified implementation. So these kind of things are interesting for the big companies these days because of cloud, right? So anything that has to do with the cloud communication is of interest to them. And of course, Martin also mentioned a lot of people are now doing smart contracts. So this is something that a lot of startups are doing these days. Well, okay. I don't have too much time, but just a few words about what I do. So we want to improve S&T solvers with machine learning, and we want to work on real-world problem, and we want to incorporate our expert knowledge about the solvers into what we do. So this is a very tiny, small example why and how we can use machine learning in solving problems in a specific domain. So I have this very trivial problem which says for all x is y such that x is less than y. And what we humans do and what the solvers don't know how to do is that we look at some examples and infer from them, right? So I for instance, check, I don't know, x is 3, and I see that 4 is greater than 3, and so on, right? So I can repeat this a couple of times and see, oh, actually, if y is x plus 1, then this is always true, right? So if I look at some small examples, as a human, I can generalize to a larger explanation that actually solves the problem in general. So this is something that completely lacks in the solvers these days. Another topic, a favorite topic of mine is quantifiers. So whenever we talk about all objects in some domain, we need quantifiers. So this all philosophers are mortal. This is quantifier because we are saying all. This is very hard to work with, and so this is something that we were looking at. Like imagine that you have this formula where, I don't know, you have potential candidates, what to plug into the quantifier, and you're hoping to derive a contradiction. And you can use machine learning to order the candidates to arrive to the contradiction earlier. Okay, so this is again a little bit technical, but well, actually I could have talked more slowly, but it's fine. Okay, so some future outlook. What is definitely lacking is this learning from experience, and I think Martin and I and Josef has been working on this, but we're still, I think, very far from really acquiring the same type of experience that humans gain. Like, for instance, when you learn fractions and you learn how to use math at the university, you gain a lot of abstraction that is completely lacking from the solvers. And the solvers, of course, they are much faster than us, but they don't have the abstraction. So this is something that is very interesting, and I think we're still scratching the surface with this. So we're hoping to incorporate machine learning, but it's more about the abstractions, I think, than the machine learning itself. A couple of challenges. We should never forget that this is very hard, theoretical, impossible, but we don't care because we want to look at the real-world problems. But that means we need good examples. This is not easy, especially in the university environment. In Europe, we don't have that much contact with industry. I think we are trying to improve on that, of course. But even if you have contact, then how to work with them. This is very, very difficult. So we have this kind of a chicken and egg problem, that hard to start the research in some directions if you don't have the data. So there's a bit of a disconnect between the people who write the solvers and who use them. And something that is maybe missing in these kind of NLP-style machine learnings or statistic-based is to come up with new concepts. So I would like it to come up with new concepts like this X+1 example. Another problem in SMT is that there's a lot of these subfields. So there's string, integers, real, arrays, quantifiers. So there's like this zoo of problems that we're looking at. How to focus on the right ones. So these are kind of challenges in the field. And yeah, so thank you. I'm happy to take questions.
So thank you very much. We have time for a few questions. Any questions from the audience, please? Anyone? Yes, Patrick, please.
Thank you for the talk. Very interesting. I'm completely far from the field, so maybe it doesn't make sense. But when it comes to this software verification business, the fact that the software is running a big neural network, does it? I mean, at least when we do AI, proving that the software is doing the right thing doesn't mean that I mean, I have the feeling that it doesn't. It's just part of the story. Of course, you don't want to have bugs, but. So my question is, because some people have tried, I think, to import or export tools from software verification to neural network verification. So is there something sensible there, and things that can be integrated from your field?
Yeah, so this is a very active research now, how to verify properties of neural networks. Yeah, so. I think one of the big motivation is, of course, this well-known attacks that you just change some small bits of a picture, and instead of a dog, it says, well, it's a house, right? But like for a human, it's not visible, the difference, but for the neural network, it's completely different because it's somehow sensitive to some noise. So this is something that you can formalize as a logic problem, where you say, if I change this input only a little bit, will it give always the same result? Right? So this is, again, like, so even though you're in a probabilistic setting or statistical setting, you can formalize this as a real, this truth-false problem, where you say, if I change it only a little bit, I pick some epsilon, am I guaranteed to be stable? Right? So these kind of attempts I have seen. I'm not active in this, so I mean, I'm sure maybe there's others here. But yeah, so this is. There's also other big attempts, like to use neural networks as controllers, right? So that you learn and then you reason about the network that the control just has some safety properties. And so it is possible, people do that. It looks scary because the network is huge. So it looks crazy, but yeah, people do it, yeah.
Okay, and my second question is for somebody who is doing very clean things, very theoretical, or about the properties of a software. I'd like to have your views about the way software development is going with a lot of AI assistance, like including using language model to debug or to test or to verify, of course, without any guarantees of any sort. So have you got any specific views on this trend in the software development industry?
So you're asking about the users of these.
So my question is for somebody who is caring about the proof, the verification, the properties. What are your thoughts about the evolution and the use of this tool and the way they are going to modify the software industry at large?
So GPT is now generating, some systems are generating code, right?
Yep.
So, and of course, you would like to know, is this correct, or does it, can one?
Yes, and also it can pretend to audit your code, saying that, or you can ask GPT or Copilot X, is this code correct, and can you find the bug? So there is this appearance of code testing or code verification with these language model-based software, but I guess I'm trying to see whether there is things that people from your field either can tell or help these new tools to do better or to be used with more caution or whatever.
Yeah, so yeah, definitely. So definitely there is an opportunity for collaboration, and I think there have been some attempts, but so far I think also very little. Right, so one thing is that one issue for software verification is that you need to write down what it means for the software to be correct. Right? Because I just give you a piece of program, if it crashes all the time, maybe this is what they wanted, right? So, so someone needs to write down what it means to be correct, and this is a lot of work. You know how hard it is to write documentation, and people typically don't even bother writing documentation. Now you want specific logic, formal specification of what the solver is supposed to be doing. And this is something that definitely could be generated by some NLP, right? So that you could generate a specification in a formal language and then try to verify it by exact symbolic methods, right? So these kind of things are possible. Of course, you're still getting in this who's gonna watch the warden, right? So you're still like in this. So someone ChatGPT generate a specification. Is it correct or not, right? Or I mean, also the other direction that maybe NLP suggests some issue with the software, and then you use some more exact methods to look for a bug. Yeah. So I mean. These are kind of these connections that we are interested in. So it should not be a fight between between the two methods, right? So we should. I'm just trying to highlight you need the exact methods as well for certain applications.
Okay, so thank you very much, Mikuláš, for a very nice talk. Thank you. And so we are moving to the last point on the program, which is the wrap-up panel discussion about trends in AI. And I would like to welcome and ask Professor Vladimír Mařík, the scientific director of CIIRC for this institute, who's going to moderate the discussion. So I would like to ask him on stage. And also take the opportunity to thank him again for creating such a wonderful environment here for science and applications also downstairs. So, Professor Mařík, please.
Thank you. I have this device. I would like to invite the panelists, because there are 6 of them in the list. So I would kindly ask Patrick, Josef, Robert, Tomáš, and also Professor Holger. Please take a seat. So I'm glad that it was possible to bring so many experts in one place at the same moment, and they are ready to answer difficult questions I have prepared for them. I didn't warn them in advance, so I'm looking forward how they would react. I don't need to introduce each of them because they presented today their research or yesterday, so it's not necessary to introduce. Now, question number 1. You are kings of the European Union, you have plenty of money, and you have to decide which 3 areas of fundamental research in AI you will fund. Just 3 areas which you feel are the most important for EU, for industry, healthcare, society, and we are talking about fundamental research. So who wants to start, or should I simply start from one end and then from the other end? So I'll start from Tomáš.
Okay, so 3 areas. Well, I'm the first one, so I guess I will have the worst ideas because I had the least amount of time to think about it. But I would say, in my view, if we would have really like this unlimited amount of money and we are the kings and everything, then on the first place I would put actually basic research, because I think that it's often overlooked. Everybody, or not everybody, but a lot of people now think that things have been solved with deep learning, neural networks. We just need to have more computers, more GPUs, and we will solve everything. I don't think it's true. I think that there's a lot of fundamental problems that current machine learning doesn't solve. Maybe we can develop some new learning algorithms, maybe some new architectures of these neural models, or maybe even different computational models than neural networks. But even areas outside of machine learning, I think they are often overlooked. They get too little funding, and I think that that is not a good thing to do. So number 1 would be really basic research, so that we build the successful future. The number 2, it was mentioned already, here, the healthcare. I think that that's a super important topic that somehow historically it seems to me that it has been overlooked. During the COVID crisis, I think that it was obvious that if we had some decision making supported by statistical models, that the societies, in my view, would be much less vulnerable towards random decisions of people who are changing opinions here and there. So again, I think that healthcare and even investing into areas like prevention, so that we would not even get ill, but that we would be living in a much more healthy way. I think that would be, once it will happen, and I'm sure that it will happen maybe 5 years from now or 10 years from now, people will be amazed by how far healthcare can be taken by statistical models the similar way as everybody is surprised now by the ChatGPT. And well, maybe the third area, because I'm biased and I always like this research direction to build AGI around language models and so on. So I think that that is an area that now is super popular. I think there is still a lot of value, but again, I'm biased. I would invest in this third area because I think that it can still bring a lot of more value, even if it is not already like the most visible part of AI.
Oh, thank you for your opinion. It was quite fair. What was interesting that you would support after COVID also research in the healthcare. The opinion of our Ministry of Industry is different. They stopped the establishing of research institute which should study applications of AI, mathematics, and other disciplines to solve such problems like epidemic, disasters, and whatever. With the explanation, COVID is over, it's not urgent, you know. So they have different opinion than you. But I fully agree with your proposals. Josef.
So I guess it's hard to disagree with Tomáš. I would say on top of the healthcare, it seems to me that AI can have a lot of applications in society, like in government, in the way how we are like collaborating with steering the society. Like there may be a lot of like algorithms are today used or almost abused. Like for example, during the elections, like there is like a very precise algorithmic targeting of the voters today. But and that might not be necessarily the best thing. And like we have similar issues like with all these social media, etc. So I could imagine that we will start designing things that will be actually helpful for like the society to come together, to rule, to govern itself in a better way. But I guess it relates to the healthcare a bit. And like maybe one more topic, I think like I'm also quite excited about like the deep learning and language modeling, and I think the progress there is really nice. But like my general criterion would be, is it good for science? Like if you can design AI systems that are doing science better and better, like better or at least as well as like, I don't know, mathematicians, physicists, biologists, doctors. And we know we sort of can do it, right? Like there's this AlphaFold, there is AlphaZero, which beats humans in like Go. So there are signs that we can really design superhuman systems that are very good at solving problems. So if we can do it, I think we will get an immense like boost. Like there will be like a snowballing thing that will help us to develop a lot of other stuff. So in general, AI for science, I think, is like one of the things I would definitely fund.
Thank you for your opinion. I think to bring AI to public sphere and to governance of the state means to educate the people and to tell them how to use it, because there are already many tools which might be used, but as the tools which support their decision making. They cannot expect that we will bring complete solution and replace them. And that if they misuse, and that was already mentioned in the first presentation today, it's even worse than not to use AI at all. So education of the people in the government and local authorities and everywhere where you make decisions is quite important. Tools are here, we need to learn people how to use them. Agree with your opinion. Josef.
So there are excellent answers what we heard before. I will add on top of this, thinking, from the perspective of the funders, I think it's harder to think, harder choice. I will maybe add on top of what was said, one thing. I think it's very important, if this was the case, to have some quality control, to really, fund things, good science. And I think for this, the ERC program, I think, is a great example of something which, is very well done. And when I talk with my US-based colleagues from the top universities, they envy us two things in Europe. One of them is the compute resources, which I think we are a bit ahead in having. I mean, they are maybe not as good as in the big companies, but it's better than what a professor, even at one of the top US universities, has access to by having these national infrastructures, but we have to really improve them even more. And the second thing which they, is a little bit sidetrack, but the second thing which they really envy us, and they say, which is great, what you have in Europe is the ERC program. So I think having that for AI, as Holger said, I think that would be wonderful. And I think there, what to fund there, I think the quality is important. We could, I think it's important to fund the basic tools, the basic research, because really AI, and I've sort of said this before, is like an engine which is going to power a lot of other disciplines, other fields in science. So I think we really want to understand that engine, develop that further. So I think we should have a program like that for, developing, understanding that engine. But I think I would not shy away to have something like a synergy, like, have really applying this engine in this cross-disciplinary areas, and that's where I'm also putting some of my energies, like with biology. What I'm hearing from biology is there is potential for really revolution biology because of AI. So I think this funding the understanding, improving the engine, but also cross-disciplinary things, very important. Focus on quality. That'll be my answer. Thank you.
I appreciate your focus at quality because it's quite important. You mentioned quality of research, quality of education, but I would like also to stress the orientation towards quality of the AI systems, which should be verified. We should verify the limits, find the methods how to verify the limits of the systems, because misuse, or if we will use it beyond the borderline of expertise, they will bring a lot of damages. So quality everywhere is your main, let's say, label. Now, Holger, please.
Well, you just said, I think, what I would consider the most important thing, which is I would invest these resources to a large extent into making AI systems that are better aware of their own limitations and capabilities, and specific AI techniques that also help monitor AI systems in general and warn us when they go wrong, right? There is, of course, research on this that already exists, very exciting research, but I think this is something that agrees very much with our values in Europe, right? Our engineering tradition that, we want correct things, we want reliable things. So this is one area that I would invest in. The second area is systems or AI techniques that help us to actually build more efficient AI systems. So as you know, this is my area as well. So this is not me saying I want more money for myself, but I do think that everybody wins if things like automatic tuning, automatic configuration, automatic synthesis of AI system can be made broadly available. And the reason for that is that this, for example, in part, could help us solve the AI sustainability problem, right? By making systems that produce similar quality at lower compute cost, and that would be very valuable. Now, being forced to pick sort of a third thing, that's very difficult, right? I think Josef here did a great job in emphasizing the need for infrastructure and supporting talent. I would want to do that too, for sure. But I do think there is one area right now that I believe is really important for the future in terms of a topic area rather than a spending mechanism. And that, I have to say, is NLP, right? There have already been good investments, and there should be more, don't get me wrong, into machine learning, reasoning, and so on, and robotics as well. And there should be more investments. But NLP is currently drastically lowering the barrier to accessing and interacting with AI systems. And this is extremely powerful, right? And it's important for us to be able to compete there and also to do better than current NLP systems do, right? Do better in the sense that we want systems that can reason, right? That don't fall prey to the actually very interesting examples that we saw in the last presentation here, right? So that is the third area that I would massively invest in, because I think it changes the game not only because it's based on awesome machine learning, it most definitely is, right? But it changes the game because
it drastically lowers the barrier to entry for interacting with and using AI systems, and getting this right is the basis for using AI responsibly, in my opinion.
Thank you. It was quite clear what you said and consistent with your presentation. NLP is now on rising curve, and it's important to finalize the development in this area in the way that the people will really be able to use it and to document usefulness of AI to the citizens who are taxpayers and who are bringing money back to continue in the research. And so it's quite important area. Yeah, thank you. Patrick.
Okay, three things. One, which has already been mentioned here, and I think I really want to emphasize it even more, which is reliability and safety. So I think it's one of the fundamental limitations of the current systems, and this prevents them from being really used in safety-critical applications. Of course, I mentioned one in my presentation, but there are others, including health. I think it's a very open scientific question, how to make these models aware of their uncertainty or confidence, how to make sure that they are verified and safe at large. So I think it's very important, and it's both scientific question and very applied. The second one is to make sure that AI becomes really a major tool for the people who are doing basic science on the major challenges we have for the humanity, again, climate, energy, and health, and having tools which are really for these people and that which need to be developed with the knowledge of these people and the knowledge of these sciences. I think it's very important. So I'm really a strong believer in the interface between machine learning and basic sciences, and we don't need to rediscover. I mean, it's interesting to rediscover mechanics by machine learning, but we know mechanics, or the same with chemistry or biology, etc. So making sure that all these things are well intertwined in order to get way stronger tools in the hands of these scientists. The third one, which is a different note, recently I have decided that I wouldn't sit in a panel if there is no women. Obviously, I failed. I'm here, and there is no women on this panel. And it's not to criticize at all, of course, but just to say that in terms of education, that's the other thing that we are lacking in many fields, but AI in particular and computer science at large. We lack diversity in terms of gender in particular. So let's invest there, and I think it's a long-term investment to be made.
Yes, that's a quite clear mission or vision, because people will decide everything in the future, and we need to enhance the university research and education. You mentioned also ethics. That's a very important issue, and I think we are facing the problems of ethics more and more as the systems of AI are being developed. So very hot topics, and this linkage between, let's say, machine learning and different disciplines. We need to learn people how to use the machine learning in the appropriate way. Thank you for your comments. Robert.
I'd like to reinforce or emphasize one of the points that already has been mentioned, and that is correctness by design or verification or whatever you'd like to call it. I was trained as a control engineer in control theory and these kind of disciplines, and you were one of my teachers. So, a great characteristic of that field is that you're trying to design systems in such a way that, at least on paper, they perform as desired, as required, and you do everything for also making sure that the eventual application or implementation is actually doing what is intended. And this is in a stark contrast to the current practice in AI and machine learning, where we use just lots of haphazard tuning of hyperparameters and basically cross our fingers hoping for that the system works. So I'd like to have much more research in sort of making current machine learning AI systems certifiable and verifiable. And the additional things that have not been mentioned are other structures than neural networks. I think we are now in the stage where, after so many years of almost having banned neural networks as a viable technique, we have overshot to using almost solely neural networks. And I think it's a kind of almost laziness. They work, right? So we have a common structure and we just put as many layers and billions of parameters, we train it and it works. But I think for a majority of real-world applications, there will be much simpler models that will do exactly the same job as the deep, over-parameterized neural network. We just need to find them. So we don't know how they look like, we don't know how to train them, but I think if we do our best, we will find methods that are just better than deep networks, or at least as good, but maybe give us more power in analyzing their performance. And finally, I think currently there's a lot of emphasis on supervised learning and on providing labeled data or semi-supervised learning where you're learning to predict, let's say, a missing word in a sentence, these kind of things. I think we should spend more research on unsupervised methods where this manual labeling, which is preventing many applications like autonomous driving, I think most of the problems are by actually failing to identify and label these edge cases in which these systems work. So it's an endless work. You just have to label more and more data. It doesn't seem to be like a viable way to getting a fully foolproof system. So we need to go after preferably unsupervised methods that will sort of teach themselves. I know it's very hard, but that's where I would spend money.
Thank you. You mentioned as the first speaker here also data and quality of data for unsupervised learning, because without quality of data and work with data, we cannot achieve good results. What was interesting, then half or more of the panelists stressed the need for verification of the AI systems, and it seems to be a hot topic. Second question to you, and I'll start from the other end. Which technology of AI developed in the AI frame will influence the society in the forthcoming 10 years, in the forthcoming decade? Will it be GPT? Will it be machine learning? Will it be robotics, industrial robotics, or healthcare systems, where you can see strong impact on the society and what will be, let's say, important for AI development in the future, to document with people that there is something useful, that it is something stable, which brings correct decisions and which replaced people in decision-making. Robert will start.
Yeah, so I'm not quite sure if I understand the question correctly. You threw many things in one bag, methods, techniques, and also application fields.
I just mentioned techniques.
Yeah, so let me just make a random pick. So I think robotics, that's my field, and also I've had a talk on that. So I think there's a lot of room for, let's say, harvesting the results in the individual disciplines, like machine learning, AI, control systems. If we manage to integrate these methods in a proper way and put them in operation on real robots, I think we can shift the progress, or we can bring it much further than where we are now. And I also embrace what was already mentioned, healthcare. I think there's an enormous space in healthcare for, again, using maybe even those methods that are available at the moment in a responsible way and giving medical practitioners the right tools that they can sort of adjust to their ways of working, and we can benefit a lot as a society.
So
it's a short take.
What you are saying is there are a lot of methods which should be in a reasonable way applied in the areas which are very important, and this will bring the results, and that's the way where to go.
Exactly. Many of the tools are there already, maybe not exactly ready yet, but it's not...
Many of them are ready already.
Yeah, agree.
Thank you. Patrick.
So things that are going to change our life in a very visible way, it has already started. It's hard to ignore. If you had asked me that 8 months ago, probably I wouldn't have... I would have ignored that because I didn't know. But I mean, these language models, when you see in companies what is happening in the daily life, people just using these Copilot for code, the ChatGPT for text, etc. It is entering the workplace. So it's changing the way people work in many jobs. So, but more importantly to me, I think that healthcare, from drug discovery to diagnosis and imaging and therapies, etc. I think here we can have something really big and really important with machine learning. And I hope we are really on the verge of seeing now the revolution starting there.
Okay, so thank you. Healthcare is in the focus of your attention, and you are right. What we need more than to be healthier and to use technology to enhance the health. Yeah. Okay.
So hard to disagree with anything you said. I mean, they're totally compelling points. So what can I say that's a little different from that? Notoriously difficult to predict what techniques will sort of be most important, right? I think most of us would have gotten that wrong the last few times around. So I'm not even going to try this, but at a general level, I think after we've learned to do amazing things, learning from large amounts of data, I think what will make a big difference is doing amazing things from very small amounts of data. And for that, I think we need new learning techniques, and I also think we need reasoning. And if we combine that in just the right way, we might not just be able to do amazing things with small amounts of data, for instance, in medicine, where we can talk about rare diseases, right? Or in diagnosing complex technical systems, where we can talk about very rare fault conditions. But we can also do it all in such a way that these systems become more predictable and more robust and basically more reliable in the way that you, Robert, actually emphasized quite nicely in the last round. So that's why I would see a lot of impact globally, and especially a lot of opportunity for impact in Europe, because once again, this sort of agrees very much with our engineering prowess that we have in many European countries. So it's a good fit for us.
Thank you. I also would like to highlight in your presentation the linkage between machine learning and reasoning, because reasoning can serve as a, let's say, glue or integration tool between among different smaller models of machine learning, which might be used in this or other area. So I think reasoning should be used in much more higher extent than up to now, linking the methods already existing, which are sometimes partial, sometimes bigger, but mainly partial, and reasoning might help to integrate them. Thank you. Josef.
I will mention two areas, and also because I have experience in them. One of them is robotics, as Robert said. I think there is an opportunity here. You'll also see there is also hardware involved, so we'll see how quickly that goes. But I think there is a lot of potential. And the second area I want to mention, I already mentioned a little bit, but I think it is, and people say health, I will go more specific. I think it's biology and chemistry. I think these are areas where really, and it's not just new drugs, we'll just develop, new understanding. It's just we see a lot of how much we get from scaling up the compute. Holger was showing the very nice example, and I'm sort of getting into that area. So I'm not an expert, but seeing that what it allows you is like speeding up the processes, which would take months to design. And I'm not in design like expert with new drugs, and we are sort of new potential molecules, and we are getting to a stage where one can do these things in a matter of minutes. So it's really, I think it is, and what colleagues of mine are also saying, it's likely going to be a revolution in biology, and I mean new drugs as outcomes, but also in chemistry and new materials. So we may really, see revolutions in drugs and materials in I imagine in the next 10 years it may happen. I think for this country, I think there's a lot of potential because we do have good machine learning, but I think there is a lot of very good, and it's just across the street, biology and chemistry, very strong people. So I think there is a lot of potential to mine here from collaboration, I feel. Thank you.
Thank you. So you think that AI needs a lot of data? And the data are in our biomedical, biochemical, and I don't know which laboratories, and they should be used by AI to bring useful results. Am I right?
And I think that it's okay. So there is it's the simulation. I think there is some data, of course, measurements, but I think the power where it's coming from, at least now, it's a combination of simulation on a molecular level and learning on top of that. So I think, and as a whole community, and this is not just one team, but I think once where I see the potential, we are not on the level there that we would like gather the current powerful languages models are trained on almost entire internet. So we are not quite there, but I think that the simulation is getting more powerful and we start accumulating data and would be able to learn from. I think that's where we are start discovering the patterns in this data and discovering new things. So I think it's a combination of simulation, learning, and then potentially verifying the hypothesis quickly in lab experiments, which maybe become automated or at least partially, or even in sort of existing, if it becomes available, clinical data. So I think that's where it can come, the breakthroughs will come.
Thank you. Josef Urban?
So I probably said it in my talk, but maybe not so explicitly. So I once called it the semantic AI paradise. I gave a talk 5 years ago at the AGI conference that no one shall drive us from the semantic AI paradise. So I sort of see it coming. There will be a big merge between the symbolic methods and the statistical methods. The current statistical methods, like the language models, will very much help us to get there. So you can already see that the language models are getting pretty good in some symbolic tasks, and people are pushing the boundaries and trying to see how far they can go with that. But what will happen will be ubiquitous transformation of what is today natural language, some disconnected databases, some pieces of knowledge flying out there on the internet into one coherent big thing. Like some people today think that the one coherent thing is ChatGPT. Now you have seen Mikuláš's examples. The ChatGPT is not a coherent thing, or at least in some senses. But there will be a way how to, or at least a gradual way, how to turn all this knowledge which is out there into like explainable knowledge, like programs that we will understand and that will be connected by like probabilistically by like these neural networks, statistical models that will be capable to combine all these things. And that's already happening very much. Like a lot of the current startups are about like using ChatGPT to turn things like natural language input into some program, then running that program and doing something again, maybe something more statistical with that, and like really like interleaving these things a lot. So I think this will really be like a major event that will happen in our lives. For me, it's mathematics and physics and sciences, but I think it will happen very quickly in law also. Like basically, all of law will become logically expressed, and we will be running like very powerful mechanical lawyers that will be like combinations of the probabilistic and the symbolic methods. So that's one thing, and I think, but maybe I'm stealing Tomáš's thunder, but I'll anyway say it. I think what will be also very interesting is to come up with the principles that are trying to come up with the development of intelligence from some very minimal, like Kolmogorov complexity, Occam's razor, etc. Like just we have discussed this a couple of times. Like how do you create mathematics, for example? Like if you should say what are just one or two principles that govern development of a body of human knowledge of like mathematics, what would they be? And I think there will be progress in that. Like it again like repeats like people saying that we need to go unsupervised, right? Like this is the like we can absorb a lot of knowledge which is out there, but how have we actually created that? So that, I think, will be like a very interesting technology development.
I do have two additional questions. One of them, do you believe that the lawyers could be completely replaced by reasoning systems equipped with huge volumes of, I don't know, legal documents?
So, like with this replacement, displacement, it's like I guess job displacement happens, but like I think the argument that there is a solid argument that whenever you create tools that increase human productivity, it doesn't really lead to unemployment. It's more like leads to development of more and more advanced fields in which humans are working. Like we will simply all be like very enhanced by all these technologies. We will be doing much more things. So the lawyers will also become much more enhanced. I know if they will be like fully replaced, right? Like it's like saying that scientists will disappear. No, they will just have much better tools, much more powerful tools, allowing them to do science.
So you mean that they will get tools which will enhance their efficiency, which will help them to make the decision, but it would be, I think, like in medical area, that doctors will get some recommendations and they should make decision, final decision. This will be the same probably, according to my opinion. Yeah. And the second question I do have is, you mentioned that if we discover one or two principles, we can make a big progress. You mean in addition to the principle we already know about the human life, or basic principles which are not discovered yet? And
yeah, I meant, for example, no mathematician will give you today an answer what governed the development of mathematics. Like some will say that it's like our attempts to emulate, to simulate and predict the real world, but there are also many other criteria which makes mathematicians think about some areas of mathematics deeply. Like it can be physics that is not yet discovered, which happened in mathematics like several times. So it's not clear to me, and in general I think to mathematicians, like we have some theories how this could go, how to just prime some AI, some autonomous system, which will develop something fairly similar to human mathematics from scratch, without any other principles, just from, let's say, 1 to first principles.
Thank you very much. And Tomáš, please.
Yeah, well, back to the original question, like what could be the things that will impact the society the most in the next 10 years? I would just give the boring answer as before. I think it could be the healthcare, and it's quite likely going to be the language models, which were the areas that I was recommending to support for the future. But to explain maybe more the healthcare, I'm thinking maybe because I think that I keep predicting this already for the last 5 years. I'm not alone. I think that on most of the panels that I have been in the last years, most of the experts actually did agree on that healthcare is actually the area where we have a lot of data. There's a huge amount of money. We as people would want this area to advance, and it's basically obviously going to be much better by using machine learning. At the same time, it's just not happening, and I don't think it's a technological issue. I think it's a social issue. It's that's why it's hard to predict when it will happen, because we have like the healthcare is organized mostly by state organization here. We have like the Ministry of Health. We have the insurance companies that keep most of the money, and then we have the hospitals and the doctors, and just making it all together, basically that all these parts will communicate with each other and somehow allow the significant change of the system to happen. I think that's the real issue, that there would probably need to be at least one person who would take it as his lifetime project and really push it for years against all the resistance, and I don't really see that person at the moment. I think it's needed. So healthcare, in my opinion, there's a huge ways how to make it better. I mentioned already before prevention, because it's always nice that we can discover new drugs by using machine learning. That's certainly true, but I think that it would be even better for us, for people, if we would be able to avoid actually getting ill. Like I mentioned the COVID thing, and there are many statistical patterns, especially when there are new diseases, but also that are different for different individuals, like personalized health recommendations. That's something that machine learning can give us much better than whatever does exist today. And as I said before, I would repeat my prediction that once we get machine learning into healthcare, people will be amazed how good it can actually become and what it can do, in a similar way how many people are now amazed by ChatGPT and what language models can do. Basically, it will be unbelievable for many people how much better the healthcare will become. And I keep predicting that this is going to happen soon, but somehow it's still not happening. So I hope that in the next 10 years we will get there. Then I mentioned the language models as the area where I would like to invest. I also see it as the area that is very likely to change our society in a big way, because it already is happening. So I'm already not really making a prediction, but rather describing the current situation. I still think that there are areas where people will discover that these language tools can be helpful. It can be helpful even for the scientists. I think it was mentioned many times on the panel that we also need this focus on the correctness and verification and ethics and so on. And I think that maybe we can be a little bit weaker on these assumptions, because we can look at different technologies that did work and were never 100% correct. There, for example, there is Jan Šedivý sitting here who was working all his life on speech recognition. Speech recognition never was 100% correct, and it was still good enough to be used. Machine translation also never was 100% correct, but it's pretty good to be used as long as the systems are good enough. There are areas where we don't really need to verify whether everything is fine, but for entertainment, for example, I think the language models can be used in computer games totally fine, and just because they generate sometimes some nonsense doesn't mean that we have to block their usage for the next 10 years. So I think that I would have weaker assumptions about what we need for this technology to be used. But I also mentioned this other area as the first one actually where I would invest, which was the basic research, and I agree what was mentioned just now, that these things are already great, but they can be even better if we would make some further advancements, because honestly, the neural language models as we have them now, of course, there's a lot of scientific PR that tries to convince us that every 2 weeks there's a new language model that is radically better than the previous ones. But if we would be more realistic and look at really the results and numbers in, say, perplexity and some standard benchmarks, then really we are not really making that many advancements. It usually takes many years to move further when it comes to some fundamental qualities of these models to generalize. And I think that maybe we are 1 or 2 more steps away from systems that will be 100 times better when it comes to their ability to, for example, store memory for a longer time, to generalize, to remember information. So I'm kind of hopeful, because there's so much excitement now about language models that people will be working on this technology, and maybe in the next 10 years there will be again some significant change. So not just more GPUs and more training data, but some better ways, maybe approaching the unsupervised learning that was already mentioned as well. Maybe there are some discoveries that are just ahead of us. That's always hard to predict, but maybe we'll get there. And I think that this can be super exciting technology, even for the scientists, because there was one of the original visions of how AGI can be accomplished and how it can work as basically being an assistant for scientists. It was proposed by Ray Solomonov, who was at the first meeting where the name itself, artificial intelligence, was actually developed. So already back then, like some 70 years ago, people were thinking about some systems that will be helping scientists to go through huge amounts of information so that we can process this information and become much more efficient scientists. So maybe that's 10 years ahead of us, maybe a bit longer, but that's something that I think will transform our society in a huge way.
So, said Tomáš Mikolov, I think there is nothing to be added. Healthcare, better language models, and of course to enhance support everywhere where it's possible. And it's task for more than 10 years, I'm quite sure, but we need where to go. The target is here. So it was the best wrap-up of this panel session, and I think it's time to thank all of you for participation. So I would like to thank Robert Babuška, Patrick Perez, Holger Hoss, Josef Šivic, Josef Urban, and Tomáš Mikolov. Thank you very much for participation in this panel and in this symposium. Tomorrow we will continue with the third day. There will be an open day for public, and you can meet many people if you are still staying here and discuss with them what's needed, what's possible, and what's in the focus of interest. Thank you once more for your participation. Thank you.